Hi everyone, welcome to the Simply Learn YouTube channel. This session will be about the top 8 machine learning algorithms. Before we begin, if you love watching tech videos, subscribe to our channel and hit the bell icon to never miss an update. In this session, you will be introduced to machine learning and machine learning algorithms. With the basic understanding, we will start exploring the first algorithm, that is linear regression. You will learn about the applications of linear regression and understand the use case scenario of the algorithm. The next algorithm we have is logistic regression. You will learn about supervised learning and what classification is. Further, you will learn about the applications of logistic regression and compare linear and logistic regression. You will have a hands-on use case scenario of the algorithm. Next, we have is decision tree algorithm. You will learn about the advantages and understand the working of the decision tree. Further, you will have a use case scenario of the algorithm. The next algorithm we have is the support vector machine algorithm. You will learn about the advantages and understand its the use case scenario in Python. Next, we have the naive Bayes algorithm. You will learn about the naive Bayes classifier and learn about its advantages. Then, we will have a demo based on text classification using naive Bayes. Next, we have the k nearest neighbor algorithm. We will learn about the use of KNN and how we choose the factor k. Further, you will have hands on the use case of the algorithm. Next, we have the k-means clustering algorithm. You will understand the working of the algorithm and have a hands-on demo and a use case scenario. At last, we would be having the random forest algorithm. You would be learning about the working and have a hands-on use case scenario of the algorithm.
Profit estimation of a company. If I was going to invest in a company, I would like to know how much money I could expect to make. So we'll take a look at a venture capitalist firm and try to understand which companies they should invest in. So we'll take the idea that we need to decide the companies to invest in. We need to predict the profit the company makes, and we're going to do it based on the company's expenses, and even just a specific expense. In this case, we have our company, we have the different expenses, so we have our R&D, which is your research and development, we have our marketing, we might have the location, we might have what kind of administration it's going through. Based on all this different information, we would like to calculate the profit. Now, in actuality, there's usually about 23 to 27 different markers that they look at if they're a heavy-duty investor. We're only going to take a look at one basic one. We're going to come in, and for simplicity, let's consider a single variable R&D and find out which companies to invest in based on that. So when we take our R&D and we're plotting the profit based on the R&D expenditure, how much money they put into the research and development, and then we look at the profit that goes with that. We can predict a line to estimate the profit. So we can draw a line right through the data. And when you look at that, you can see how much they invest in the R&D is a good marker as to how much profit they're going to have. We can also note that companies spending more on R&D make good profit. So let's invest in the ones that spend a higher rate in their R&D. Let's look at another example of machine learning. Based on the amount of rainfall, how much would be the crop yield? So here we have our crops, we have our rainfall, and we want to know how much we're going to get from our crops this year. So we're going to introduce two variables, independent and dependent. The independent variable is a variable whose value does not change by the effect of other variables and is used to manipulate the dependent variable. It is often denoted as x. In our example, rainfall is the independent variable. This is a wonderful example because you can easily see that we can't control the rain, but the rain does control the crop. So when we talk about the independent variable controlling the dependent variable, let's define dependent variable as a variable whose value change when there is any manipulation in the values of the independent variables. It is often denoted as y. And you can see here our crop yield is dependent variable, and it is dependent on the amount of rainfall received. Now that we've taken a look at a real-life example, let's go a little bit into the theory and some definitions on machine learning and see how that fits together with linear regression. Numerical and categorical values. Let's take our data coming in, and this is kind of random data from any kind of project. We want to divide it up into numerical and categorical. So numerical is numbers, age, salary, height, where categorical would be a description, the color, a dog's breed, gender. Categorical is limited to very specific items, where numerical is a range of information. Now that you've seen the difference between numerical and categorical data, let's take a look at some different machine learning definitions. When we look at our different machine learning algorithms, we can divide them into three areas: supervised, unsupervised, reinforcement. We're only going to look at supervised today. Unsupervised means we don't have the answers and we're just grouping things. Reinforcement is where we give positive and negative feedback to our algorithm to program it, and it doesn't have the information until after the fact. But today we're just looking at supervised because that's where linear regression fits in. In supervised data, we have our data already there and our answers for a group, and then we use that to program our model and come up with an answer. The two most common uses for that is through the regression and classification. Now we're doing linear regression, so we're just going to focus on the regression side. And in the regression, we have simple linear regression, we have multiple linear regression, and we have polynomial linear regression. Now on these three, simple linear regression is the examples we've looked at so far, where we have a lot of data and we draw a straight line through it. Multiple linear regression means we have multiple variables. Remember where we had the rainfall and the crops? We might add additional variables in there, like how much food do we give our crops? When do we harvest them? Those would be additional information add into our model, and that's why it'd be multiple linear regression. And finally, we have polynomial linear regression. That is, instead of drawing a line, we can draw a curved line through it. Now that you see where a regression model fits into the machine learning algorithms, and we're specifically looking at linear regression, let's go ahead and take a look at applications for linear regression. Let's look at a few applications of linear regression. Economic growth, used to determine the economic growth of a country or a state in the coming quarter, can also be used to predict the GDP of a country. Product price can be used to predict what would be the price of a product in the future. We can guess whether it's going to go up or down, or should I buy today. Housing sales, to estimate the number of houses a builder would sell and what price in the coming months. Score predictions, cricket fever, to predict the number of runs a player would score in the coming matches based on the previous performance. I'm sure you can figure out other applications you could use linear regression for. So let's jump in and let's understand linear regression and dig into the theory. Understanding linear regression. Linear regression is the statistical model used to predict the relationship between independent and dependent variables by examining two factors. The first important one is which variables in particular are significant predictors of the outcome variable. And the second one that we need to look at closely is how significant is the regression line to make predictions with the highest possible accuracy. If it's inaccurate, we can't use it. So it's very important we find out the most accurate line we can get. Since linear regression is based on drawing a line through data, we're going to jump back and take a look at some Euclidean geometry. The simplest form of a simple linear regression equation with one dependent and one independent variable is represented by y equals m times x plus c. And if you look at our model here, we plotted 2 points on here, x1 and y1, x2 and y2. Y being the dependent variable, remember that from before, and x being the independent variable. So y depends on whatever x is. M, in this case, is the slope of the line, where m equals the difference in the y2 minus y1 and x2 minus x1. And finally we have c, which is the coefficient of the line, or where it happens to cross the zero axes. Let's go back and look at an example we used earlier of linear regression. We're going to go back to plotting the amount of crop yield based on the amount of rainfall. And here we have our rainfall. Remember, we cannot change rainfall. And we have our crop yield, which is dependent on the rainfall. So we have our independent and our dependent variables. We're going to take this and draw a line through it as best we can through the middle of the data. And then we look at that. We put the red point on the y-axis is the amount of crop yield you can expect for the amount of rainfall, represented by the green dot. So if we have an idea what the rainfall is for this year and what's going on, then we can guess how good our crops are going to be. And we've created a nice line right through the middle to give us a nice mathematical formula. Let's take a look and see what the math looks like behind this. Let's look at the intuition behind the regression line. Now, before we dive into the math and the formulas that go behind this and what's going on behind the scenes, I want you to note that when we get into the case study and we actually apply some Python script, that this math that you're going to see here is already done automatically for you. You don't have to have it memorized. It is, however, good to have an idea what's going on, so if people reference the different terms, you'll know what they're talking about. Let's consider a sample data set with 5 rows and find out how to draw the regression line. We're only going to do 5 rows because if we did like the rainfall with hundreds of points of data, that would be very hard to see what's going on with the mathematics. So we'll go ahead and create our own 2 sets of data, and we have our independent variable x and our dependent variable y. And when x was 1, we got y equals 2. When x was 2, y was 4, and so on and so on. If we go ahead and plot this data on a graph, we can see how it forms a nice line through the middle. You can see where it's kind of grouped going upwards to the right. The next thing we want to know is what the means is of each of the data coming in, the x and the y. The means doesn't mean anything other than the average. So we add up all the numbers and divide by the total. So 1 plus 2 plus 3 plus 4 plus 5 over 5 equals 3. And the same for y, we get 4. If we go ahead and plot the means on the graph, we'll see we get 3, 4, which draws a nice line down the middle. A good estimate. Here we're going to dig deeper into the math behind the regression line. Now remember before I said you don't have to have all these formulas memorized or fully understand them, even though we're going to go into a little more detail of how it works. And if you're not a math whiz and you don't know, if you've never seen the sigma character before, which looks a little bit like an E that's opened up, that just means summation. That's all that is. So when you see the sigma character, it just means we're adding everything in that row. And for computers, this is great because as a programmer, you can easily iterate through each of the XY points and create all the information you need. So in the top half, you can see where we've broken that down into pieces. And as it goes through the first 2 points, it computes the squared value of x, the squared value of y, and x times y. And then it takes all of x and adds them up, all of y adds them up, all of x squared adds them up, and so on and so on. And you can see we have the sum of equal to 15, the sum is equal to 20, all the way up to x times y, where the sum equals 66. This all comes from our formula for calculating a straight line, where y equals the slope times x plus the coefficient c. So we go down below, and we're going to compute more like the averages of these, and we're going to explain exactly what that is in just a minute, and where that information comes from. It's called the square means error. But we'll go into that in detail in a few minutes. All you need to do is look at the formula and see how we've gone about computing it line by line instead of trying to have a huge set of numbers pushed into it. And down here you'll see where the slope m equals, and on the top part, if you read through the brackets, you have the number of data points times the sum of x times y, which we computed one line at a time there, and that's just the 66. And take all that and you subtract it from the sum of x times the sum of y. And those have both been computed. So you have 15 times 20. And on the bottom, we have the number of lines times the sum of x squared, easily computed as 86 for the sum, minus, I'll take all that and subtract the sum of x squared. And we end up, as we come across with our formula, you can plug in all those numbers, which is very easy to do on the computer. You don't have to do the math on a piece of paper or a calculator. And you'll get a slope of 0.6. And you'll get your c coefficient. If you continue to follow through that formula, you'll see it comes out as equal to 2.2. Continuing deeper into what's going behind the scenes, let's find out the predicted values of y for corresponding values of x using the linear equation where m equals 0.6 and c equals 2.2. We're going to take these values and we're going to go ahead and plot them. We're going to predict them, so y equals 0.6 times where x equals 1 plus 2.2 equals 2.8, so on and so on. And here, the blue points represent the actual y values, and the brown points represent the predicted y values based on the model we created. The distance between the actual and predicted values is known as residuals or errors. The best fit line should have the least sum of squares of these errors, also known as e-square. If we put these into a nice chart where you can see x and you can see y, what the actual values were, and you can see y predicted, you can easily see where we take y minus y predicted and we get an answer. What is the difference between those two? And if we square that, y minus y prediction squared, we can then sum those squared values. That's where we get the 0.64 plus the 0.36 plus 1, all the way down until we have a summation equals 2.4. So the sum of squared errors for this regression line is 2.4. We check this error for each line and conclude the best fit line having the least e-square value. In a nice graphical representation, we can see here where we keep moving this line through the data points to make sure the best fit line has the least square distance between the data points and the regression line. Now, we only looked at the most commonly used formula for minimizing the distance. There are lots of ways to minimize the distance between the line and the data points, like sum of squared errors, sum of absolute errors, root mean square error, etc. What you want to take away from this is whatever formula is being used, you can easily, using a computer programming and iterating through the data, calculate the different parts of it. That way, these complicated formulas you see with the different summations and absolute values are easily computed one piece at a time. Up until this point, we've only been looking at two values, x and y. Well, in the real world, it's very rare that you only have two values when you're figuring out a solution. So let's move on to the next topic, multiple linear regression. Let's take a brief look at what happens when you have multiple inputs. So in multiple linear regression, we have, we'll start with the simple linear regression, where we had y equals m plus x plus c, and we're trying to find the value of y. Now with multiple linear regression, we have multiple variables coming in. So instead of having just x, we have x1, x2, x3. And instead of having just one slope, each variable has its own slope attached to it. As you can see here, we have m1, m2, m3, and we still just have the single coefficient. So when you're dealing with multiple linear regression, you basically take your single linear regression and you spread it out. So you have y equals m1 times x1 plus m2 times x2, so on all the way to m to the nth, x to the nth, and then you add your coefficient on there. Implementation of linear regression. Now we get into my favorite part. Let's understand how multiple linear regression works by implementing it in Python. If you remember before, we were looking at a company and just based on its R&D, trying to figure out its profit. We're going to start looking at the expenditure of the company. We're going to go back to that. And we're going to predict its profit. But instead of predicting it just on the R&D, we're going to look at other factors like administration costs, marketing costs, and so on. And from there, we're going to see if we can figure out what the profit of that company is going to be. To start our coding, we're going to begin by importing some basic libraries. And we're going to be looking through the data before we do any kind of linear regression. We're going to take a look at the data to see what we're playing with. Then we'll go ahead and format the data to the format we need to be able to run it in the linear regression model. And then from there, we'll go ahead and solve it and just see how valid our solution is. So let's start with importing the basic libraries. Now, I'm going to be doing this in Anaconda Jupyter Notebook, a very popular IDE. I enjoy it because it's such a visual to look at and it's so easy to use. Just any IDE for Python will work just fine for this. So break out your favorite Python IDE. So here we are in our Jupyter Notebook. Let me go ahead and paste our first piece of code in there. And let's walk through what libraries we're importing. First, we're going to import NumPy as NP. And then I want you to skip one line and look at import pandas as PD. These are very common tools that you need with most of your linear regression. The NumPy, which stands for NumPython, is usually denoted as NP, and you have to almost have that for your sklearn toolbox. So you always import that right off the beginning. Pandas, although you don't have to have it for your sklearn libraries, it does such a wonderful job of importing data, setting it up into a data frame so we can manipulate it rather easily, and it has a lot of tools also in addition to that. So we usually like to use the pandas when we can, and I'll show you what that looks like. The other three lines are for us to get a visual of this data and take a look at it. So we're going to import matplotlibary.pyplot as PLT and then Seaborn as SNS. Seaborn works with the Matplot library. So you have to always import Matplot library and then Seaborn sits on top of it. And we'll take a look at what that looks like. You could use any of your own plotting libraries you want. There's all kinds of ways to look at the data. These are just very common ones, and the Seaborn is so easy to use that it just looks beautiful. It's a nice representation that you can actually take and show somebody. And the final line is the ampersand matplot library inline. That is only because I'm doing an inline IDE. My interface in the Anaconda Jupyter Notebook requires I put that in there, or you're not going to see the graph when it comes up. Let's go ahead and run this. It's not going to be that interesting because we're just setting up variables. In fact, it's not going to do anything. that we can see, but it is importing these different libraries and setup. The next step is load the data set and extract independent and dependent variables. Now, here in the slide, you'll see companies equals pd.read CSV, and it has a long line there with the file at the end, 1000 companies.csv. You're going to have to change this to fit whatever setup you have. And the file itself, you can request. Just go down to the commentary below this video and put a note in there, and Simply Learn will try to get in contact with you and supply you with that file so you can try this coding yourself. So we're going to add this code in here, and we're going to see that I have companies equals pd.reader_csv, and I've changed this path to match my computer, c:/simplylearn/1000_companies.csv. And then below there, we're going to set the x equals to companies under the I location, and because this is companies is a PD data set, I can use this nice notation that says take every row, that's what the first colon is, comma, except for the last column. That's what the second part is, where we have a colon -1, and we want the values set into there. So X is no longer a data set, a pandas data set, but we can easily extract the data from our pandas data set with this notation. And then Y, we're going to set equal to the last row. Well, the question is going to be, what are we actually looking at? So let's go ahead and take a look at that. And we're going to look at the companies.head, which lists the first 5 rows of data. And I'll open up the file in just a second so you can see where that's coming from. But let's look at the data in here as far as the way the pandas sees it. When I hit run, you'll see it breaks it out into a nice setup. This is what pandas, one of the things pandas is really good about, is it looks just like an Excel spreadsheet. You have your rows, and remember, when we're programming, we always start with 0. We don't start with 1. So it shows the first 5 rows. 0, 1, 2, 3, 4, and then it shows your different columns: R&D spend, administration, marketing spend, state, profit. It even notes that the top are column names. It was never told that, but Pandas is able to recognize a lot of things that they're not the same as the data rows. Why don't we go ahead and open this file up in a CSV so you can actually see the raw data. So here I've opened it up as a text editor, and you can see at the top we have R&D spend, comma, administration, comma, marketing spend, comma, state, comma, profit, carriage return. I don't know about you, but I'd go crazy trying to read files like this. That's why we use the pandas. You could also open this up in an Excel and it would separate it, since it is a comma separated variable file. But we don't want to look at this one. We want to look at something we can read rather easily. So let's flip back and take a look at that top part, the first 5 rows. Now, as nice as this format is, where I can see the data, to me it doesn't mean a whole lot. Maybe you're an expert in business and investments and you understand what $165,349.20 compared to the administration cost of $136,897.80, so on, helps to create the profit of $192,261.83. That makes no sense to me whatsoever. No pun intended. So let's flip back here and take a look at our next set of code where we're going to graph it so we can get a better understanding of our data and what it means. So at this point, we're going to use a single line of code to get a lot of information so we can see where we're going with this. Let's go ahead and paste that into our notebook and see what we got going. And so we have the visualization, and again we're using SNS, which is pandas. As you can see, we imported the matplot library, .pyplot as PLT, which then the Seaborn uses. And we imported the Seaborn as SNS. And then that final line of code helps us show this in our inline coding. Without this, it wouldn't display, and you could display it to a file and other means. And that's the matplot library inline with the ampersand at the beginning. So here we come down to the single line of code. Seaborn is great because it actually recognizes the Panda data frame. So I can just take the companies.core for coordinates, and I can put that right into the Seaborn. And when we run this, we get this beautiful plot. And let's just take a look at what this plot means. If you look at this plot, on mine, the colors are probably a little bit more purplish and blue than the original one. We have the columns and the rows. We have R&D spending, we have administration, we have marketing spending, and profit. And if you cross-index any 2 of these, since we're interested in profit, if you cross-index profit with profit, it's going to show up, if you look at the scale on the right, way up in the dark. Why? Because those are the same data. They have an exact correspondence. So R&D spending is going to be the same as R&D spending, and the same thing with administration costs. So right down the middle, you get this dark row, or dark diagonal row that shows that this is the highest corresponding data that's exactly the same. And as it becomes lighter, there's less connections between the data. So we can see with profit, obviously profit is the same as profit. And next, it has a very high correlation with R&D spending, which we looked at earlier. And it has a slightly less connection to marketing spending, and even less to how much money we put into the administration. So now that we have a nice look at the data, let's go ahead and dig in and create some actual useful linear regression models so that we can predict values and have a better profit. Now that we've taken a look at the visualization of this data, we're going to move on to the next step. Instead of just having a pretty picture, we need to generate some hard data, some hard values. So let's see what that looks like. We're going to set up our linear regression model in 2 steps. The first one is we need to prepare some of our data so it fits correctly. And let's go ahead and paste this code into our Jupyter Notebook. And what we're bringing in is we're going to bring in the sklearn pre-processing, where we're going to import the label encoder and the one-hot encoder. To use the label encoder, we're going to create a variable called label encoder and set it equal to capital L label capital E encoder. This creates a class that we can reuse for transferring the labels back and forth. Now about now you should ask, what labels are we talking about? Let's go take a look at the data we processed before and see what I'm talking about here. If you remember when we did the companies.head and we printed the top 5 rows of data, we have our columns going across. We have column 0, which is R&D spending, column 1, which is administration, column 2, which is marketing spending, and column 3 is state. And you'll see under state we have New York, California, Florida. Now, to do a linear regression model, it doesn't know how to process New York. It knows how to process a number. So the first thing we're going to do is we're going to change that New York, California, and Florida, and we're going to change those to numbers. That's what this line of code does here. X equals, and then it has the colon comma 3 in brackets. The first part, the colon comma, means that we're going to look at all the different rows. So we're going to keep them all together. But the only row we're going to edit is the 3rd row. And in there we're going to take the label coder and we're going to fit and transform the X, also the 3rd row. So we're going to take that 3rd row, we're going to set it equal to a transformation. And that transformation basically tells it that instead of having a New York, it has a 0 or a 1 or a 2. And then finally we need to do a one-hot encoder, which equals one-hot encoder categorical features equals 3. And then we take the X and we go ahead and do that equal to one-hot encoder fit transform X to array. This final transformation preps our data for us so it's completely set the way we need it as just a row of numbers. Even though it's not in here, let's go ahead and print X and just take a look at what this data is doing. You'll see you have an array of arrays, and then each array is a row of numbers. And if I go ahead and just do row 0, you'll see I have a nice organized row of numbers that the computer now understands. We'll go ahead and take this out there because it doesn't mean a whole lot to us. It's just a row of numbers. Next, on setting up our data, we have avoiding dummy variable trap. This is very important. Why? Because the computer has automatically transformed our header into the setup, and it's automatically transformed all these different variables. So when we did the encoder created 2 columns. And what we need to do is just have the 1, because it has both the variable and the name. That's what this piece of code does here. Let's go ahead and paste this in here, and we have X equals X colon comma 1 colon. All this is doing is removing that 1 extra column we put in there when we did our one-hot encoder and our label encoding. Let's go ahead and run that. And now we get to create our linear regression model. And let's see what that looks like here. And we're going to do that in 2 steps. The first step is going to be in splitting the data. Now, whenever we create a predictive model of data, we always want to split it up so we have a training set and we have a testing set. That's very important. Otherwise, we'd be very unethical without testing it to see how good our fit is. And then we'll go ahead and create our multiple linear regression model and train it and set it up. Let's go ahead and paste this next piece of code in here, and I'll go ahead and shrink it down a size or 2 so it all fits on one line. So from the sklearn module selection, we're going to import train, test, split. And you'll see that we've created 4 completely different variables. We have capital X train, capital X test, smaller case y train, smaller case y test. That is the standard way that they usually reference these when we're doing different models. You usually see that, a capital X, and you see the train and the test and the lowercase y. What this is X is our data going in. That's our R&D spend, our administration, our marketing. And then Y, which we're training, is the answer. That's the profit. Because we want to know the profit of an unknown entity. So that's what we're going to shoot for in this tutorial. The next part, train, test, split, we take X and we take Y. We've already created those. X has the columns with the data in it, and Y has a column with profit in it. And then we're going to set the test size equals 0.2. That basically means 20%. So 20% of the rows are going to be tested. We're going to just put them off to the side. So since we're using 1,000 lines of data, that means that 200 of those lines we're going to hold off to the side to test for later. And then the random state equals 0. We're going to randomize which ones it picks to hold off to the side. We'll go ahead and run this. It's not overly exciting because it's setting up our variables. But the next step we actually create our linear regression model. Now that we got to the linear regression model, we get that next piece of the puzzle. Let's go ahead and put that code in there and walk through it. So here we go. We're going to paste it in there. And let's go ahead and, since this is a shorter line of code, let's zoom up there so we can get a good look. And we have from the sklearn.linear_model, we're going to import linear regression. Now, I don't know if you recall from earlier when we were doing all the math. Let's go ahead and flip back there and take a look at that. Do you remember this, where we had this long formula on the bottom and we were doing all this summization? And then we also looked at setting it up with the different lines, and then we also looked all the way down to multiple linear regression, where we're adding all those formulas together. All of that is wrapped up in this one section. So what's going on here is I'm going to create a variable called regressor. And the regressor equals the linear regression. That's a linear regression model that has all that math built in. So we don't have to have it all memorized or have to compute it individually. And then we do the regressor.fit. In this case, we do xtrain and ytrain because we're using the training data, x being the data in and y being profit, what we're looking at. And this does all that math for us. So within one click and one line, we've created the whole linear regression model. And we fit the data to the linear regression model. And you can see that when I run the regressor, it gives an output, linear regression. It says copy x equals true, fit intercept equals true, in jobs equal 1, normalize equals false. It's just giving you some general information on what's going on with that regressor model. Now that we've created our linear regression model, let's go ahead and use it. And if you remember, we kept a bunch of data aside. So we're going to do a yPredict variable, and we're going to put in the xTest. And let's see what that looks like. Scroll up a little bit, paste that in here. Predicting the test set results. So here we have yPredict equals regressor.predict xTest going in, and this gives us yPredict. Now because I'm in Jupyter Inline, I can just put the variable up there, and when I hit the run button, it'll print that array out. I could have just as easily done print yPredict. So if you're in a different IDE that's not an inline setup like the Jupyter Notebook, you can do it this way, print yPredict. And you'll see that for the 200 different test variables we kept off to the side, it's going to produce 200 answers. This is what it says the profit are for those 200 predictions. But let's don't stop there. Let's keep going and take a couple look. We're going to take just a short detail here and calculating the coefficients and the intercepts. This gives us a quick flash at what's going on behind the line. We're going to take a short detour here, and we're going to be calculating the coefficient and intercepts. So you can see what those look like. What's really nice about our regressor we created is it already has the coefficients for us. And we can simply just print regressor.coefficient underscore. When I run this, you'll see our coefficients here. And if we can do the regressor coefficient, we can also do the regressor intercept. And let's run that and take a look at that. This all came from the multiple regression model, and we'll flip over so you can remember where this is going into and where it's coming from. You can see the formula down here where y equals m1 times x1 plus m2 times x2 and so on plus c, the coefficient. So these variables fit right into this formula. Y equals slope 1 times column 1 variable plus slope 2 times column 2 variable all the way to the m into the n and x to the n plus c, the coefficient. Or in this case, you have minus 8.89 to the power of 2, etc., times the first column and the second column and the third column. And then our intercept is the minus 103009 point. Boy, it gets kind of complicated when you look at it. This is why we don't do this by hand anymore. This is why we have the computer to make these calculations easy to understand and calculate. Now, I told you that was a short detour, and we're coming towards the end of our script. As you remember from the beginning, I said if we're going to divide this information, we have to make sure it's a valid model, that this model works, and understand how good it works. So, calculating the R-squared value. That's what we're going to use to predict how good our prediction is. And let's take a look at what that looks like in code. And so we're going to use this from sklearn.metrics. We're going to import R2 score. That's the R-squared value. And we're looking at the error. So, in the R2 score, we take our y-test versus our y-predict. Y-test is the actual values we're testing. That was the one that was given to us, so we know are true. The Y-predict of those 200 values is what we think it was true. And when we go ahead and run this, we see we get a 0.9352. That's the R2 score. Now, it's not exactly a straight percentage, so it's not saying it's 93% correct. But you do want that in the upper 90s, and higher, shows that this is a very valid prediction based on the R2 score. And if R-squared value of 0.91, or 92 as we got on our model, because remember it does have a random generation involved, this proves the model is a good model, which means success! Yay! We successfully trained our model with certain predictors and estimated the profit of the companies using linear regression. So now that we have a successful linear regression model, let's take a look at what we went over today and take a look at our key takeaways. First, we have an introduction to machine learning. We talked about some general setup in predicting crops and weather. We saw this that numbers are age, salary, so on. Then we have categorical, color. When we did our actual regression model, we saw that we had numbers, which was dollar amounts, and we had a location, which was Florida and New York, which was categorical, that we had to convert. Next, we have application of a linear regression model. We had some showing there some different applications you could use it for. We had our use case implementation of linear regression, where we dug in deep. It showed how those are set up. We had our multiple linear regression model, so you could see the math behind it. And finally, prediction using the regression line. So we showed you how to predict things on a regression line setup and the actual scripting and code.
Choose from over 300 in-demand skills and get access to 1,000 plus hours of video content for free. Visit SkillUp by Simplilearn. Click on the link in the description to know more.
What is logistic regression? Let's say we have to build a predictive model or a machine learning model to predict whether the passengers of the Titanic ship have survived or not, the shipwreck. So how do we do that? So we use logistic regression to build a model for this. How do we use logistic regression? So we have the information about the passengers, their ID, whether they have survived or not, their class and name and so on and so forth. And we use this information where we already know whether the person has survived or not. That is the labeled information. And we help the system to train based on this information, based on this labeled data. This is known as labeled data. And during the process of building the model, we probably will remove some of the non-essential parameters or attributes here. We only take those attributes which are really required to make these predictions. And once we train the model, we run new data through it, whereby the model will predict whether the passenger has survived or not. Alright, so let's start with what is supervised learning. Supervised learning is one of the two main types of machine learning methods. Here we use what is known as labeled data to help the system learn. This is very similar to how we human beings learn. So let's say you want to teach a child to recognize an apple. How do we do that? We never tell the child, okay, this is an apple has a certain diameter on the top, a certain diameter at the bottom, and this has a certain RGB color. No, we just show an apple to the child and tell the child this is apple. And then next time when we show an apple, child immediately recognizes, yes, this is an apple. Supervised learning works very similar on the similar lines. So where does logistic regression fit into the overall machine learning process? Machine learning is divided into two types, mainly two types. There is a third one called reinforcement learning, but we will not talk about that right now. So one is supervised learning and the other is unsupervised learning. Unsupervised learning uses techniques like clustering and association, and supervised learning uses techniques like classification and regression. Now, supervised learning is used when you have labeled data. You have historical data, then you use supervised learning. When you don't have labeled data, then you used unsupervised learning. In supervised learning, there are two types of techniques that are used, classification and regression, based on what is the kind of problem we are solving. Let's say we want to take the data and classify it. It could be binary classification, like a 0 or a 1. An example of classification we have just seen, whether the passenger has survived or not survived. It's like a 0 or 1. That is known as binary classification. Regression, on the other hand, is you need to predict a value, what is known as a continuous value. Classification is for discrete values. Regression is for continuous values. Let's say you want to predict the share price, or you want to predict the temperature that will be there. What will be the temperature tomorrow? That is where you use regression. Whereas classification are discrete values. Will the customer buy the product or will not buy the product? Will you get a promotion or you will not get a promotion? I hope you're getting the idea. Or it could be multi-class classification as well. Let's say you want to build an image classification model. So the image classification model would take an image as an input and classify into multiple classes, whether this image is of a cat or a dog or an elephant or a tiger. So there are multiple classes, so not necessarily binary classification. So that is known as multi-class classification. So we are going to focus on classification because logistic regression is one of the algorithms used for classification. Now, the name may be a little confusing. In fact, whenever people come across logistic regression, it always causes confusion because the name has regression in it, but we are actually using this for performing classification. Okay, so yes, it is logistic regression, but it is used for classification. And in case you are wondering, is there something similar for regression? Yes, for regression we have linear regression. Keep that in mind. So linear regression is used for regression, logistic regression is used for classification. So in this video, we are going to focus on supervised learning, and within supervised learning, we are going to focus on classification, and then within classification, we are going to focus on logistic regression algorithm. So first of all, classification. So what are the various algorithms available for performing classification? The first one is decision tree. There are of course multiple algorithms, but here we will talk about a few. Decision trees are quite popular and very easy to understand, and therefore they are used for classification. Then we have k-nearest neighbors. This is another algorithm for performing classification. And then there is logistic regression, and this is what we are going to focus on in this video, and we are going to go into a little bit of details about logistic regression. Alright, what is logistic regression? As I mentioned earlier, logistic regression is an algorithm for performing binary classification. So let's take an example and see how this works. Let's say your car has not been serviced for quite a few years, and now you want to find out if it is going to break down in the near future. So this is like a classification problem. Find out whether your car will break down or not. So how are we going to perform this classification? So here's how it looks. If we plot the information along the x and y axis, x is the number of years since the last service was performed, and y is the probability of your car breaking down. And let's say this data was collected from several car users. It's not just your car, but several car users. So that is our labeled data. So the data has been collected, and for the number of years and when the car broke down and what was the probability, and that has been plotted along x and y axis. So this provides an idea, or from this graph we can find out whether your car will break down or not. We'll see how. So first of all, the probability can go from 0 to 1. As you all are aware, probability can be between 0 and 1. And as we can imagine, it is intuitive as well, as the number of years are on the lower side, maybe 1 year, 2 years, or 3 years still after the service, the chances of your car breaking down are very limited, right? So for example, chances of your car breaking down, or the probability of your car breaking down within 2 years of your last service are 0.1 probability. Similarly, 3 years is maybe 0.3 and so on. But as the number of years increases, let's say if it was 6 or 7 years, there is almost a certainty that your car is going to break down. That is what this graph shows. So this is an example of an application of the classification algorithm. And we will see in little details how exactly logistic regression is applied here. One more thing needs to be added here is that the dependent variables outcome is discrete. So if we are talking about whether the car is going to break down or not, so that is a discrete value, the y that we are talking about, the dependent variable that we are talking about. What we are looking at is whether the car is going to break down or not, yes or no. That is what we are talking about. So here the outcome is discrete and not a continuous value. So this is how the logistic regression curve looks. Let me explain a little bit what exactly and how exactly we are going to determine the class, the outcome rather. So for a logistic regression curve, a threshold has to be set saying that because this is a probability calculation, remember this is a probability calculation, and the probability itself will not be 0 or 1. But based on the probability, we need to decide what the outcome should be. So there has to be a threshold. Like for example, 0.5 can be the threshold, let's say in this case. So any value of the probability below 0.5 is considered to be 0, and any value above 0.5 is considered to be 1. So an output of, let's say, 0.8 will mean that the car will break down. So that is considered as an output of 1, and let's say an output of 0.29 is considered as 0, which means that the car will not break down. So that's the way logistic regression works. Now let's do a quick comparison between logistic regression and linear regression, because they both have the term regression in them, so that can cause confusion. So let's try to remove that confusion. So what is linear regression? Linear regression is a process, is once again an algorithm for supervised learning. However, here you're going to find a continuous value. You're going to determine a continuous value. It could be the price of a real estate property. It could be your hike, how much hike you're going to get, or it could be a stock price. These are all continuous values. These are not discrete compared to a yes or a no kind of a response that we are looking for in logistic regression. So this is one example of a linear regression. Let's say the HR team of a company tries to find out what should be the salary hike of an employee. So they collect all the details of their existing employees, their ratings and their salary hikes, what has been given, and that is the labeled information that is available, and the system learns from this. It is trained and it learns from this labeled information, so that when a new employee's information is fed based on the rating, it will determine what should be the hike. So this is a linear regression problem and a linear regression example. Now, salary is a continuous value. You can get 5,000, 5,500, 5,600. It is not discrete like a cat or a dog or an apple or a banana. These are discrete, or a yes or a no. These are discrete values, right? So this, where you're trying to find continuous values, is where we use linear regression. So let's say, just to extend on this scenario, we now want to find out whether this employee is going to get a promotion or not. So we want to find out, that is a discrete problem, right? A yes or no kind of a problem. In this case, we actually cannot use linear regression, even though we may have labeled data. So this is the labeled data. So based on the employee rating, these are the ratings, and then some people got the promotion, and this is the ratings for which people did not get promotion. That is a no. And this is the rating for which people got promotion. We just plotted the data about whether a person has got, an employee has got promotion or not, yes, no, right? So there is nothing in between. And what is the employee's rating? Okay. and ratings can be continuous. That is not an issue. But the output is discrete in this case. Whether employee got promotion, yes, no. Okay, so if we try to plot that and we try to find a straight line, this is how it would look. And as you can see, it doesn't look very right because it looks like there will be a lot of errors. This root mean square error, if you remember, for linear regression would be very, very high. And also the values cannot go beyond 0 or beyond 1. So the graph should probably look somewhat like this, clipped at 0 and 1. But still, the straight line doesn't look right. Therefore, instead of using a linear equation, we need to come up with something different. And therefore, the logistic regression model looks somewhat like this. So we calculate the probability, and if we plot that probability, not in the form of a straight line, but we need to use some other equation. We will see very soon what that equation is. Then it is a gradual process, right? So you see here, people with some of these ratings are not getting any promotions, and then slowly at certain rating they get promotion. So that is a gradual process. And this is how the math behind logistic regression looks. So we are trying to find the odds for a particular event happening. And this is the formula for finding the odds. So the probability of an event happening divided by the probability of the event not happening. So P, if it is the probability of the event happening, probability of the person getting a promotion, and divided by the probability of the person not getting a promotion, that is 1 minus P. So this is how you measure the odds. Now, the values of the odds range from 0 to infinity. So when this probability is 0, then the value of the odds is equal to 0. And when the probability becomes 1, then the value of the odds is 1 by 0, that will be infinity. But the probability itself remains between 0 and 1. Now, this is how an equation of a straight line looks. So y is equal to beta 0 plus beta 1x, where beta 0 is the y-intercept and beta 1 is the slope of the line. If we take the odds equation and take a log of both sides, then this would look somewhat like this. And the term logistic is actually derived from the fact that we are doing this. We take a log of px by 1 minus px. This is an extension of the calculation of odds that we have seen, right? And that is equal to beta 0 plus beta 1x, which is the equation of the straight line. And now from here, if you want to find out the value of px, you will see we can take the exponential on both sides, and then if we solve that equation, we will get the equation of px like this. Px is equal to 1 by 1 plus e to the power of minus beta 0 plus beta 1x. And recall, this is nothing but the equation of the line, which is equal to y. Y is equal to beta 0 plus beta 1x. So this is the equation also known as the sigmoid function, and this is the equation of the logistic regression algorithm. Alright, and if this is plotted, this is how the sigmoid curve is obtained. So let's compare linear and logistic regression, how they are different from each other. Let's go back. So linear regression is solved or used to solve regression problems, and logistic regression is used to solve classification problems. So both are called regression, but linear regression is used for solving regression problems where we predict continuous values, whereas logistic regression is used for solving classification problems where we have to predict discrete values. The response variables in case of linear regression are continuous in nature, whereas here they are categorical or discrete in nature. And linear regression helps to estimate the dependent variable when there is a change in the independent variable, whereas here in case of logistic regression, it helps to calculate the probability or the possibility of a particular event happening. And linear regression, as the name suggests, is a straight line. That's why it's called linear regression, whereas logistic regression is a sigmoid function, and the shape of the curve is S. It's an S-shaped curve. This is another example of application of logistic regression in weather prediction, whether it's going to rain or not rain. Now keep in mind, both are used in weather prediction. If we want to find the discrete values, like whether it's going to rain or not rain, that is a classification problem. We use logistic regression. But if we want to determine what is going to be the temperature tomorrow, then we use linear regression. So just keep in mind that in weather prediction we actually use both. But these are some examples of logistic regression. So we want to find out whether it's going to rain or not, whether it's going to be sunny or not, whether it's going to snow or not. These are all logistic regression examples. A few more examples. Classification of objects. This is again another example of logistic regression. Now here, of course, one distinction is that these are multi-class classification. So logistic regression is not used in its original form, but it is used in a slightly different form. So we say whether it is a dog or not a dog. I hope you understand. So instead of saying is it a dog or a cat or an elephant, we convert this into saying, so because we need to keep it to binary classification. So we say, is it a dog or not a dog? Is it a cat or not a cat? So that's the way logistic regression can be used for classifying objects. Otherwise, there are other techniques which can be used for performing multi-class classification. In healthcare, logistic regression is used to find the survival rate of a patient. So they take multiple parameters like trauma score and age and so on and so forth, and they try to predict the rate of survival. Alright, now finally let's take an example and see how we can apply logistic regression to predict the number that is shown in the image. So this is actually a live demo. I will take you into Jupyter Notebook and show the code. But before that, let me take you through a couple of slides to explain what we are trying to do. So let's say you have an 8x8 image and the image has a number 1, 2, 3, 4, and you need to train your model to predict what this number is. So how do we do this? So the first thing is, obviously, in any machine learning process, you train your model. So in this case, we are using logistic regression. So, and then we provide a training set to train the model, and then we test how accurate our model is with the test data, which means that like any machine learning process, we split our initial data into two parts, training set and test set. With the training set, we train our model, and then with the test set, we test the model till we get good accuracy, and then we use it for inference, right? So that is typical methodology of training, testing, and then deploying of machine learning models. So let's take a look at the code and see what we are doing. So I'll not go line by line, but just take you through some of the blocks. So first thing we do is import all the libraries, and then we basically take a look at the images and see what is the total number of images. We can display using matplotlib some of the images or a sample of these images, and then we split the data into training and test, as I mentioned earlier, and we can do some exploratory analysis, and then we build our model. We train our model with the training set, and then we test it with our test set and find out how accurate our model is using the confusion matrix, the heat map, and use heat map for visualizing this. And I will show you in the code what exactly is the confusion matrix and how it can be used for finding the accuracy. In our example, we get an accuracy of about 0.94, which is pretty good, or 94%, which is pretty good. Alright, so what is a confusion matrix? This is an example of a confusion matrix, and this is used for identifying the accuracy of a classification model, or like a logistic regression model. So the most important part in a confusion matrix is that, first of all, this, as you can see, this is a matrix, and the size of the matrix depends on how many outputs we are expecting. So the most important part here is that the model will be most accurate when we have the maximum numbers in its diagonal. Like in this case, that's why it has almost 93-94%, because the diagonals should have the maximum numbers, and the others other than diagonals, the cells other than the diagonals, should have very few numbers. So here that's what is happening. So there is a 2 here, there is a 1 here, but most of them are along the diagonal. What does this mean? This means that the number that has been fed is 0, and the number that has been detected is also 0. So the predicted value and the actual value are the same. So along the diagonals, that is true, which means that let's take this diagonal, right? If the maximum number is here, that means that like here in this case it is 34, which means that 34 of the images that have been fed, or rather actually there are two misclassifications in there. So 36 images have been fed which have number 4, and out of which 34 have been predicted correctly as number 4, and one has been predicted as number 8, and another one has been predicted as number 9. So these are two misclassifications. Okay, so that is the meaning of saying that the maximum number should be in the diagonal. So if you have all of them, so for an ideal model which has, let's say, 100% accuracy, everything will be only in the diagonal. There will be no numbers other than 0 in all other cells. So that is like a 100% accurate model. Okay, so that's a gist of how to use this matrix, how to use this confusion matrix. I know the name is a little funny sounding, confusion matrix, but actually it is not very confusing. It's very straightforward. So you are just plotting what has been predicted and what is the labeled information, or what is the actual data. That's also known as the ground truth sometimes. Okay, these are some fancy terms that are used. So predicted label and the actual label, that's all it is. Okay, yeah, so we are showing a little bit more information here. So 38 have been predicted, and here you will see that all of them have been predicted correctly. There have been 38 zeros, and the predicted value and the actual value is exactly the same. Whereas in this case, right, it has, there are, I think, 37 plus 5, yeah, 42 have been fed the images. 42 images are of digit 3, and the accuracy is only 37 of them have been accurately predicted. 3 of them have been predicted as number 7, and 2 of them have been predicted as number 8, and so on and so forth. Okay, all right, so with that, let's go into Jupyter Notebook and see how the code looks. So this is the code in Jupyter Notebook for logistic regression. In this particular demo, what we are going to do is train our model to recognize digits, which are the images which have digits from let's say 0 to 5 or 0 to 9, and then we will see how well it is trained and whether it is able to predict these numbers correctly or not. So let's get started. So the first part is, as usual, we are importing some libraries that are required, and then the last line in this block is to load the digits. So let's go ahead and run this code. Then here we will visualize the shape of these digits. So we can see here, if we take a look, this is how the shape is, 1797 by 64. These are like 8 by 8 images. So that's what is reflected in this shape. Now from here onwards, we are basically once again importing some of the libraries that are required, like NumPy and Matplot, and we will take a look at some of the sample images that we have loaded. So this one, for example, creates a figure, and then we go ahead and take a few sample images to see how they look. So let me run this code, and so that it becomes easy to understand. So these are about 5 images, sample images that we are looking at. 0, 1, 2, 3, 4. So this is how the images, this is how the data is. Okay, and based on this, we will actually train our logistic regression model, and then we will test it and see how well it is able to recognize. So the way it works is the pixel information. So as you can see here, this is an 8 by 8 pixel kind of a image, and each pixel, whether it is activated or not activated, that is the information available for each pixel. Now based on the pattern of this activation and non-activation of the various pixels, this will be identified as a 0, for example, right? Similarly, as you can see, so overall each of these numbers actually has a different pattern of the pixel activation, and that's pretty much that our model needs to learn for which number, what is the pattern of the activation of the pixels, right? So that is what we are going to train our model. Okay, so the first thing we need to do is to split our data into training and test data set. right? So whenever we perform any training, we split the data into training and test so that the training data set is used to train the system. So we pass this probably multiple times and then we test it with the test data set, and the split is usually in the form of and there are various ways in which you can split this data. It is up to the individual preferences. In our case here, we are splitting in the form of 23 and 77. So when we say test size as 0.23, that means 23% of that entire data is used for testing, and the remaining 77% is used for training. So there is a readily available function which is called train test split. So we don't have to write any special code for the splitting. It will automatically split the data based on the proportion that we give here, which is test size. So we just give the test size, automatically training size will be determined, and we pass the data that we want to split, and the results will be stored in x_train and y_train for the training data set. And what is x_train? These are the features, right, which is like the independent variable, and y_train is the label, right? So in this case, what happens is we have the input value, which is, or the features value, which is in x_train, and since this is labeled data, for each of them, each of the observations, we already have the label information saying whether this digit is a 0 or a 1 or a 2, so that this is what will be used for comparison to find out whether the system is able to recognize it correctly or there is an error. For each observation, it will compare with this, right? So this is the label. So the same way, x_train, y_train is for the training data set, x_test, y_test is for the test data set. Okay, so let me go ahead and execute this code as well, and then we can go and check quickly what is how many entries are there and in each of these. So x_train, the shape is 1383 by 64, and y_train has 1383 because there is nothing like the second part is not required here. And then x_test shape we see is 414. So actually there are 414 observations in test and 1383 observations in train. So that's basically what these 4 lines of code are saying. Okay, then we import the logistic regression library, and which is a part of scikit-learn. So we don't have to implement the logistic regression process itself. We just call these the function, and let me go ahead and execute that. So that we have the logistic regression library imported. Now we create an instance of logistic regression, right? So logistic regr is an instance of logistic regression, and then we use that for training our model. So let me first execute this code. So these 2 lines. So the first line basically creates an instance of logistic regression model, and then the second line is where we are passing our data, the training data set. Right, this is our the predictors, and this is our target. We are passing this data set to train our model. All right. So once we do this, in this case the data is not large, but by and large the training is what takes usually a lot of time. So we spend in machine learning activities, in machine learning projects, we spend a lot of time for the training part of it. Okay, so here the data set is relatively small, so it was pretty quick. So all right, so now our model has been trained using the training data set, and we want to see how accurate this is. So what we'll do is we will test it out in probably phases. So let me first try out how well this is working for one image. Okay, I will just try it out with one image, the first entry in my test data set, and see whether it is correctly predicting or not. So and in order to test it, so for training purpose we use the fit method. There is a method called fit which is for training the model. And once the training is done, if you want to test for a particular value, new input, you use the predict method. Okay, so let's run the predict method, and we pass this particular image, and we see that the shape is or the prediction is 4. So let's try a few more. Let me see for the next 10. seems to be fine. So let me just go ahead and test the entire data set. Okay, that's basically what we will do. So now we want to find out how accurately this has performed. So we use the score method to find what is the percentage of accuracy, and we see here that it has performed up to 94% accurate. Okay, so that's on this part. Now what we can also do is we can also see this accuracy using what is known as a confusion matrix. So let us go ahead and try that as well, so that we can also visualize how well this model has done. So let me execute this piece of code, which will basically import some of the libraries that are required, and we basically create a confusion matrix, an instance of confusion matrix, by running confusion matrix and passing these values. So this confusion underscore matrix method takes two parameters. One is the y underscore test, and the other is the prediction. So what is the y underscore test? These are the labeled values which we already know for the test data set, and predictions are what the system has predicted for the test data set. Okay, so this is known to us, and this is what the system has, the model has generated. So we kind of create the confusion matrix and we will print it, and this is how the confusion matrix looks. As the name suggests, it is a matrix, and the key point out here is that the accuracy of the model is determined by how many numbers are there in the diagonal. The more the numbers in the diagonal, the better the accuracy is. Okay, and first of all, the total sum of all the numbers in this whole matrix is equal to the number of observations in the test data set. That is the first thing, right? So if you add up all these numbers, that will be equal to the number of observations in the test data set, and then out of that, the maximum number of them should be in the diagonal. That means the accuracy is pretty good. If the numbers in the diagonal are less, and in all other places there are a lot of numbers, which means the accuracy is very low. The diagonal indicates a correct prediction. This means that the actual value is same as the predicted value. Here again, actual value is same as the predicted value, and so on, right? So the moment you see a number here, that means the actual value is something and the predicted value is something else, right? Similarly here, the actual value is something and the predicted value is something else. So that is basically how we read the confusion matrix. Now, how do we find the accuracy? You can actually add up the total values in the diagonal. So it's like 38 plus 44 plus 43 and so on, and divide that by the total number of test observations. That will give you the percentage accuracy using a confusion matrix. Now let us visualize this confusion matrix in a slightly more sophisticated way using a heat map. So we will create a heat map with we'll add some colors as well. It's like a more visually more appealing. So that's the whole idea. So let me run this piece of code, and this is how the heat map looks. And as you can see here, the diagonals again are all the values are here, most of the values. So which means this seems to be reasonably accurate. And yeah, basically the accuracy score is 94%. This is calculated, as I mentioned, by adding all these numbers divided by the total test values, or the total number of observations in test data set. Okay, so this is the confusion matrix for logistic regression. Alright, so now that we have seen the confusion matrix, let's take a quick sample and see how well the system has classified, and we will take a few examples of the data. So if we see here, we picked up randomly a few of them. So this is number 4, which is the actual value, and also the predicted value. Both are 4. This is an image of 0, so the predicted value is also 0. Actual value is of course 0. Then this is the image of 9. So this has also been predicted correctly, 9, and actual value is 9. And this is the image of 1, and again this has been predicted correctly as like the actual value. Okay, so this was a quick demo of logistic regression, how to use logistic regression to identify images. Okay, so let's summarize what we have learned in this video. We discussed about what is logistic regression and how it fits into the overall machine learning. We discussed about the different types of machine learning and how logistic regression is one of the algorithms for classification. And then we compared logistic regression with linear regression because the names may be sounding similar, but these are completely different algorithms. Linear regression is used for predicting continuous values, whereas logistic regression is used for finding discrete values. And then we talked about the math behind logistic regression, and we derived that function as well, the sigmoid function. We did a quick tabular comparison between linear and logistic regression. We saw some examples of day-to-day life, how logistic regression is used for solving some of the classification problems. And then in the end, we looked at the code to see how we can implement logistic regression to train the model to identify images.
If getting your learning started is half the battle, what if you could do that for free? Visit SkillUp by Simplilearn. Click on the link in the description to know more.
So the decision tree, one of the many powerful tools in the machine learning library, begins with a problem. I think I have to buy a car. So in making this question, you want to know, how do I decide which one to buy? And you're going to start asking questions. Is the mileage greater than 20? Is the price less than 15? Will it be sufficient for 6 people? Does it have enough airbag, anti-lock brakes? All these questions come up. Then as we feed all this data in, we make a decision. And that decision comes up, oh, hey, this seems like a good idea. Here's a car. So as we go in through this decision process using a decision tree, we're going to explore this, maybe not in buying a car, but in how to process data. Problems in machine learning. To understand where the decision tree fits into our machine learning tools, we have to understand the basics of some of the machine learning problems. And 3 of the primary ones fall underneath classification, problems with categorical solutions like yes or no, true or false, 1 or 0. This might be, does it belong to a particular group? Yes or no. Then we have regression, problems where there's a continuous value needs to be predicted, like product prices, profit. And you can see here, this is a very simple linear graph. You can guess what the next value is based on the first 4. It kind of follows a straight line going up. And clustering. This is problems where the data needs to be organized to find specific patterns, like in the case of product recommendation. They group all the different products that people just like you viewed on a shopping site and say, if people who bought this also bought this. The most commonly used for the decision tree is for classification, for figuring out, is it red or is it not? Is it a fruit or is it a vegetable? Yes or no? True, false? Left or right, 0, 1. And so when we talk about classification, we're going to look at the basic machine learning. These are the 4 main tools used in classification. There's Naive Bayes, logistic regression, decision tree, and random forest. The first 2 are for simpler data. So if your data is not very complex, you can usually use these to do a fairly good representation by drawing a line through the data or a curve through the data. They work wonderful in a lot of problems. But as things get more complicated, the decision tree comes in. And then if you have a very large amount of data, you start getting into the random forest. So the decision tree is actually a part of the random forest. But today we're just going to focus on the decision tree. What is a decision tree? Let's go through a very simple example before we dig in deep. Decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. Let's start with a simple question. How to identify a random vegetable from a shopping bag? So we have this group of vegetables in here, and we can start off by asking a simple question, is it red? And if it's not, then it's going to be the purple fruit to the left, probably an eggplant. If it's true, it's going to be one of the red fruits. Is the diameter greater than 2? If false, it's going to be what looks to be a red chili. And if it's true, it's going to be a bell pepper from the capsicum family. So it's a capsicum. Problems that decision tree can solve. So let's look at the 2 different categories the decision tree can be used on. It can be used on the classification, the true, false, yes, no, and it can be used on regression, where we figure out what the next value is in a series of numbers or a group of data. In classification, the classification tree will determine a set of logical if-then conditions to classify problems. For example, discriminating between 3 types of flowers based on certain features. In regression, a regression tree is used when the target variable is numerical or continuous in nature. We fit the regression model to the target variable using each of the independent variables. Each split is made based on the sum of squared error. Before we dig deeper into the mechanics of the decision tree, let's take a look at the advantages of using a decision tree, and we'll also take a glimpse at the disadvantages. The first thing you'll notice is that it's simple to understand, interpret, and visualize. It really shines here because you can see exactly what's going on in a decision tree. Little effort is required for data preparation, so you don't have to do special scaling. There's a lot of things you don't have to worry about when using a decision tree. It can handle both numerical and categorical data, as we discovered earlier, and nonlinear parameters don't affect its performance. So even if the data doesn't fit an easy curved graph, you can still use it to create an effective decision or prediction. If we're going to look at the advantages of a decision tree, we also need to understand the disadvantages of a decision tree. The first disadvantage is overfitting. Overfitting occurs when the algorithm captures noise in the data. That means you're solving for one specific instance instead of a general solution for all the data. High variance. The model can get unstable due to small variation in data. Low bias tree. A highly complicated decision tree tends to have a low bias, which makes it difficult for the model to work with new data. Decision tree important terms. Before we dive in further, we need to look at some basic terms. We need to have some definitions to go with our decision tree and the different parts we're going to be using. We'll start with entropy. Entropy is a measure of randomness or unpredictability in the data set. For example, we have a group of animals. In this picture, there's 4 different kinds of animals, and this data set is considered to have a high entropy. You really can't pick out what kind of animal it is based on looking at just the 4 animals as a big clump of entities. So as we start splitting it into subgroups, we come up with our second definition, which is information gain. Information gain. It is a measure of decrease in entropy after the data set is split. So in this case, based on the color yellow, we've split one group of animals on one side as true and those who aren't yellow as false. As we continue down the yellow side, we split based on the height, true or false equals 10, and on the other side, height is less than 10, true or false. And as you see, as we split it, the entropy continues to be less and less and less, and so our information gain is simply the entropy E1 from the top and how it's changed to E2 in the bottom. And we'll look at the deeper math, although you really don't need to know a huge amount of math when you actually do the programming in Python, because it'll do it for you. But we'll look on the actual math at how they compute entropy. Finally, we went over the different parts of our tree, and they call the leaf node. Leaf node carries the classification or the decision, so it's the final end at the bottom. The decision node has 2 or more branches. This is where we're breaking the group up into different parts. And finally, you have the root node. The topmost decision node is known as the root node. How does a decision tree work? Wonder what kind of animals I'll get in the jungle today? Maybe you're the hunter with the gun, or if you're more into photography, you're a photographer with a camera. So let's look at this group of animals and let's try to classify different types of animals based on their features using a decision tree. So the problem statement is to classify the different types of animals based on their features using a decision tree. The data set is looking quite messy and the entropy is high in this case. So let's look at a training set or a training data set. And we're looking at color, we're looking at height, and then we have our different animals. We have our elephants, our giraffes, our monkeys, and our tigers. And they're of different colors and shapes. Let's see what that looks like and how do we split the data. We have to frame the conditions that split the data in such a way that the information gain is the highest. Note, gain is the measure of decrease in entropy after splitting. So the formula for entropy is the sum, that's what this symbol looks like, that looks like kind of like a funky E, of K, where I equals 1 to K. K would represent the number of the different animals in there, where value, or P, value of I, would be the percentage of that animal, times the log base 2 of the same, the percentage of that animal. Let's try to calculate the entropy for the current data set and take a look at what that looks like. And don't be afraid of the math. You don't really have to memorize this math. Just be aware that it's there and this is what's going on in the background. And so we have 3 giraffes, 2 tigers, 1 monkey, 2 elephants, a total of 8 animals gathered. And if we plug that into the formula, we get an entropy that equals 3 over 8. So we have 3 giraffes, a total of 8, times the log. Usually they use base 2 on the log. So log base 2 of 3 over 8 plus, in this case let's say it's the elephants, 2 over 8, 2 elephants over a total of 8 times log base 2, 2 over 8, plus 1 monkey over a total of 8, log base 2, 1 over 8, and plus 2 over 8 of the tigers, log base 2 over 8. And if we plug that into our computer or calculator, I obviously can't do logs in my head, we get an entropy equal to 0.571. The program will actually calculate the entropy of the data set similarly after every split to calculate the gain. Now we're not going to go through each set one at a time to see what those numbers are. We just want you to be aware that this is a formula or the mathematics behind it. Gain can be calculated by finding the difference of the subsequent entropy values after a split. Now we will try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking that the gain we get out of them. The condition that gives us the highest gain will be used to make the first split. Can you guess what that first split will be just by looking at this image? As a human, it's probably pretty easy to split it. Let's see if you're right. If you guessed the color yellow, you're correct. Let's say the condition that gives us the maximum gain is yellow. So we will split the data based on the color yellow. If it's true, that group of animals goes to the left. If it's false, it goes to the right. The entropy after the splitting has decreased considerably. However, we still need some splitting at both the branches to attain an entropy value equal to 0. So we decide to split both the nodes using height as a condition. Since every branch now contains single label type, we can say that entropy in this case has reached the least value. And here you see we have the giraffes, the tigers, the monkey, and the elephants all separated into their own groups. This tree can now predict all the classes of animals present in the dataset with 100% accuracy. That was easy. Use case, loan repayment prediction. Let's get into my favorite part and open up some Python and see what the programming code and the scripting looks like. In here, we're going to want to do a prediction. And we start with this individual here who's requesting to find out how good his customers are going to be, whether they're going to repay their loan or not for his bank. And from that, we want to generate a problem statement to predict if a customer will repay loan amount or not, and then we're going to be using the decision tree algorithm in Python. Let's see what that looks like, and let's dive into the code. In our first few steps of implementation, we're going to start by importing the necessary packages that we need from Python, and we're going to load up our data and take a look at what the data looks like. So the first thing I need something to edit my Python and run it in. So let's flip on over, and here I'm using the Anaconda Jupyter Notebook. Now you can use any Python IDE you like to run it in, but I find the Jupyter Notebook's really nice for doing things on the fly. And let's go ahead and just paste that code in the beginning. And before we start, let's talk a little bit about what we're bringing in. And then we're going to do a couple things in here where I have to make a couple changes as we go through this first part of the import. The first thing we bring in is NumPy as NP. That's very standard. When we're dealing with mathematics, especially with very complicated machine learning tools, you almost always see the NumPy come in for your numbers. It's called NumPython. It has your mathematics in there. In this case, we actually could take it out, but generally you'll need it for most of your different things you work with. And then we're going to use pandas as PD. That's also a standard. The pandas is a data frame setup, and you can liken this to taking your basic data and storing it in a way that looks like an Excel spreadsheet. So as we come back to this, when you see NP or PD, those are very standard uses, you'll know that that's the pandas, and I'll show you a little bit more when we explore the data in just a minute. Then we're going to need to split the data, so I'm going to bring in our train, test, and split, and this is coming from the sklearn package cross-validation. In just a minute, we're going to change that, and we'll go over that too. And then there's also the sk.tree import decision tree classifier. That's the actual tool we're using. Remember I told you don't be afraid of the mathematics, it's going to be done for you. Well, the decision tree classifier has all that mathematics in there for you, so you don't have to figure it back out again. And then we have sklearn.metrics for accuracy score. We need to score our setup. That's the whole reason we're splitting it between the training and testing data. And finally, we still need the sklearn import tree. And that's just the basic tree function is needed for the decision tree classifier. And finally, we're going to load our data down here. And I'm going to run this, and we're going to get two things on here. One, we're going to get an error, and two, we're going to get a warning. Let's see what that looks like. So the first thing we had is we have an error. Why is this error here? Well, it's looking at this and it says, I need to read a file. And when this was written, the person who wrote it, this is their path where they stored the file. So let's go ahead and fix that. And I'm going to put in here my file path. I'm just going to call it full file name. And you'll see it's on my C drive, and there's this very lengthy setup on here where I stored the data2.csv file. Don't worry too much about the full path because on your computer it'll be different. The data.2csv file was generated by Simplilearn. If you want a copy of that, you can comment down below and request it here in the YouTube. And then if I'm going to give it a name, full file name, I'm going to go ahead and change it here to full file name. So let's go ahead and run it now and see what happens. And we get a warning. When you're coding, understanding these different warnings and these different errors that come up is probably the hardest lesson to learn. So let's just go ahead and take a look at this and use this as an opportunity to understand what's going on here. If you read the warning, it says the cross-validation is depreciated. So it's a warning on it's being removed. And it's going to be moved in favor of the model selection. So if we go up here, we have sklearn.cross-validation. And if you research this and go to the sklearn site, you'll find out that you can actually just swap it right in there with model selection. And so when I come in here and I run it again, that removes a warning. What they've done is they've had two different developers develop it in two different branches. And then they decided to keep one of those and eventually get rid of the other one. That's all that is. And very easy and quick to fix. Before we go any further, I went ahead and opened up the data from this file. Remember the data file we just loaded on here, the data_2.csv. Let's talk a little bit more about that and see what that looks like both as a text file, because it's a comma-separated variable file, and in a spreadsheet. This is what it looks like as a basic text file. You can see at the top they've created a header, and it's got 5 columns, and each column has data in it. And let me flip this over because we're also going to look at this in an actual spreadsheet so you can see what that looks like. And here I've opened it up in the OpenOffice Calc, which is pretty much the same as Excel, and zoomed in, and you can see we've got our columns and our rows of data. A little easier to read in here. We have a result, yes, yes, no. We have initial payment, last payment, credit score, house number. If we scroll way down, we'll see that this occupies 1,001 lines of code, or lines of data, with the first one being a column and then 1,000 lines of data. Now, as a programmer, if you're looking at a small amount of data, I usually start by pulling it up in different sources so I can see what I'm working with. But in larger data, you won't have that option. It'll just be too large. So you need to either bring in a small amount that you can look at it like we're doing right now, or we can start looking at it through the Python code. So let's go ahead and move on and take the next couple steps to explore the data using Python. Let's go ahead and see what it looks like in Python to print the length and the shape of the data. So let's start by printing the length of the database. We can use a simple len function from Python. And when I run this, you'll see that it's 1,000 long. And that's what we expected. There's 1,000 lines of data in there if you subtract the column head. And this is one of the nice things when we did the balance data from the Panda Read CSV. You'll see that the header is row 0, so it automatically removes a row and then shows the data separate. It does a good job sorting that data out for us. And then we can use a different function, and let's take a look at that. And again, we're going to utilize the tools in Panda. And since the balance underscore data was loaded as a Panda data frame, we can do a shape on it. And let's go ahead and run the shape and see what that looks like. What's nice about this shape is not only does it give me the length of the data, we have 1,000 lines, it also tells me there's 5 columns. So when we were looking at the data, we had 5 columns of data. And then let's take one more step to explore the data using Python. And now that we've taken a look at the length and the shape, let's go ahead and use the pandas module for head, another beautiful thing in the data set that we can utilize. So let's put that on our sheet here, and we have print data set and balance data.head. And this is a pandas print statement of its own. So it has its own print feature in there. And then we went ahead and gave a label for our print job here of data set, just a simple print statement. And when we run that, And let's just take a closer look at that. Let me zoom in here. There we go. Pandas does such a wonderful job of making this a very clean, readable data set. So you can look at the data, you can look at the column headers, you can have it, when you put it as the head, it prints the first 5 lines of the data. And we always start with 0. So we have 5 lines, we have 0, 1, 2, 3, 4 instead of 1, 2, 3, 4, 5. That's a standard scripting and programming set, as you want to start with the 0 position. And that is what the data head does. It pulls the first 5 rows of data, puts it in a nice format that you can look at and view. Very powerful tool to view the data. So instead of having to flip and open up an Excel spreadsheet or open Office Calc or trying to look at a Word doc where it's all scrunched together and hard to read, you can now get a nice open view of what you're working with. We're working with a shape of 1,000 long, 5 wide, so we have 5 columns, and we do the full data head. You can actually see what this data looks like. The initial payment, last payment, credit scores, house number. So let's take this, now that we've explored the data, and let's start digging into the decision tree. So in our next step, we're going to train and build our data tree. And to do that, we need to first separate the data out. We're going to separate it into 2 groups so that we have something to actually train the data with, and then we have some data on the side to test it, to see how good our model is. Remember, with any of the machine learning, you always want to have some kind of test set to weigh it against, so you know how good your model is when you distribute it. Let's go ahead and break this code down and look at it in pieces. So first we have our X and Y. Where do X and Y come from? Well, X is going to be our data, and Y is going to be the answer or the target. You can look at it as source and target. In this case, we're using X and Y to denote the data in and the data that we're actually trying to guess what the answer is going to be. And so to separate it, we can simply put in X equals the balance of the data.values. The first brackets means that we're going to select all the lines in the database. So it's all the data. And the second one says we're only going to look at columns 1 through 5. Remember, we always start with 0. 0 is a yes or no, and that's whether the loan went default or not. So we want to start with 1. If we go back up here, that's the initial payment, and it goes all the way through the house number. Well, if we want to look at 1 through 5, we can do the same thing for Y, which is the answers, and we're going to set that just equal to the 0 row. So it's just the 0 row, and then it's all rows going in there. So now we've divided this into 2 different data sets. One of them with the data going in, and one with the answers. Next, we need to split the data. And here you'll see that we have it split into 4 different parts. The first one is your X training, your X test, your Y train, your Y test. Simply put, we have X going in, where we're going to train it, and we have to know the answer to train it with. And then we have X test, where we're going to test that data. And we have to know in the end what the Y was supposed to be. And that's where this train test split comes in, that we loaded earlier in the modules. This does it all for us. And you can see they set the test size equal to 0.3, so that's roughly 30% will be used in the test. And then we use a random state, so it's completely random which rows it takes out of there. And then finally we get to actually build our decision tree. And they've called it here CLF_entropy. That's the actual decision tree, or decision tree classifier. And in here they've added a couple variables, which we'll explore in just a minute. And then finally, we need to fit the data to that. So we take our CLF entropy that we created, and we fit the X train, and since we know the answers for X train or the Y train, we go ahead and put those in. And let's go ahead and run this. And what most of these sklearn modules do is when you set up the variable, in this case when we set the CLF entropy equal to decision tree classifier, it automatically prints out what's in that decision tree. There's a lot of variables you can play with in here, and it's quite beyond the scope of this tutorial to go through all of these and how they work. But we're working on entropy, that's one of the options. We've added that it's completely a random state of 100, so 100%. And we have a max depth of 3. Now the max depth, if you remember above when we were doing the different graphs of animals, means it's only going to go down 3 layers before it stops. And then we have minimal samples of leaves as 5. So it's going to have at least 5 leaves at the end. So I'll have at least 3 splits, or I'll have no more than 3 layers, and at least 5 end leaves with the final result at the bottom. Now that we've created our decision tree classifier, not only created it but trained it. Let's go ahead and apply it and see what that looks like. So let's go ahead and make a prediction and see what that looks like. We're going to paste our predict code in here. And before we run it, let's just take a quick look at what it's doing here. We have a variable yPredict that we're going to do. And we're going to use our variable CLF entropy that we created. And then you'll see .predict. And that's very common in the sklearn modules that their different tools have the predict when you're actually running a prediction. In this case, we're going to put our X-test data in here. Now, if you delivered this for use, an actual commercial use, and distributed it, this would be the new loans you're putting in here to guess whether the person's going to be pay them back or not. In this case, though, we need to test out the data and just see how good our sample is, how good of our tree does at predicting the loan payments. And finally, since Anaconda Jupyter Notebook works as a command line for Python, we can simply put the yPredictEn to print it. I could just as easily have put the print and put brackets around yPredictEn to print it out. We'll go ahead and do that. It doesn't matter which way you do it. And you'll see right here that it runs a prediction. This is roughly 300 in here. Remember, it's 30% of 1,000, so you should have about 300 answers in here. And this tells you which each one of those lines of our test went in there, and this is what our yPredict came out. So let's move on to the next step, where we're going to take this data and try to figure out just how good a model we have. So here we go. Since sklearn does all the heavy lifting for you and all the math, we have a simple line of code to let us know what the accuracy is. And let's go ahead and go through that and see what that means and what that looks like. Let's go ahead and paste this in, and let me zoom in a little bit. There we go. So you have a nice full picture. And we'll see here we're just going to do a print accuracy is, and then we do the accuracy score. And this was something we imported earlier, if you remember at the very beginning. Let me just scroll up there real quick so you can see where that's coming from. That's coming from here, down here, from sklearn.metrics import accuracy score. And you could probably run a script, make your own script to do this very easily. How accurate is it? How many out of 300 do we get right? And so we put in our y-test, that's the one we ran the predict on. And then we put in our yPredictEn, that's the answers we got. And we're just going to multiply that by 100, because this is just going to give us an answer as a decimal. And we want to see it as a percentage. And let's run that and see what it looks like. And if you see here, we got an accuracy of 93.66667. So when we look at the number of loans and we look at how good our model fit, we can tell people it has about a 93.6 fitting to it. So just a quick recap on that. We now have accuracy set up on here. And so we have created a model that uses the decision tree algorithm to predict whether a customer will repay the loan or not. The accuracy of the model is about 94.6%. The bank can now use this model to decide whether it should approve the loan request from a particular customer or not. And so this information is really powerful. We may not be able to, as individuals, understand all these numbers because they have thousands of numbers that come in. But you can see that this is a smart decision for the bank to use a tool like this to help them to predict how good their profit's going to be off of the loan balances and how many are going to default or not. So we've had a lot of fun learning about decision trees. So let's take a look at the key takeaways that we've covered today. What is machine learning? We covered up some different aspects of machine learning and what that is utilized in your everyday life and what you can use it for predicting, for describing, for guessing what the next outcome is, for storing information. We looked at the three main types of machine learning: supervised learning, unsupervised learning, and reinforced learning. We looked at problems in machine learning and what it solves: classification, regression, and clustering. Finally, we went through how does the decision tree work, where we looked at the hunter and he's trying to sort out the different animals and what kind of animals they are. And then we rolled up our sleeves and did our Python coding and actually applied it to a data set. So the decision tree, one of the many powerful tools in the machine learning library, begins with a problem. I think I have to buy a car. So in making this question, you want to know, how do I decide which one to buy? And you're going to start asking questions. Is the mileage greater than 20? Is the price less than 15? Will it be sufficient for 6 people? Does it have enough airbag, anti-lock brakes? All all these questions come up. Then as we feed all this data in, we make a decision. And that decision comes up, oh, hey, this seems like a good idea. Here's a car. So as we go in through this decision process, using a decision tree, we're going to explore this, maybe not in buying a car, but in how to process data. Problems in machine learning. To understand where the decision tree fits into our machine learning tools, we have to understand the basics of some of the machine learning problems. And three of the primary ones fall underneath classification, problems with categorical solutions like yes or no, true or false, 1 or 0. This might be, does it belong to a particular group? Yes or no. Then we have regression, problems where there's a continuous value needs to be predicted, like product prices, profit. And you can see here, this is a very simple linear graph. You can guess what the next value is based on the first 4. It kind of follows a straight line going up. And clustering. This is problems where the data needs to be organized to find specific patterns, like in the case of product recommendation. They group all the different products that people just like you viewed on a shopping site and say, if people who bought this also bought this. The most commonly used for the decision tree is for classification, for figuring out, is it red or is it not? Is it a fruit or is it a vegetable? Yes or no? True, false? Left or right, 0, 1. And so when we talk about classification, we're going to look at the basic machine learning. These are the 4 main tools used in classification. There's Naive Bayes, logistic regression, decision tree, and random forest. The first 2 are for simpler data. So if your data is not very complex, you can usually use these to do a fairly good representation by drawing a line through the data or a curve through the data. They work wonderful in a lot of problems. But as things get more complicated, the decision tree comes in. And then if you have a very large amount of data, you start getting into the random forest. So the decision tree is actually a part of the random forest. But today we're just going to focus on the decision tree. What is a decision tree? Let's go through a very simple example before we dig in deep. Decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. Let's start with a simple question. How to identify a random vegetable from a shopping bag? So we have this group of vegetables in here, and we can start off by asking a simple question, is it red? And if it's not, then it's going to be the purple fruit to the left, probably an eggplant. If it's true, it's going to be one of the red fruits. Is the diameter greater than 2? If false, it's going to be what looks to be a red chili. And if it's true, it's going to be a bell pepper from the capsicum family. So it's a capsicum. Problems that decision tree can solve. So let's look at the 2 different categories the decision tree can be used on. It can be used on the classification, the true, false, yes, no, and it can be used on regression, where we figure out what the next value is in a series of numbers or a group of data. In classification, the classification tree will determine a set of logical if-then conditions to classify problems. For example, discriminating between 3 types of flowers based on certain features. In regression, a regression tree is used when the target variable is numerical or continuous in nature. We fit the regression model to the target variable using each of the independent variables. Each split is made based on the sum of squared error. Before we dig deeper into the mechanics of the decision tree, let's take a look at the advantages of using a decision tree, and we'll also take a glimpse at the disadvantages. The first thing you'll notice is that it's simple to understand, interpret, and visualize. It really shines here because you can see exactly what's going on in a decision tree. Little effort is required for data preparation, so you don't have to do special scaling. There's a lot of things you don't have to worry about when using a decision tree. It can handle both numerical and categorical data, as we discovered earlier, and nonlinear parameters don't affect its performance. So even if the data doesn't fit an easy curved graph, you can still use it to create an effective decision or prediction. If we're going to look at the advantages of a decision tree, we also need to understand the disadvantages of a decision tree. The first disadvantage is overfitting. Overfitting occurs when the algorithm captures noise in the data. That means you're solving for one specific instance instead of a general solution for all the data. High variance. The model can get unstable due to small variation in data. Low bias tree. A highly complicated decision tree tends to have a low bias, which makes it difficult for the model to work with new data. Decision tree, important terms. Before we dive in further, we need to look at some basic terms. We need to have some definitions to go with our decision tree and the different parts we're going to be using. We'll start with entropy. Entropy is a measure of randomness or unpredictability in the data set. For example, we have a group of animals. In this picture, there's 4 different kinds of animals, and this data set is considered to have a high entropy. You really can't pick out what kind of animal it is based on looking at just the 4 animals as a big clump of entities. So as we start splitting it into subgroups, we come up with our second definition, which is information gain. Information gain. It is a measure of decrease in entropy after the data set is split. So in this case, based on the color yellow, we've split one group of animals on one side as true and those who aren't yellow as false. As we continue down the yellow side, we split based on the height, true or false equals 10, and on the other side, height is less than 10, true or false. And as you see, as we split it, the entropy continues to be less and less and less, and so our information gain is simply the entropy E1 from the top and how it's changed to E2 in the bottom. And we'll look at the deeper math, although you really don't need to know a huge amount of math when you actually do the programming in Python, because it'll do it for you. But we'll look on the actual math at how they compute entropy. Finally, we went over the different parts of our tree, and they call the leaf node. Leaf node carries the classification or the decision, so it's the final end at the bottom. The decision node has 2 or more branches. This is where we're breaking the group up into different parts. And finally, you have the root node. The topmost decision node is known as the root node. How does a decision tree work? Wonder what kind of animals I'll get in the jungle today? Maybe you're the hunter with a gun, or if you're more into photography, you're a photographer with a camera. So let's look at this group of animals and let's try to classify different types of animals based on their features using a decision tree. So the problem statement is to classify the different types of animals based on their features using a decision tree. The data set is looking quite messy and the entropy is high in this case. So let's look at a training set or a training data set. And we're looking at color, we're looking at height, and then we have our different animals. We have our elephants, our giraffes, our monkeys, and our tigers. And they're of different colors and shapes. Let's see what that looks like and how do we split the data. We have to frame the conditions that split the data in such a way that the information gain is the highest. Note, gain is the measure of decrease in entropy after splitting. So the formula for entropy is the sum, that's what this symbol looks like, that looks like kind of like a funky E, of K, where I equals 1 to K. K would represent the number of the different animals in there, where value, or P, value of I, would be the percentage of that animal, times the log base 2 of the same, the percentage of that animal. Let's try to calculate the entropy for the current data set and take a look at what that looks like. And don't be afraid of the math. You don't really have to memorize this math. Just be aware that it's there and this is what's going on in the background. And so we have 3 giraffes, 2 tigers, 1 monkey, 2 elephants, a total of 8 animals gathered. And if we plug that into the formula, we get an entropy that equals 3 over 8. So we have 3 giraffes, a total of 8, times the log. Usually they use base 2 on the log. So log base 2 of 3 over 8 plus, in this case let's say it's the elephants, 2 over 8, 2 elephants over a total of 8 times log base 2, 2 over 8, plus 1 monkey over a total of 8, log base 2, 1 over 8, and plus 2 over 8 of the tigers, log base 2 over 8. And if we plug that into our computer or calculator, I obviously can't do logs in my head, we get an entropy equal to 0.571. The program will actually calculate the entropy of the data set similarly after every split to calculate the gain. Now we're not going to go through each set one at a time to see what those numbers are. We just want you to be aware that this is a formula or the mathematics behind it. Gain can be calculated by finding the difference of the subsequent entropy values after a split. Now we will try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking that the gain we get out of them. The condition that gives us the highest gain will be used to make the first split. Can you guess what that first split will be just by looking at this image? As a human, it's probably pretty easy to split it. Let's see if you're right. If you guessed the color yellow, you're correct. Let's say the condition that gives us the maximum gain is yellow. So we will split the data based on the color yellow. If it's true, that group of animals goes to the left. If it's false, it goes to the right. The entropy after the splitting has decreased considerably. However, we still need some splitting at both the branches to attain an entropy value equal to 0. So we decide to split both the nodes using height as a condition. Since every branch now contains single label type, we can say that entropy in this case has reached the least value. And here you see we have the giraffes, the tigers, the monkey, and the elephants all separated into their own groups. This tree can now predict all the classes of animals present in the dataset with 100% accuracy. That was easy. Use case, loan repayment prediction. Let's get into my favorite part and open up some Python and see what the programming code and the scripting looks like. In here, we're going to want to do a prediction. And we start with this individual here who's requesting to find out how good his customers are going to be, whether they're going to repay their loan or not for his bank. And from that, we want to generate a problem statement to predict if a customer will repay loan amount or not, and then we're going to be using the decision tree algorithm in Python. Let's see what that looks like, and let's dive into the code. In our first few steps of implementation, we're going to start by importing the necessary packages that we need from Python, and we're going to load up our data and take a look at what the data looks like. So the first thing I need something to edit my Python and run it in. So let's flip on over, and here I'm using the Anaconda Jupyter Notebook. Now you can use any Python IDE you like to run it in, but I find the Jupyter Notebook's really nice for doing things on the fly. And let's go ahead and just paste that code in the beginning. And before we start, let's talk a little bit about what we're bringing in. And then we're going to do a couple things in here where I have to make a couple changes as we go through this first part of the import. The first thing we bring in is NumPy as NP. That's very standard. When we're dealing with mathematics, especially with very complicated machine learning tools, you almost always see the NumPy come in for your numbers. It's called NumPy. It has your mathematics in there. In this case, we actually could take it out, but generally you'll need it for most of your different things you work with. And then we're going to use pandas as PD. That's also a standard. The pandas is a data frame setup, and you can liken this to taking your basic data and storing it in a way that looks like an Excel spreadsheet. So as we come back to this, when you see NP or PD, those are very standard uses, you'll know that that's the pandas, and I'll show you a little bit more when we explore the data in just a minute. Then we're going to need to split the data, so I'm going to bring in our train, test, and split, and this is coming from the sklearn package cross-validation. In just a minute, we're going to change that, and we'll go over that too. And then there's also the sk.tree import decision tree classifier. That's the actual tool we're using. Remember I told you don't be afraid of the mathematics, it's going to be done for you. Well, the decision tree classifier has all that mathematics in there for you, so you don't have to figure it back out again. And then we have sklearn.metrics for accuracy score. We need to score our setup. That's the whole reason we're splitting it between the training and testing data. And finally, we still need the sklearn import tree. And that's just the basic tree function is needed for the decision tree classifier. And finally, we're going to load our data down here. And I'm going to run this, and we're going to get two things on here. One, we're going to get an error, and two, we're going to get a warning. Let's see what that looks like. So the first thing we had is we have an error. Why is this error here? Well, it's looking at this, it says, I need to read a file. And when this was written, the person who wrote it, this is their path where they stored the file. So let's go ahead and fix that. And I'm going to put in here my file path. I'm just going to call it full file name. And you'll see it's on my C drive, and there's this very lengthy setup on here where I stored the data2.csv file. Don't worry too much about the full path because on your computer it'll be different. The data.2csv file was generated by Simplilearn. If you want a copy of that, you can comment down below and request it here in the YouTube. And then if I'm going to give it a name, full file name, I'm going to go ahead and change it here to full file name. So let's go ahead and run it now and see what happens. And we get a warning. When you're coding, understanding these different warnings and these different errors that come up is probably the hardest lesson to learn. So let's just go ahead and take a look at this and use this as an opportunity to understand what's going on here. If you read the warning, it says the cross-validation is depreciated. So it's a warning on it's being removed. And it's going to be moved in favor of the model selection. So if we go up here, we have sklearn.cross-validation. And if you research this and go to the sklearn site, you'll find out that you can actually just swap it right in there with model selection. And so when I come in here and I run it again, that removes a warning. What they've done is they've had two different developers develop it in two different branches. And then they decided to keep one of those and eventually get rid of the other one. That's all that is, and very easy and quick to fix. Before we go any further, I went ahead and opened up the data from this file. Remember the data file we just loaded on here, the data_2.csv. Let's talk a little bit more about that and see what that looks like both as a text file, because it's a comma-separated variable file, and in a spreadsheet. This is what it looks like as a basic text file. You can see at the top they've created a header, and it's got 1, 2, 3, 4, 5 columns, and each column has data in it. And let me flip this over because we're also going to look at this in an actual spreadsheet so you can see what that looks like. And here I've opened it up in the OpenOffice Calc, which is pretty much the same as Excel, and zoomed in, and you can see we've got our columns and our rows of data. A little easier to read in here. We have a result, yes, yes, no. We have initial payment, last payment, credit score, house number. If we scroll way down, we'll see that this occupies 1,001 lines of code, or lines of data, with the first one being a column and then 1,000 lines of data. Now, as a programmer, if you're looking at a small amount of data, I usually start by pulling it up in different sources so I can see what I'm working with. But in larger data, you won't have that option. It'll just be too large. So you need to either bring in a small amount that you can look at it like we're doing right now, or we can start looking at it through the Python code. So let's go ahead and move on and take the next couple steps to explore the data using Python. Let's go ahead and see what it looks like in Python to print the length and the shape of the data. So let's start by printing the length of the database. We can use a simple len function from Python. And when I run this, you'll see that it's 1,000 long. And that's what we expected. There's 1,000 lines of data in there if you subtract the column head. And this is one of the nice things when we did the balance data from the Panda Read CSV. You'll see that the header is row 0, so it automatically removes a row and then shows the data separate. It does a good job sorting that data out for us. And then we can use a different function, and let's take a look at that. And again, we're going to utilize the tools in Panda. And since the balance_data was loaded as a Panda data frame, we can do a shape on it. And let's go ahead and run the shape and see what that looks like. What's nice about this shape is not only does it give me the length of the data, we have 1,000 lines, it also tells me there's 5 columns. So when we were looking at the data, we had 5 columns of data. And then let's take one more step to explore the data using Python. And now that we've taken a look at the length and the shape, let's go ahead and use the pandas module for head, another beautiful thing in the data set that we can utilize. So let's put that on our sheet here, and we have print data set and balance data.head. And this is a pandas print statement of its own. So it has its own print feature in there. And then we went ahead and gave a label for our print job here of dataset, just a simple print statement. And when we run that, and let's just take a closer look at that. Let me zoom in here. There we go. Pandas does such a wonderful job of making this a very clean, readable data set. So you can look at the data, you can look at the column headers, you can have it, when you put it as the head, it prints the first 5 lines of the data. And we always start with 0. So when we have 5 lines, we have 0, 1, 2, 3, 4 instead of 1, 2, 3, 4, 5. That's a standard scripting and programming set, as you want to start with the 0 position. And that is what the data head does. It pulls the first 5 rows of data, puts it in a nice format that you can look at and view. Very powerful tool to view the data. So instead of having to flip and open up an Excel spreadsheet or OpenOffice Calc or trying to look at a Word doc where it's all scrunched together and hard to read, you can now get a nice open view of what you're working with. We're working with a shape of 1,000 long, 5 wide, so we have 5 columns, and we do the full data head. You can actually see what this data looks like. The initial payment, last payment, credit scores, house number. So let's take this, now that we've explored the data, and let's start digging into the decision tree. So in our next step, we're going to train and build our data tree. And to do that, we need to first separate the data out. We're going to separate it into two groups so that we have something to actually train the data with, and then we have some data on the side to test it, to see how good our model is. Remember, with any of the machine learning, you always want to have some kind of test set to weigh it against, so you know how good your model is when you distribute it. Let's go ahead and break this code down and look at it in pieces. So first we have our x and y. Where do x and y come from? Well, x is going to be our data, and y is going to be the answer or the target. You can look at it as source and target. In this case, we're using x and y to denote the data in and the data that we're actually trying to guess what the answer is going to be. And so to separate it, we can simply put in x equals the balance of the data dot values. The first brackets means that we're going to select all the lines in the database. So it's all the data. And the second one says we're only going to look at columns 1 through 5. Remember, we always start with 0. 0 is a yes or no, and that's whether the loan went default or not. So we want to start with 1. If we go back up here, that's the initial payment, and it goes all the way through the house number. Well, if we want to look at 1 through 5, we can do the same thing for y, which is the answers, and we're going to set that just equal to the 0 row. So it's just the 0 row, and then it's all rows going in there. So now we've divided this into two different data sets. One of them with the data going in, and one with the answers. Next, we need to split the data. And here you'll see that we have it split into 4 different parts. The first one is your X training, your X test, your Y train, your Y test. Simply put, we have X going in, where we're going to train it, and we have to know the answer to train it with. And then we have X test, where we're going to test that data. And we have to know in the end what the Y was supposed to be. And that's where this train test split comes in, that we loaded earlier in the modules. This does it all for us. And you can see they set the test size equal to 0.3, so it's roughly 30% will be used in the test. And then we use a random state, so it's completely random which rows it takes out of there. And then finally we get to actually build our decision tree. And they've called it here CLF_entropy. That's the actual decision tree, or decision tree classifier. And in here they've added a couple variables, which we'll explore in just a minute. And then finally, we need to fit the data to that. So we take our CLF entropy that we created, and we fit the X train, and since we know the answers for X train or the Y train, we go ahead and put those in. And let's go ahead and run this. And what most of these sklearn modules do is when you set up the variable, in this case when we set the CLF entropy equal to decision tree classifier, it automatically prints out what's in that decision tree. There's a lot of variables you can play with in here, and it's quite beyond the scope of this tutorial to go through all of these and how they work. But we're working on entropy, that's one of the options. We've added that it's completely a random state of 100, so 100%. And we have a max depth of 3. Now the max depth, if you remember above when we were doing the different graphs of animals, means it's only going to go down 3 layers before it stops. And then we have minimal samples of leaves as 5. So it's going to have at least 5 leaves at the end. So it'll have at least 3 splits, it'll have no more than 3 layers, and at least 5 end leaves with the final result at the bottom. Now that we've created our decision tree classifier, not only created it but trained it, let's go ahead and apply it and see what that looks like. So let's go ahead and make a prediction and see what that looks like. We're going to paste our predict code in here. And before we run it, let's just take a quick look at what's it's doing here. We have a variable yPredict that we're going to do. And we're going to use our variable CLF entropy that we created. And then you'll see .predict. And that's very common in the sklearn modules that their different tools have the predict when you're actually running a prediction. In this case, we're going to put our X test data in here. Now, if you delivered this for use, an actual commercial use, and distributed it, this would be the new loans you're putting in here to guess whether the person's going to be pay them back or not. In this case, though, we need to test out the data and just see how good our sample is, how good of our tree does at predicting the loan payments. And finally, since Anaconda Jupyter Notebook works as a command line for Python, we can simply put the yPredict in to print it. I could just as easily have put the print and put brackets around yPredict in to print it out. We'll go ahead and do that. It doesn't matter which way you do it. And you'll see right here that it runs a prediction. This is roughly 300 in here. Remember, it's 30% of 1,000, so you should have about 300 answers in here. And this tells you which each one of those lines of our test went in there, and this is what our y-predict came out. So let's move on to the next step, where we're going to take this data and try to figure out just how good a model we have. So here we go. Since sklearn does all the heavy lifting for you and all the math, we have a simple line of code to let us know what the accuracy is. And let's go ahead and go through that and see what that means and what that looks like. Let's go ahead and paste this in, and let me zoom in a little bit. There we go. So you have a nice full picture. And we'll see here we're just going to do a print accuracy is, and then we do the accuracy score. And this was something we imported earlier, if you remember at the very beginning. Let me just scroll up there real quick so you can see where that's coming from. That's coming from here, down here, from sklearn.metrics import accuracy score. And you could probably run a script, make your own script to do this very easily. How accurate is it? How many out of 300 do we get right? And so we put in our y-test, that's the one we ran the predict on, and then we put in our y-predict en, that's the answers we got, and we're just going to multiply that by 100, because this is just going to give us an answer as a decimal, and we want to see it as a percentage. And let's run that and see what it looks like. And if you see here, we got an accuracy of 93.66667. So when we look at the number of loans and we look at how good our model fit, we can tell people it has about a 93.6 fitting to it. So just a quick recap on that. We now have accuracy set up on here. And so we have created a model that uses the decision tree algorithm to predict whether a customer will repay the loan or not. The accuracy of the model is about 94.6%. The bank can now use this model to decide whether it should approve the loan request from a particular customer or not. And so this information is really powerful. We may not be able to, as individuals, understand all these numbers because they have thousands of numbers that come in. But you can see that this is a smart decision for the bank to use a tool like this to help them to predict how good their profit's going to be off of the loan balances and how many are going to default or not. So we've had a lot of fun learning about decision trees. So let's take a look at the key takeaways that we've covered today. What is machine learning? We covered up some different aspects of machine learning and what that is utilized in your everyday life and what you can use it for predicting, for describing, for guessing what the next outcome is, for storing information. We looked at the three main types of machine learning: supervised learning, unsupervised learning, and reinforced learning. We looked at problems in machine learning and what it solves: classification, regression, and clustering. Finally, we went through how does the decision tree work, where we looked at the hunter and he's trying to sort out the different animals and what kind of animals they are. And then we rolled up our sleeves and did our Python coding and actually applied it to a data set. Have you ever wondered how your mail provider implements spam filtering, or how online news channels perform news text classification, or how companies perform sentimental analysis of their audience on social media? All of this and more is done through a machine learning algorithm called Naive Bayes classifier. What is naive Bayes? Let's start with a basic introduction to the Bayes theorem, named after Thomas Bayes from the 1700s, who first coined this in the Western literature. Naive Bayes classifier works on the principle of conditional probability as given by the Bayes theorem. Before we move ahead, let us go through some of the simple concepts in the probability that we will be using. Let us consider the following example of tossing two coins. Here we have two quarters, and if we look at all the different possibilities of what they can come up as, we get that they could come up as head-heads, they could come up as head-tail, tail-head, and tail-tail. When doing the math on probability, we usually denote probability as a P, a capital P. So the probability of getting two heads equals 1/4. You can see on our data set we have two heads, and this occurs once out of the four possibilities. And then the probability of at least one tail occurs 3/4 of the time. You'll see on 3 of the coin tosses we have tails in them, and out of 4 that's 3/4. And then the probability of the second coin being head given the first coin is tail is 1/2, and the probability of getting two heads given the first coin is a head is 1/2. We'll demonstrate that in just a minute and show you how that math works. Now when we're doing it with two coins, it's easy to see, but when you have something more complex, you can see where these formulas really come in and work. So the Bayes theorem gives us the conditional probability of an event A given another event B has occurred. In this case, the first coin toss will be B, and the second coin toss A. This can be confusing because we've actually reversed the order of them and go from B to A instead of A to B. You'll see this a lot when you work in probabilities. The reason is we're looking for event A. We want to know what that is. So we're going to label that A since that's our focus. And then given another event B has occurred. In the Bayes theorem, as you can see on the left, the probability of A occurring given B has occurred equals the probability of B occurring given A has occurred times the probability of A over the probability of B. This simple formula can be moved around just like any algebra formula. And we could do the probability of A after a given B times probability of B equals the probability of B given A times probability of A. You can easily move that around and multiply it and divide it out. Let us apply Bayes' theorem to our example. Here we have our 2 quarters, and we'll notice that the first 2 probabilities of getting 2 heads and at least 1 tail we compute directly off the data. So you can easily see that we have one example, HH, out of 4, 1/4, and we have 3 with tails in them, giving us 3/4, or 3/4, 75%. The second condition, the second set, 3 and 4, we're going to explore a little bit more in detail. Now we stick to a simple example with 2 coins because you can easily understand the math. The probability of throwing a tail doesn't matter what comes before it, and the same with the heads. So it's still going to be 50% or 1/2. But when that probability gets more complicated, let's say you have a D6 dice or some other instance, then this formula really comes in handy. But let's stick to the simple example for now. In this sample space, let A be the event that the second coin is head and B be the event that the first coin is tails. Again, we reversed it because we want to know what the second event's going to be, so we're going to be focusing on A. And we write that out as the probability of A given B. And we know this from our formula that equals the probability of B given A times the probability of A over the probability of B. And when we plug that in, we plug in the probability of the first coin being tails given the second coin is heads, and the probability of the second coin being heads given the first coin being over the probability of the first coin being tails. When we plug that data in, and we have the probability of the first coin being tails given the second coin is heads times the probability of the second coin being heads over the probability of the first coin being tails. You can see it's a simple formula to calculate. We have 1/2 times 1/2 over 1/2, or 1/2 equals 0.5, or 1/4. So the Bayes theorem basically calculates the conditional probability of the occurrence of an event based on prior knowledge of conditions that might be related to the event. We will explore this in detail when we take up an example of online shopping further in this tutorial. Understanding naive Bayes and machine learning. Like with any of our other machine learning tools, it's important to understand where the naive Bayes fits in the hierarchy. So under the machine learning, we have supervised learning, and there is other things like unsupervised learning. There's also reward system. This falls under the supervised learning. And then under the supervised learning, there's classification. There's also regression, but we're going to be in the classification side. And then under classification is your naive Bayes. Let's go ahead and glance into where is naive Bayes used. Let's look at some of the use scenarios for it. As a classifier, we use it in face recognition. Is this Cindy or is it not Cindy or whoever? Or it might be used to identify parts of the face that they then feed into another part of the face recognition program. This is the eye, this is the nose, this is the mouth. Weather prediction, is it going to be rainy or sunny? Medical recognition, news prediction. It's also used in medical diagnosis. We might diagnose somebody as either as high risk or not as high risk for cancer or heart disease or other ailments. And news classification. When you look at the Google News and it says, well, is this political or is this world news? Or a lot of that's all done with the naive Bayes. Understanding naive Bayes classifier. Now, we already went through a basic understanding with the coins and the 2 heads and 2 tails and head tail, tail heads, etc. We're going to do just a quick review on that and remind you that the naive Bayes classifier is based on the Bayes theorem, which gives a conditional probability of event A given event B. And that's where the probability of A given B equals the probability of B given A times probability of A over probability of B. Remember, this is an algebraic function, so we can move these different entities around. We can multiply by the probability of B, so it goes to the left-hand side, and then we could divide by the probability of A given B, and just as easily come up with a new formula for the probability of B. To me, staring at these algebraic functions kind of gives me a slight headache. It's a lot better to see if we can actually understand how this data fits together in a table. And let's go ahead and start applying it to some actual data so you can see what that looks like. So we're going to start with the shopping demo. problem statement. And remember, we're going to solve this first in table form so you can see what the math looks like, and then we're going to solve it in Python. And in here we want to predict whether the person will purchase a product. Are they going to buy or don't buy? Very important if you're running a business, you want to know how to maximize your profits, or at least maximize the purchase of the people coming into your store. And we're going to look at a specific combination of different variables. In this case, we're going to look at the day, the discount, and the free delivery. And you can see here under the day, we want to know whether it's on the weekday. You know, somebody's working, they come in after work, or maybe they don't work. Weekend, you can see the bright colors coming down there, celebrating not being in work, or holiday. And did we offer a discount that day? Yes or no? Did we offer free delivery that day? Yes or no? And from this, we want to know whether the person's going to buy based on these traits so we can maximize them and find out the best system for getting somebody to come in and purchase our goods and products from our store. Now, having a nice visual is great, but we do need to dig into the data. So let's go ahead and take a look at the data set. We have a small sample data set of 30 rows. We're showing you the first 15 of those rows for this demo. Now, the actual data file you can request. Just type in below under the comments on the YouTube video, and we'll send you some more information and send you that file. As you can see here, the file is very simple, columns and rows. We have the day, the discount, the free delivery, and did the person purchase or not. And then we have under the day whether it was a weekday, a holiday, was it the weekend. This is a pretty simple set of data, and long before computers, people used to look at this data and calculate this all by hand. So let's go ahead and walk through this and see what that looks like when we put that into tables. Also note, in today's world, we're not usually looking at 3 different variables in 30 rows. Nowadays, because we're able to collect data so much, we're usually looking at 27, 30 variables across hundreds of rows. The first thing we want to do is we're going to take this data and based on the data set containing our 3 inputs, day, discount, and free delivery, we're going to go ahead and populate that to frequency tables for each attribute. So we want to know if they had a discount, how many people buy and did not buy. Did they have a discount, yes or no? Do we have a free delivery, yes or no? On those days, how many people made a purchase and how many people didn't? And the same with the 3 days of the week. Was it a weekday, a weekend, a holiday? And did they buy, yes or no? As we dig in deeper to this table for our Bayes theorem, let the event buy be A. Now remember, when we looked at the coins, I said we really want to know what the outcome is. Did the person buy or not? And that's usually event A is what you're looking for. And the independent variables, discount, free delivery, and day, be B. So we'll call that probability of B. Now let us calculate the likelihood table for one of the variables. Let's start with day, which includes weekday, weekend, and holiday. And let us start by summing all of our rows. So we have the weekday row, and out of the weekdays there's 9 plus 2, so it's 11 weekdays. There's 8 weekend days and 11 holidays. Wow, that's a lot of holidays. And then we want to sum up the total number of days. So we're looking at a total of 30 days. Let's start pulling some information from our chart and see where that takes us. And when we fill in the chart on the right, you can see that 9 out of 24 purchases are made on the weekday, 7 out of 24 purchases on the weekend, and 8 out of 24 purchases on a holiday. And out of all the people who come in, 24 out of 30 purchase. You can also see how many people do not purchase. On the weekday, it's 2 out of 6 didn't purchase, and so on and so on. We can also look at the totals, and you'll see on the right we put together some of the formulas. The probability of making a purchase on the weekend comes out at 11 out of 30. So out of the 30 people who came into the store throughout the weekend, weekday, and holiday, 11 of those purchases were made on the weekday. And then you can also see the probability of them not making a purchase. And this is done for, doesn't matter which day of the week. So we call that probability of no buy. It would be 6 over 30 or 0.2. So there's a 20% chance that they're not going to make a purchase no matter what day of the week it is. And finally, we look at the probability of B if A. In this case, we're going to look at the probability of the weekday and not buying. 2 of the no buys were done out of the weekend out of the 6 people who did not make purchases. So when we look at that, probability of the weekday without a purchase is going to be 0.33 or 33%. Let's take a look at this at different probabilities, and based on this likelihood table, let's go ahead and calculate conditional probabilities as below. The first 3 we just did. The probability of making a purchase on the weekday is 11 out of 30, or roughly 36 or 37%, 0.367. The probability of not making a purchase at all, doesn't matter what day of the week, is roughly 0.2 or 20%. And the probability of a weekday no purchase is roughly 2 out of 6. So 2 out of 6 of our no purchases were made on the weekday. And then finally we take our P of AB, If you look, we've kept the symbols up there. We got P of probability of B, probability of A, probability of B if A. We should remember that the probability of A if B is equal to the first one times the probability of no buys over the probability of the weekday. So we could calculate it both off the table we created. We can also calculate this by the formula, and we get the 0.367, which equals, or 0.33 times 0.2 over 0.367, which equals 0.179, or roughly 17 to 18%. And that'd be the probability of no purchase done on the weekday. And this is important because we can look at this and say, as the probability of buying on the weekday is more than the probability of not buying on the weekday, we can conclude that customers will most likely buy the product on a weekday. Now, we've kept our chart simple and we're only looking at one aspect. So you should be able to look at the table and come up with the same information or the same conclusion. That should be kind of intuitive at this point. Next, we can take the same setup. We have the frequency tables of all three independent variables. Now we can construct the likelihood tables for all three of the variables we're working with. We can take our day like we did before. We have weekday, weekend, and holiday. We filled in this table. And then we can come in and also do that for the discount, yes or no. Did they buy, yes or no? And we fill in that full table. So now we have our probabilities for a discount and whether the discount leads to a purchase or not, and the probability for free delivery. Does that lead to a purchase or not? And this is where it starts getting really exciting. Let us use these three likelihood tables to calculate whether a customer will purchase a product on a specific combination of day, discount, and free delivery, or not purchase. Here, let us take a combination of these factors. Day equals holiday, discount equals yes, free delivery equals yes. Let's dig deeper into the math and actually see what this looks like. And we're going to start with looking for the probability of them not purchasing on the following combinations of days. We are actually looking for the probability of A equal no buy, no purchase. And our probability of B we're going to set equal to, is it a holiday? Did they get a discount? Yes. And was it a free delivery? Yes. Before we go further, let's look at the original equation. The probability of A if B equals the probability of B given the condition A and the probability times the probability of A over the probability of B occurring. Now this is basic algebra, so we can multiply this information together. So when you see the probability of A given B, in this case the condition is B, C, and D, or the three different variables we're looking at. And when you see the probability of B, that would be the conditions. We're actually going to multiply those three separate conditions out. Probability of, you'll see that in just a second in the formula, times the full probability of A over the full probability of B. So here we are back to this, and we're going to have let A equal no purchase, and we're looking for the probability of B on the condition A, where A sets for three different things. Remember that equals the probability of A given the condition B. And in this case, we just multiply those three different variables together. So we have the probability of the discount times the probability of free delivery times the probability is the day equal a holiday. Those are our three variables of the probability of A if B. And then that is going to be multiplied by the probability of them not making a purchase. And then we want to divide that by the total probabilities, and they're multiplied together. So we have the probability of a discount, the probability of a free delivery, and the probability of it being on a holiday. When we plug those numbers in, we see that 1 out of 6 were no purchase on a discounted day, 2 out of 6 were a no purchase on a free delivery day, and 3 out of 6 were a no purchase on a holiday. Those are our three probabilities of A if B multiplied out. And then that has to be multiplied by the probability of a no purchase. And remember, the probability of a no buy is across all the data. So that's where we get the 6 out of 30. We divide that out by the probability of each category over the total number. So we get the 20 out of 30 had a discount, 23 out of 30 had a yes for free delivery, and 11 out of 30 were on a holiday. We plug all those numbers in, we get 0.178. So in our probability math, we have a 0.178 if it's a no buy for a holiday, a discount, and a free delivery. Let's turn that around and see what that looks like if we have a purchase. I promise this is the last page of math before we dig into the Python script. So here we're calculating the probability of the purchase using the same math we did to find out if they didn't buy. Now we want to know if they did buy. And again, we're going to go by the day equals a holiday, discount equals yes, free delivery equals yes, and let A equal buy. Now right about now you might be asking, why are we doing both calculations? Why would we want to know the no buys and buys for the same data going in? Well, we're going to show you that in just a moment, but we have to have both of those pieces of information so that we can figure it out as a percentage as opposed to a probability equation. And we'll get to that normalization here in just a moment. Let's go ahead and walk through this calculation. And as you can see here, the probability of A on the condition of B being all three categories. Did we have a discount with a purchase? Did we have a free delivery with a purchase? And is a day equal to holiday? And when we plug this all into that formula and multiply it all out, we get our probability of a discount, probability of a free delivery, probability of the day being a holiday, times the overall probability of it being a purchase, divided by, again multiplying the three variables out, the full probability of there being a discount, the full probability of being a free delivery, and the full probability of there being a day equal holiday. And that's where we get this 19 over 24 times 21 over 24 times 8 over 24 times the P of A, 24 over 30, divided by the probability of the discount, the free delivery times the day, or 20 over 30, 23 over 30 times 11 over 30, and that gives us our 0.986. So, what are we going to do with these two pieces of data we just generated? Well, let's go ahead and go over them. We have a probability of purchase equals 0.986. We have a probability of no purchase equals 0.178. So, finally, we have a conditional probabilities of purchase on this day. Let us take that, we're going to normalize it, and we're going to take these probabilities and turn them into percentages. This is simply done by taking the sum of probabilities, which equals 0.986 plus 0.178, and that equals the 1.164. If we divide each probability by the sum, we get the percentage. And so the likelihood of a purchase is 84.71%, and the likelihood of no purchase is 15.29%, given these three different variables. So if it's on a holiday, if it's with a discount and has free delivery, then there's an 84.71% chance that the customer is going to come in and make a purchase. Hooray! They purchased our stuff. We're making money. If you're owning a shop, that's is the bottom line, is you want to make some money so that you can keep your shop open and have a living. Now, I promised you that we were going to be finishing up the math here with a few pages. So we're going to move on and we're going to do two steps. The first step is I want you to understand why you want to use the naive Bayes. What are the advantages of naive Bayes? And then once we understand those advantages, we'll just look at that briefly, then we're going to dive in and do some Python coding. Advantages of naive Bayes classifier. So let's take a look at the 6 advantages of the naive Bayes classifier, and we're going to walk around this lovely wheel. It looks like an origami folded paper. The first one is very simple and easy to implement. Certainly you could walk through the tables and do this by hand. You got to be a little careful because the notations can get confusing. You have all these different probabilities, and I certainly mess those up as I put them on, is it on the top or the bottom? You got to really pay close attention to that. When you put it into Python, it's really nice because you don't have to worry about any of that. You let the Python handle that, the Python module. But understanding it, you can put it on a table and you can easily see how it works, and it's a simple algebraic function. It needs less training data, so if you have smaller amounts of data, this is a great, powerful tool for that. Handles both continuous and discrete data. It's highly scalable with number of predictors and data points. So as you can see, you can just keep multiplying different probabilities in there, and you can cover not just 3 different variables or sets. You can now expand this to even more categories. Number 5, it's fast. It can be used in real-time predictions. This is so important. This is why it's used in a lot of our predictions on online shopping carts, referrals, spam filters, is because there's no time delay as it has to go through and figure out a neural network or one of the other many setups where you're doing classification. And certainly there's a lot of other tools out there in the machine learning that can handle these, but most of them are not as fast as the naive Bayes. And then finally, it's not sensitive to irrelevant features. So it picks up on your different probabilities, and if you're short on data on one probability, you can it automatically adjust for that. Those formulas are very automatic, And so you can still get a very solid predictability even if you're missing data or you have overlapping data for two completely different areas. We see that a lot in doing census and studying of people and habits, where they might have one study that covers one aspect and another one that overlaps, and because the two overlap, they can then predict the unknowns for the group that they haven't done the second study on, or vice versa. So it's very powerful in that it is not sensitive to the irrelevant features, and in fact you can use it to help predict features that aren't even in there. So now we're down to my favorite part. We're going to roll up our sleeves and do some actual programming. We're going to do the use case text classification. Now, I would challenge you to go back and send us a note on the notes below underneath the video and request the data for the shopping cart. So you can plug that into Python code and do that on your own time so you can walk through it, since we walk through all the information on it. But we're going to do a Python code doing text classification, very popular for doing the naive Bayes. So we're going to use our new tool to perform a text classification of news headlines and classify news into different topics for a news website. As you can see here, we have a nice image of the Google News, and then related on the right, subgroups. I'm not sure where they actually pulled the actual data we're going to use from. It's one of the standard sets. But certainly this can be used on any of our news headlines in classification. So let's see how it can be done using the naive Bayes classifier. Now we're at my favorite part. We're actually going to write some Python script. Roll up our sleeves. And we're going to start by doing our imports. These are very basic imports, including our news group. And we'll take a quick glance at the target names. Then we're going to go ahead and start training our data set and putting it together. We'll put together a nice graph, because it's always good to have a graph to show what's going on. And once we've trained it and we've shown you a graph of what's going on, then we're going to explore how to use it and see what that looks like. Now, I'm going to open up my favorite editor, inline editor for Python. You don't have to use this. You can use whatever your editor that you like, whatever interface IDE you want. This just happens to be the Anaconda Jupyter Notebook. And I'm going to paste that first piece of code in here so we can walk through it. Let's make it a little bigger on the screen so you have a nice view of what's going on. And we're using Python 3, in this case 3.5. So this would work in any of your 3x. If you have it set up correctly, it should also work in a lot of the 2x. You just have to make sure all of the versions of the modules match your Python version. And in here, you'll notice the first line is your percentage matplotlib library in line. Now, 3 of these lines of code are all about plotting the graph. This one lets the notebook know, since this is an inline setup, that we want the graphs to show up on this page. Without it in a notebook like this, which is an Explorer interface, it won't show up. Now, a lot of IDEs don't require that. A lot of them, like if I'm working on one of my other setups, it just has a pop-up and the graph pops up on there. So you have that setup also. But for this, we want the matplotlib library inline. And then we're going to import NumPy as NP. That's NumberPython, which has a lot of different formulas in it that we use for both of our sklearn module. And we also use it for any of the upper math functions in Python. And it's very common to see that as NP, NumPy as NP. The next 2 lines are all about our graphing. Remember I said 3 of these were about graphing? Well, we need our matplotlib.pyplot as PLT, and you'll see that PLT is a very common setup, as is the SNS, and just like the NP. And we're going to import Seaborn as SNS, and we're going to do the SNS.set. Now, Seaborn sits on top of PyPlot, and it just makes a really nice heat map. It's really good for heat maps. And if you're not familiar with heat maps, that just means we give it a color scale. The term comes from the brighter red it is, the hotter it is in some form of data, and you can set it to whatever you want. And we'll see that later on. So you'll see that those 3 lines of code here are just importing the graph function so we can graph it. And as a data scientist, you always want to graph your data and have some kind of visual. It's really hard just to shove numbers in front of people and they look at it and it doesn't mean anything. And then from the sklearn.datasets, we're going to import the fetch 20 news groups. Very common one for analyzing, tokenizing words and setting them up and exploring how the words work and how do you categorize different things when you're dealing with documents. And then we set our data equal to fetch 20 news groups. So our data variable will have the data in it. And we're going to go ahead and just print the target names, data.targetNames. And let's see what that looks like. And you'll see here we have alt atheism, comp graphics, comp OS, MS, Windows.miscellaneous. And it goes all the way down to talkpolitics.miscellaneous, talkreligion.miscellaneous. These are the categories they've already assigned to this news group. And it's called Fetch 20 because you'll see I believe there's 20 different topics in here, or 20 different categories as we scroll down. Now, we've gone through the 20 different categories, and we're going to go ahead and start defining all the categories and set up our data. So we're actually going to go ahead and get the data all set up and take a look at our data. And let's move this over to our Jupyter Notebook, and let's see what this code does. First, we're going to set our categories. Now, if you noticed up here, I could have just as easily set this equal to data.target_names, because it's the same thing. But we want to kind of spell it out for you so you can see the different categories. It kind of makes it more visual so you can see what your data is looking like in the background. Once we've created the categories, we're going to open up a train set. So this training set of data is going to go into Fetch 20 news groups, and it's a subset in there called train, and categories equals categories. So we're pulling out those categories that match. And then if you have a train set, you should also have the testing set. We have test equals Fetch 20 news groups, subset equals test, and categories equals categories. And let's go down one size so it all fits on my screen. There we go. And just so we can really see what's going on, let's see what happens when we print out one part of that data. So it creates train, and under train it creates train.data, and we're just going to look at data piece number 5. And let's go ahead and run that and see what that looks like. And you can see when I print train.data number 5 under train, it prints out one of the articles. This is article number 5. You can go through and read it on there. And we can also go in here and change this to test, which should look identical because it's splitting the data up into different groups, train and test. And we'll see test number 5 is a different article, but it's another article in here. And maybe you're curious and you want to see just how many articles are in here. We could do length of train.data. And if we run that, you'll see that the training data has 11,314 articles. So we're not going to go through all those articles. That's a lot of articles. But we can look at one of them just so you can see what kind of information is coming out of it and what we're looking at. And we'll just look at number 5 for today. And here we have it. Rewording the Second Amendment IDs, VTT, lines 58, in article, etc. And you can scroll all the way down and see all the different parts to there. Now, we've looked at it, and that's pretty complicated when you look at one of these articles to try to figure out how do you weight this. If you look down here, we have different words, and maybe the word from. Well, from is probably in all the articles, so it's not going to have a lot of meaning as far as trying to figure out whether this article fits one of the categories or not. So trying to figure out which category it fits in based on these words is where the challenge comes in. Now that we've viewed our data, we're going to dive in and do the actual predictions. This is the actual naive Bayes. And we're going to throw another model at you, or another module at you here in just a second. We can't go into too much detail, but it deals specifically working with words and text and what they call tokenizing those words. So let's take this code and let's skip on over to our Jupyter Notebook and walk through it. And here we are in our Jupyter Notebook. Let's paste that in there. And I can run this code right off the bat. It's not actually going to display anything yet, but it has a lot going on in here. So at the top, we had the print module from the earlier one. I didn't know why that was in there. So we're going to start by importing our necessary packages. And from the sklearn features extraction.txt, we're going to import tf-idf vectorizer. I told you we're going to throw a module at you. We can't go too much into the math behind this or how it works. You can look it up. The notation for the math is usually tf.idf. And that's just a way of weighing the words. And it weighs the words based on how many times they're used in a document, how many times or how many documents they're used in. And it's a well-used formula. It's been around for a while. It's a little confusing to put this in here, but let's let it know that it just goes in there and weights the different words in the document for us. That way we don't have to wait. And if you put a weight on it, if you remember I was talking about that up here earlier, if these are all emails, they probably all have the word from in them. From probably has a very low weight. It has very little value in telling you what this document's about. Same with words like in article, in articles, in, cost of, un, maybe cost might, or where words like criminal, weapons, destruction, these might have a heavier weight because they describe a little bit more what the article's doing. Well, how do you figure out all those weights in the different articles? That's what this module does. That's what the tf-idf vectorizer is going to do for us. And then we're going to import our sklearn.naive Bayes, and that's our multinomial NB. Multinomial naive Bayes. Pretty easy to understand that, where that comes from. And then finally we have the sklearn pipeline import make pipeline. Now, the make pipeline is just a cool piece of code because we're going to take the information we get from the TF-IDF vectorizer and we're going to pump that into the multinomial NB. So a pipeline is just a way of organizing how things flow. It's used commonly. You probably already guessed what it is if you've done any businesses. They talk about the sales pipeline. If you're on a work crew or a project manager, you have your pipeline of information that's going through, or your projects and what has to be done in what order. That's all this pipeline is. We're going to take the TF-ID vectorizer and then we're going to push that into the multinomial NB. Now, we've designated that as the variable model. We have our pipeline model. And we're going to take that model, and this is just so elegant. This is done in just a couple lines of code. Model.fit. And we're going to fit the data, and first the train data, and then the train target. Now, the train data has the different articles in it. You can see the one we were just looking at. And the train.target is what category they already categorized that particular article as. And what's happening here is the train data is going into the TF-ID vectorizer. So when you have one of these articles, it goes in there, it weights all the words in there. So there's thousands of words with different weights on them. I remember once running a model on this and I literally had 2.4 million tokens go into this. So when you're dealing like large document bases, you can have a huge number of different words. It then takes those words, gives them a weight, and then based on that weight, based on the words and the weights, and then puts that into the multinomial NB. And once we go into our naive Bayes, we want to put the train target in there. So the train data that's been mapped to the TF-ID vectorizer is now going through the multinomial NB, and then we're telling it, well, these are the answers. These are the answers to the different documents. So this document that has all these words with these different weights from the first part is going to be whatever category it comes out of. Maybe it's the talk show or the article on religion, miscellaneous. Once we fit that model, we can then take labels and we're going to set that equal to model.predict. Most of the sklearn use the term .predict to let us know that we've now trained the model and now we want to get some answers. And we're going to put our test data in there because our test data is the stuff we held off to the side. We didn't train it on there and we don't know what's going to come up out of it, and we just want to find out how good our labels are. Do they match what they should be? Now, I've already run this through. There's no actual output to it to show. This is just setting it all up. This is just training our model, creating the labels so we can see how good it is, and then we move on to the next step to find out what happened. To do this, we're going to go ahead and create a confusion matrix and a heat map. So the confusion matrix, which is confusing just by its very name, is basically going to ask how confused is our answer. Did it get it correct, or did it miss some things in there or have some missed labels? And then we're going to put that on a heat map so we'll have some nice colors to look at to see how that plots out. Let's go ahead and take this code and see how that, take a walk through it and see what that looks like. So back to our Jupyter Notebook, I'm going to put the code in there, and let's go ahead and run that code. Take it just a moment. And remember, we had the inline, that way my graph shows up on the inline here. And let's walk through the code and then we'll look at this and see what that means. So, make it a little bit bigger. There we go. No reason not to use the whole screen. Too big. So we have here, from sklearn metrics, import confusion matrix. And that's just going to generate a set of data that says the prediction was such, the actual truth was either agreed with it or is something different. And it's going to add up those numbers so we can take a look and just see how well it worked. And we're going to set a variable mat equal to confusion matrix. And we have our test target, our test data that was not part of the training. Very important in data science, we always keep our test data separate. Otherwise, it's not a valid model if we can't properly test it with new data. And this is the labels we created from that test data. These are the ones that we predict it's going to be. So we go in and we create our SN heat map. The SNS is our seaborne, which sits on top of the pie plot. So when we create a SNS.heatmap, we take our confusion matrix, and it's going to be mat.t. And do we have other variables that go into the SNS.heatmap? We're not going to go into detail what all the variables mean. The annotation equals true. That's what tells it to put the numbers here. So you have the 166, the 1, the 0001. Format D and C bar equals false have to do with the format. If If you take those out, you'll see that some things disappear. And then the X tick labels and the Y tick labels, those are our target names. And you can see right here, that's the alt atheism, comp graphics, comp OS, MS, Windows, miscellaneous. And then finally, we have our plt.x label. Remember, the SNS or the Seaborn sits on top of our matplot library, our PLT. And so we want to just tell it x label equals a true is true. The labels are true, and then the y label is prediction label. So when we say a true, this is what it actually is, and the prediction is what we predicted. And let's look at this graph, because that's probably a little confusing the way I rattled through it. And what I'm going to do is I'm going to go ahead and flip back to the slides, because they have a black background they put in there that helps it shine a little bit better so you can see the graph a little bit easier. So in reading this graph, what we want to look at is how the color scheme has come out. And you'll see a line right down the middle, diagonally, from upper left to bottom right. What that is if you look at the labels, we have our predicted label on the left and our true label on the right. Those are the numbers where the prediction and the true come together. And this is what we want to see, is we want to see those lit up. That's what that heat map does, is you can see that it did a good job of finding those data. And you'll notice that there's a couple of red spots on there where it missed. You know, it's a little confused when we talk about talk religion miscellaneous versus talk politics miscellaneous, social religion Christian versus alt atheism. It mislabeled some of those. And those are very similar topics, so you could understand why it might mislabel them. But overall, it did a pretty good job. If we're going to create these models, we want to go ahead and be able to use them. So let's see what that looks like. To do this, let's go ahead and create a definition, a function to run. And we're going to call this function, let me just expand that just a notch here. There we go. I like mine in big letters. Predict categories. We want to predict the category. We're going to send it S, a string. And then we're sending it train equals train. We have our training model. And then we had our pipeline, model equals model. This way we don't have to resend these variables each time. The definition knows that because I said train equals train, and I put the equal for model. And then we're going to set the prediction equal to the model.predictS. So it's going to send whatever string we send to it. It's going to push that string through the pipeline, the model pipeline. It's going to go through and tokenize it and put it through the TF, IDF, convert that into numbers and weights for all the different documents and words, and then it'll put that through our naive Bayes. And from it, we'll go ahead and get our prediction. We're going to predict what value it is. And so we're going to return train.targetNamesPredict of 0. And remember that the train.targetNames, that's just categories. I could have just as easily put categories in there .predict of 0. So we're taking the prediction, which is a number, and we're converting it to an actual category. We're converting it from, I don't know what the actual numbers are, but let's say 0 equals alt atheism. So we're going to convert that 0 to the word, or 1, maybe it equals comp graphics. So we're going to convert number 1 into comp graphics. That's all that is. And then we got to go ahead and then we need to go ahead and run this. So I load that up. And then once I run that, we can start doing some predictions. I'm going to go ahead and type in predict category. And let's just do predict category Jesus Christ. And it comes back and says it's social, religion, Christian. That's pretty good. Now, note I didn't put print on this. One of the nice things about the Jupyter Notebook Editor and a lot of inline editors is if you just put the name of the variable out as returning the variable train.target_names, it'll automatically print that for you. In your own IDE, you might have to put in print. Let's see where else we can take this. And maybe you're a space science buff. So how about sending load to International Space Station? And if we run that, we get science space. Or maybe you're a automobile buff. And let's do, they were going to tell me Audi is better than BMW, but I'm going to do BMW is better than an Audi. So maybe you're a car buff. And we run that, and you'll see it says recreational. I'm assuming that's what REC stands for. Autos. So I did a pretty good job labeling that one. How about if we have something like a caption running through there? President of India. And if we run that, it comes up and says talk, politics, miscellaneous. So when we take our definition or our function and we run all these things through, Kudos, we made it. We were able to correctly classify texts into different groups based on which category they belong to using the naive Bayes classifier. Now, we did throw in the pipeline, the TF-IDF vectorizer, we threw in the graphs. Those are all things that you don't necessarily have to know to understand the naive Bayes setup or classifier, but they're important to know. One of the main uses for the naive Bayes is with the TF-IDF tokenizer or vectorizer, where it tokenizes the word and adds labels. And we use the pipeline because you need to push all that data through, and it makes it really easy and fast. You don't have to know those to understand naive Bayes, but they certainly help for understanding the industry and data science. And we can see our categorizer, our naive Bayes classifier. We were able to predict the category religion, space, motorcycles, autos, politics, and properly classify all these different things we pushed into our prediction in our trained model. Let's go ahead and wrap it up. And let's just go through what we covered. We gave you an introduction to naive Bayes and how it's used to perform basic classification as a classifier. We went through the basic formula, the probability of A given B and the probability of B given A, the basics of the naive Bayes. We touched a little bit on some of the different uses for the naive Bayes. We also went over the advantages of it and where it really shines, especially when we talk about real-time processing. Naive Bayes is very fast. We talked about the shopping demo. Remember that if you want to try that on your own, send a note down below. Let us know and we'll get you that data set. And we also went through the Python, my favorite part, the text classification. So we learned all kinds of things in there and walking through a real life scenario where you'd use the naive Bayes at. By now, we all know machine learning models make predictions by learning from the past data available. So we have our input values. Our machine learning model builds on those inputs of what we already know, and then we use that to create a predicted output. Is that a dog? Little kid looking over there and watching the black cat cross their path. No, dear, you can differentiate between a cat and a dog based on their characteristics. Cats. Cats have sharp claws, uses to climb, smaller length of ears, meows and purrs, doesn't love to play around. Dogs have dull claws, bigger length of ears, barks, loves to run around. You usually don't see a cat running around people, although I do have a cat that does that, where dogs do. And we can look at these, we can say, we can evaluate the sharpness of the claws, how sharp are their claws, and we can evaluate the length of the ears, and we can usually sort out cats from dogs based on even those two characteristics. Now tell me if it is a cat or a dog. An odd question. Usually little kids know cats and dogs by now, unless they live in a place where there's not many cats or dogs. So if we look at the sharpness of the claws, the length of the ears, and we can see that the cat has smaller ears and sharper claws than the other animals. Its features are more like cats. It must be a cat. Sharp claws, length of ears, and it goes in the cat group. Because KNN is based on feature similarity, we can do classification using KNN classifier. So we have our input value, the picture of the black cat. It goes into our trained model, and it predicts that this is a cat coming out. So what is KNN? What is the KNN algorithm? K nearest neighbors is what that stands for. It's one of the simplest supervised machine learning algorithms, mostly used for classification. So we want to know, is this a dog or is not a dog? Is it a cat or not a cat? It classifies a data point based on how its neighbors are classified. KNN stores all available cases and classifies new cases based on a similarity measure. And here we've gone from cats and dogs right into wine, another favorite of mine. KNN stores all available cases and classifies new cases based on a similarity measure. And here you see we have a measurement of sulfur dioxide versus the chloride level, and then the different wines they've tested and where they fall on that graph based on how much sulfur dioxide and how much chloride. K in KNN is a perimeter that refers to the number of nearest neighbors to include in the majority of the voting process. And so if we add a new glass of wine there, red or white, we want to know what the neighbors are. In this case, we're going to put K equals 5. We'll talk about K in just a minute. A data point is classified by the majority of votes from its 5 nearest neighbors. Here, the unknown point would be classified as red since 4 out of 5 neighbors are red. So how do we choose K? How do we know K equals 5? I mean, that was the value we put in there, so we're going to talk about it. How do we choose the factor K? KNN algorithm is based on feature similarity. Choosing the right value of K is a process called parameter tuning and is important for better accuracy. So at k equals 3, we can classify, we have a question mark in the middle, as either as a square or not. Is it a square, or is it, in this case, a triangle? And so if we set k equals to 3, we're going to look at the 3 nearest neighbors. We're going to say this is a square. And if we put k equals to 7, we classify as a triangle, depending on what the other data is around it. And you can see as the k changes, depending on where that point is, that drastically changes your answer. And we jump here where we go, how do we choose the factor of k? You'll find this in all machine learning. Choosing these factors, that's the face you get. It's like, oh my gosh, did I choose the right k? Did I set it right, my values in whatever machine learning tool you're looking at, so that you don't have a huge bias in one direction or the other. And in terms of KNN, the number of k, if you choose it too low, the bias is based on, it's just too noisy. It's right next to a couple things, and it's going to pick those things, and you might get a skewed answer. And if your k is too big, then it's going to take forever to process. So you're going to run into processing issues and resource issues. So what we do, the most common use, and there's other options for choosing k, is to use the square root of n. So n is a total number of values you have, and you take the square root of it. In most cases, you also, if it's an even number, so if you're using, like in this case, squares and triangles, if it's even, you want to make your k value odd. That helps it select better. So in other words, you're not going to have a balance between two different factors that are equal. So usually you take the square root of n, and if it's even, you add 1 to it or subtract 1 from it, and that's where you get the k value from. That is the most common use, and it's pretty solid. It works very well. When do we use KNN? We can use KNN when data is labeled. So you need a label on it. We know we have a group of pictures with dogs, dogs, cats, cats. Data is noise free. And so you can see here, when we have a class and we have like underweight, 140, 23, Hello Kitty, normal, that's pretty confusing. We have a high variety of data coming in, so it's very noisy, and that would cause an issue. Data set is small, so we're usually working with smaller data sets where, I mean, you might get into a gig of data if it's really clean, doesn't have a lot of noise. Because KNN is a lazy learner, i.e. it doesn't learn a discriminative function from the training set. So it's very lazy, so if you have very complicated data and you have a large amount of it, you're not going to use the KNN. But it's really great to get a place to start. Even with large data, you can sort out a small sample and get an idea of what that looks like using the KNN. And also just using for smaller data sets, KNN works really good. How does the KNN algorithm work? Consider a data set having two variables, height in centimeters and weight in kilograms. And each point is classified as normal or underweight. So we can see right here we have two variables, true, false. They're either normal or they're not. They're underweight. On the basis of the given data, we have to classify the below set as normal or underweight using KNN. So if we have new data coming in that says 57 kilograms and 177 centimeters, is that going to be normal or underweight? To find the nearest neighbors, we'll calculate the Euclidean distance. According to the Euclidean distance formula, the distance between 2 points in the plane with the coordinates x, y, and ab is given by distance d equals the square root of x minus a squared plus y minus b squared. And you can remember that from the two edges of a triangle. We're computing the third edge since we know the x side and the y side. Let's calculate it to understand clearly. So we have our unknown point, and we placed it there in red, and we have our other points where the data is scattered around. The distance d1 is the square root of 170 minus 167 squared plus 57 minus 51 squared, which is about 6.7. And distance 2 is about 13. And distance 3 is about 13.4. Similarly, we will calculate the Euclidean distance of unknown data point from all the points in the data set. And because we're dealing with small amount of data, that's not that hard to do, and it's actually pretty quick for a computer. And it's not a really complicated math, so you can just see how close is the data based on the Euclidean distance. Hence, we have calculated the Euclidean distance of unknown data point from all the points as shown, where x1 and y1 equal 57 and 170, whose class we have to classify. So now we're looking at that, we're saying, well, here's the Euclidean distance. Who's going to be their closest neighbors? Now let's calculate the nearest neighbor at k equals 3. And we can see the three closest neighbors puts them at normal. And that's pretty self-evident. When you look at this graph, it's pretty easy to say, okay, we're just voting. Normal, 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 3 votes for normal. This is going to be a normal weight. So majority of neighbors are pointing towards normal. Hence, as per KNN algorithm, the class of 57,170 should be normal. So a recap of KNN. Positive integer k is specified along with a new sample. We select the k entries in our database which are closest to the new sample. We find the most common classification of these entries. This is the classification we give to the new sample. So as you can see, it's pretty straightforward. We're just looking for the closest things that match what we got. So let's take a look and see what that looks like in a use case in Python. So let's dive into the predict diabetes use case. So use case, predict diabetes. The objective, predict whether a person will be diagnosed with diabetes or not. We have a data set of 768 people who were or were not diagnosed with diabetes. And let's go ahead and open that file and just take a look at that data. And this is in a simple spreadsheet format. The data itself is comma separated, very common set of data, and it's also a very common way to get the data. And you can see here we have columns A through I. That's what 1, 2, 3, 4, 5, 6, 7, 8. 8 columns with a particular attribute, and then the 9th column, which is the outcome, is whether they have diabetes. As a data scientist, the first thing you should be looking at is insulin. Well, you know if someone has insulin, they have diabetes because that's why they're taking it. And that could cause issue in some of the machine learning packages, but for a very basic setup, this works fine for doing the KNN. And the next thing you notice is it didn't take very much to open it up. I can scroll down to the bottom of the data. There's 768. It's pretty much a small data set. You know, at 769, I can easily fit this into my RAM on my computer. I can look at it, I can manipulate it, and it's not going to really tax just a regular desktop computer. You don't even need an enterprise version to run a lot of this. So let's start with importing all the tools we need. And before that, of course, we need to discuss what IDE I'm using. Certainly you can use any particular editor for Python, but I like to use for doing very basic visual stuff the Anaconda, which is great for doing demos, with the Jupyter Notebook. And just a quick view of the Anaconda Navigator, which is the new release out there, which is really nice. You can see under Home, I can choose my application. We're going to be using Python 3.6. I have a couple different versions on this particular machine. If I go under Environments, I can create a unique environment for each one, which is nice. And there's even a little button there where I can install different packages. So if I click on that button and open the terminal, I can then use a simple pip install to install different packages I'm working with. Let's go ahead and go back under Home, and we're going to launch our notebook. And I've already, kind of like the old cooking shows, I've already prepared a lot of my stuff, so we don't have to wait for it to launch because it takes a few minutes for it to open up a browser window. In this case, it's going to open up Chrome because that's my default that I use. And since the script is pre-done, you'll see I have a number of windows open up at the top, the one we're working in. And since we're working on the KNN predict whether a person will have diabetes or not, let's go ahead and put that title in there. And I'm also going to go up here and click on Cell. Actually, we want to go ahead and first insert a cell below, and then I'm going to go back up to the top cell, and I'm going to change the cell type to Markdown. That means this is not going to run as Python. It's a Markdown language. So if I run this first one, it comes up in nice big letters, which is kind of nice. Remind us what we're working on. And by now, you should be familiar with doing all of our imports. We're going to import the pandas as PD, import NumPy as NP. Pandas is the pandas data frame, and NumPy is a number array. Very powerful tools to use in here. So we have our imports. So we've brought in our pandas, our NumPy, our two general Python tools. And then you can see over here we have our train test split. By now you should be familiar with splitting the data. We want to split part of it for training our thing and then training our particular model. And then we want to go ahead and test the remaining data to see how good it is. Pre-processing, a standard scalar preprocessor, so we don't have a bias of really large numbers. Remember in the data we had like number of pregnancies isn't going to get very large, where the amount of insulin they take can get up to 256. So 256 versus 6. That will skew results, so we want to go ahead and change that so that they're all uniform between -1 and 1. And then the actual tool. This is the K-neighbors classifier we're going to use. And finally, the last three are 3 tools to test, all about testing our model. How good is it? We just put down test on there. And we have our confusion matrix, our F1 score, and our accuracy. So we have our 2 general Python modules we're importing, and then we have our 6 modules specific from the sklearn setup. And then we do need to go ahead and run this, so that these are actually imported. There we go. And then move on to the next step. And so in this set, we're going to go ahead and load the database. We're going to use pandas. Remember, pandas is PD. And we'll take a look at the data in Python. We looked at it in a simple spreadsheet, but usually I like to also pull it up so that we can see what we're doing. So here's our data set equals pd.readcsv. That's a pandas command. And the diabetes folder I just put in the same folder where my IPython script is. If you put in a different folder, you'd need the full length on there. We can also do a quick length of the data set. That is a simple Python command, len for length. We might even, let's go ahead and print that. We'll go print. And if you do it on its own line, length.dataset in the Jupyter Notebook, it'll automatically print it. But when you're in most of your different setups, you want to do the print in front of there. And then we want to take a look at the actual data set. And since we're in pandas, we can simply do dataset head. And again, let's go ahead and add the print in there. If you put a bunch of these in a row, the dataset 1 head, dataset 2 head, it only prints out the last one. So I usually always like to keep the print statement in there. But because most projects only use one data frame, pandas data frame, doing it this way doesn't really matter. The other way works just fine. And you can see when we hit the run button, we have the 768 lines, which we knew, and we have our pregnancies. It's automatically given a label on the left. Remember, the head only shows the first 5 lines. So we have 0 through 4. And just a quick look at the data, you can see it matches what we looked at before. We have pregnancy, glucose, blood pressure, all the way to age, and then the outcome on the end. And we're going to do a couple things in this next step. We're going to create a list of columns where we can't have 0. There's no such thing as 0 skin thickness or 0 blood pressure, 0 glucose. Any of those you'd be dead. So not a really good factor if they have a 0 in there because they didn't have the data. And we'll take a look at that because we're going to start replacing that information with a couple of different things. And let's see what that looks like. So first we create a nice list. As you can see, we have the values we talked about: glucose, blood pressure, skin thickness. And this is a nice way when you're working with columns, is to list the columns you need to do some kind of transformation on. Very common thing to do. And then for this particular setup, we certainly could use there's some Panda tools that will do a lot of this, where we can replace the NA. But we're going to go ahead and do it as a dataset column equals dataset column.replace. This is still pandas. You can do a direct. There's also one that you look for your NaN. A lot of different options in here. But the NaN, NumPy NaN is what that stands for, is none, it doesn't exist. So the first thing we're doing here is we're replacing the 0 with a NumPy none. There's no data there. That's what that says. That's what this is saying right here. So put the 0 in, and we're going to replace zeros with no data. So if it's a 0, that means the person's, well, hopefully not dead. Hopefully they just didn't get the data. The next thing we want to do is we're going to create the mean, which is the integer from the data set from the column dot mean, where we skip NAs. We can do that. That is a pandas command there, the skip NA. So we're going to figure out the mean of that data set. And then we're going to take that data set column and we're going to replace all the NP-NaN with the means. Why did we do that? And we could have actually just taken this step and gone right down here and just replaced 0 and skip anything where, except you could actually, there's a way to skip zeros and then just replace all the zeros. But in this case, we want to go ahead and do it this way. So you can see that we're switching this to a non-existent value. Then we're going to create the mean. Well, this is the average person. So if we don't know what it is, if they did not get the data and the data is missing, one of the tricks is you replace it with the average. What is the most common data for that? This way, you can still use the rest of those values to do your computation, and it kind of just brings that particular value, or those missing values, out of the equation. Let's go ahead and take this, and we'll go ahead and run it. Doesn't actually do anything, so we're still preparing our data. If you wanted to see what that looks like, we don't have anything in the first few lines, so it's not going to show up, but we certainly could look at a row. Let's do that. Let's go into our data set. Let's print a data set, and let's pick, in this case, let's just do glucose. And if I run this, this is going to print all the different glucose levels going down, and we thankfully don't see anything in here that looks like missing data, at least on the ones it shows. You can see it skipped a bunch in the middle, because that's what it does. If you have too many lines in Jupyter Notebook, it'll skip a few and go on to the next in a data set. Let me go ahead and remove this, and we'll just zero out that. And of course, before we do any processing, before proceeding any further, we need to split the data set into our train and testing data. That way we have something to train it with and something to test it on. And you're going to notice we did a little something here with the pandas database code. There we go, my drawing tool. We've added in this right here. off the data set. And what this says is that the first one in pandas, this is from the PD pandas, it's going to say within the data set we want to look at the iLocation, and it is all rows. That's what that says. So we're going to keep all the rows, but we're only looking at column 0 to 8. Remember, column 9, here it is right up here, we printed it in here, is outcome. Well, that's not part of the training data, that's part of the answer. Yes, column 9, but it's listed as 8, number 8. So 0 to 8 is 9 columns. So 8 is the value. And when you see it in here, 0, this is actually 0 to 7. It doesn't include the last one. And then we go down here to Y, which is our answer, and we want just the last one, just column 8. And you can do it this way with this particular notation. And then if you remember, we imported the train test split. That's part of the sklearn right there. And we simply put in our X and our Y. We're going to do random state equals 0. You don't have to necessarily seed it. That's a seed number. I think the default is 1 when you seed it. I'd have to look that up. And then the test size. Test size is 0.2. That simply means we're going to take 20% of the data and put it aside so that we can test it later. That's all that is. And again, we're going to run it. Not very exciting. So far, we haven't had any printout other than to look at the data. But that is a lot of this, is prepping this data. Once you prep it, the actual lines of code are quick and easy. And we're almost there with the actual running of our KNN. We need to go ahead and scale the data. If you remember correctly, we're fitting the data in a standard scaler, which means instead of the data being from 5 to 303 in one column, and the next column is 1 to 6, we're going to set that all so that all the data is between -1 and 1. That's what that standard scaler does. Keeps it standardized. And we only want to fit the scaler with the training set, but we want to make sure the testing set is, the X test going in is also transformed, so it's processing it the same. So here we go with our standard scaler. We're going to call it sc_x for the scaler, and we're going to import the standard scaler into this variable, and then our X train equals sc_x dot fit transform. So we're creating the scaler on the X train variable, and then our X test, we're also going to transform it. So we've trained and transformed the X train, and then the X test isn't part of that training. It isn't part of training the transformer. It just gets transformed. That's all it does. And again, we're going to go ahead and run this. And if you look at this, we've now gone through these steps, all 3 of them. We've taken care of replacing our zeros for key columns that shouldn't be 0, and we replaced that with the means of those columns. That way that they fit right in with our data models. We've come down here and we split the data. So now we have our test data and our training data. And then we've taken and we've scaled the data. So all of our data going in. Now, no, we don't train the Y part, the Y train and Y test. That never has to be trained. It's only the data going in. That's what we want to train in there. Then define the model using K-neighbors classifier and fit the train data in the model. So we do all that data prep. And you can see down here we're only going to have a couple lines of code where we're actually building our model and training it. That's one of the cool things about Python and how far we've come. It's such an exciting time to be in machine learning because there's so many automated tools. Let's see, before we do this, let's do a quick length of, and let's do Y. Let's just do length of Y. And we get 768. And if we import math, we do math dot square root. Let's do Y train. There we go. It's actually supposed to be X train. Before we do this, let's go ahead and do import math and do math square root length of Y test. And when I run that, we get 12.409. I wanted to show you where this number comes from we're about to use. 12 is an even number, so if you're ever voting on things, remember the neighbors all vote, don't want to have an even number of neighbors voting, so we want to do something odd. And let's just take one away and we'll make it 11. Let me delete this out of here. That's one of the reasons I love Jupyter Notebook, because you can flip around and do all kinds of things on the fly. So we'll go ahead and put in our classifier. We're creating our classifier now, and it's going to be the K-neighbors classifier. N neighbors equal 11. Remember we did 12 minus 1 for 11, so we have an odd number of neighbors. P equals 2, because we're looking for are they diabetic or not, and we're using the Euclidean metric. There are other means of measuring the distance. You could do like square means value. There's all kinds of measure this, but the Euclidean's the most common one, and it works quite well. It's important to evaluate the model. Let's use the confusion matrix to do that. And we're going to use the confusion matrix, wonderful tool, and then we'll jump into the F1 score. And finally, accuracy score, which is probably the most commonly used quoted number when you go into a meeting or something like that. So let's go ahead and paste that in there, and we'll set the CM equal to confusion matrix, Y test, Y predict. So those are the two values we're going to put in there. And let me go ahead and run that and print it out. And the way you interpret this is you have the Y predicted, which would be your title up here. We could do, let's just do PRED. Predicted across the top, and actual going down. Actual. It's always hard to write in here. Actual. That means that this column here down the middle, that's the important column. And it means that our prediction said 94, and prediction and the actual agreed on 94 and 32. This number here, the 13 and the 15, those are what was wrong. So you could have like three different, if you're looking at this across three different variables instead of just two, you'd end up with the third row down here and the column going down the middle. So in the first case we have the and I believe the 0 is the 94 people who don't have diabetes. The prediction said that 13 of those people did have diabetes and were at high risk. And the 32 that had diabetes, it had correct. But our prediction said another 15. Out of that 15, it classified as incorrect. So you can see where that classification comes in and how that works on the confusion matrix. And then we're going to go ahead and print the F1 score. Let me just run that. And you see we get a 0.69 in our F1 score. The F1 takes into account both sides of the balance of false positives. Where if we go ahead and just do the accuracy account, and that's what most people think of, is it looks at just how many we got right out of how many we got wrong. So a lot of people, when you're a data scientist and you're talking to other data scientists, they're going to ask you what the F1 score or the F score is. If you're talking to the general public or the decision makers in the business, they're going to ask what the accuracy is. And the accuracy is always better than the F1 score. But the F1 score is more telling. It lets us know that there's more false positives than we would like on here. But 82%, not too bad for a quick flash look at people's different statistics and running an sklearn and running the KNN, the K nearest neighbor on it. So we have created a model using KNN, which can predict whether a person will have diabetes or not, or at the very least whether they should go get a checkup and have their glucose checked regularly or not. The print accuracy score, we got the 0.818, was pretty close to what we got, and we can pretty much round that off and just say we have an accuracy of 80%. Tells us it is a pretty fair fit in the model. To pull that all together, it's always a lot of fun, make sure we cover everything we went over today. We covered why we need a KNN, looking at cats and dogs. Great if you have a cat door and you want to figure out whether there's a cat or dog coming in. Don't let the dog in or out. Using Euclidean distance, the simple distance calculated by the two sides of the triangle or the square root of the two sides squared. Choosing the value of K. We discussed that a little bit, at least one of the main choices that people use for choosing K, and how KNN works, and then finally we did a full KNN classifier for diabetes prediction.
So what is K-means clustering? K-means clustering is an unsupervised learning algorithm. In this case, you don't have labeled data, unlike in supervised learning. So you have a set of data and you want to group them. And as the name suggests, you want to put them into clusters, which means objects that are similar in nature, similar in characteristics, need to be put together. So that's what K-means clustering is all about. The term K is basically a number. So we need to tell the system how many clusters we need to perform. So if K is equal to 2, there will be 2 clusters. If K is equal to 3, it's 3 clusters, and so on and so forth. That's what the K stands for. And of course, there is a way of finding out what is the best or optimum value of K for a given data. We will look at that. So that is K-means clustering. So let's take an example. K-means clustering is used in many scenarios, but let's take an example of cricket, the game of cricket. Let's say you received data of a lot of players from maybe all over the country or all over the world, and this data has information about the runs scored by the people or by the player and the wickets taken by the player. And based on this information, we need to cluster this data into 2 clusters, batsmen and bowlers. So this is an interesting example. Let's see how we can perform this. So we have the data which consists of primarily two characteristics, which is the runs and the wickets. So the bowlers basically take wickets and the batsmen score runs. There will be, of course, a few bowlers who can score some runs, and similarly there will be some batsmen who would have taken a few wickets. But with this information, we want to cluster those players into batsmen and bowlers. So how does this work? Let's say this is how the data is. So there is information on the y-axis about the runs scored, and on the x-axis about the wickets taken by the players. So if we do a quick plot, this is how it would look. And when we do the clustering, we need to have the clusters like shown in the third diagram out here. So we need to have a cluster which consists of people who have scored high runs, which is basically the batsmen, and then we need a cluster with people who have taken a lot of wickets, which is typically the bowlers. There may be a certain amount of overlap, but we will not talk about it right now. So with k-means clustering, we will have here, that means k is equal to 2, and we will have two clusters, which is batsmen and bowlers. So how does this work? The way it works is, the first step in k-means clustering is the allocation of two centroids randomly. So 2 points are assigned as so-called centroids. So in this case, we want two clusters, which means k is equal to 2. So 2 points have been randomly assigned as centroids. Keep in mind, these points can be anywhere. They are random points. They are not really the centroids. Centroid means it's a central point of a given data set, but in this case, when it starts off, it's not really the centroid. Okay, so these points, though in our presentation here we have shown them 1 point closer to these data points and another closer to these data points, they can be assigned randomly anywhere. Okay, so that's the first step. The next step is to determine the distance of each of the data points from each of the randomly assigned centroids. So for example, we take this point and find the distance from this centroid and the distance from this centroid. This point is taken and the distance is found from this centroid and this centroid, and so on and so forth. So for every point, the distance is measured from both the centroids, and then whichever distance is less, that point is assigned to that centroid. So for example, in this case, visually it is very obvious that all these data points are assigned to this centroid and all these data points are assigned to this centroid. And that's what is represented here in blue color and in this yellow color. The next step is to actually determine the central point or the actual centroid for these two clusters. So we have this one initial cluster, this one initial cluster, but as you can see, these points are not really the centroid. Centroid means it should be the central position of this data set, central position of this data set. So that is what needs to be determined as the next step. So the central point or the actual centroid is determined and the original randomly allocated centroid is repositioned to the actual centroid of this new clusters. And this process is actually repeated. Now what might happen is some of these points may get reallocated. In our example, that is not happening probably, but it may so happen that the distance is found between each of these data points once again with these centroids. And if it is required, some points may be reallocated. We will see that in a later example, but for now we will keep it simple. So this process is continued till the centroid repositioning stops, and that is our final cluster. So this is so after iteration, we come to this position, this situation where the centroid doesn't need any more repositioning, and that means our algorithm has converged. Convergence has occurred, and we have the cluster, two clusters, we have the clusters with a centroid. So this process is repeated. The process of calculating the distance and repositioning the centroid is repeated till the repositioning stops, which means that the algorithm has converged and we have the final cluster with the data points and the centroids. First of all, what are the types of clustering? There are primarily two categories of clustering: hierarchical clustering and then partitional clustering. And each of these categories are further subdivided into agglomerative and divisive clustering and k-means and fuzzy c-means clustering. Let's take a quick look at what each of these types of clustering are. In hierarchical clustering, the clusters have a tree-like structure, and hierarchical clustering is further divided into agglomerative and divisive. Agglomerative clustering is a bottom-up approach. We begin with each element as a separate cluster and merge them into successively larger clusters. So for example, we have A, B, C, D, E, F. We start by combining B and C, form one cluster, D and E, form one more. Then we combine D, E, and F, one more bigger cluster, and then add BC to that, and then finally A to it. Compared to that, divisive clustering or divisive clustering is a top-down approach. We begin with the whole set and proceed to divide it into successively smaller clusters. So we have A, B, C, D, E, F. We first take that as a single cluster and then break it down into A, B, C, D, E, and F. Then we have partitional clustering split into two subtypes, k-means clustering and fuzzy c-means. In k-means clustering, the objects are divided into the number of clusters mentioned by the number k. That's where the k comes from. So if we say k is equal to 2, the objects are divided into two clusters, C1 and C2. And the way it is done is the features or characteristics are compared, and all objects having similar characteristics are clubbed together. So that's how k-means clustering is done. We will see it in more detail as we move forward. And fuzzy c-means is very similar to k-means in the sense that it clubs objects that have similar characteristics together, but while in k-means clustering, two objects cannot belong to, or any object, a single object cannot belong to two different clusters, in c-means objects can belong to more than one cluster. So that is the primary difference between k-means and fuzzy c-means. So what are some of the applications of k-means clustering? K-means clustering is used in a variety of examples or variety of business cases in real life, starting from academic performance, diagnostic systems, search engines, and wireless sensor networks, and many more. So let us take a little deeper look at each of these examples. Academic performance. So based on the scores of the students are categorized into A, B, C, and so on. Clustering forms a backbone of search engines. When a search is performed, the search results need to be grouped together. The search engines very often use clustering to do this. And similarly, in case of wireless sensor networks, the clustering algorithm plays the role of finding the cluster heads, which collects all the data in its respective cluster. So clustering, especially k-means clustering, uses distance measure. So let's take a look at what is distance measure. So while these are the different types of clustering, in this video we will focus on k-means clustering. So distance measure tells how similar some objects are. So the similarity is measured using what is known as distance measure. And what are the various types of distance measures? There is Euclidean distance, there is Manhattan distance, then we have squared Euclidean distance measure and cosine distance measure. These are some of the distance measures supported by k-means clustering. Let's take a look at each of these. What is Euclidean distance measure? This is nothing but the distance between 2 points. So we have learnt in high school how to find the distance between 2 points. This is a little sophisticated formula for that, but we know a simpler one is square root of y2 minus y1 whole square plus x2 minus x1 whole square. So this is an extension of that formula. So that is the Euclidean distance between 2 points. What is the squared Euclidean distance measure? It's nothing but the square of the Euclidean distance, as the name suggests. So instead of taking the square root, we leave the square as it is. And then we have Manhattan distance measure. In case of Manhattan distance, it is the sum of the distances across the x-axis and the y-axis. And note that we are taking the absolute value so that the negative values don't come into play. So that is the Manhattan distance measure. Then we have cosine distance measure. In this case, we take the angle between the two vectors formed by joining the points from the origin. So that is the cosine distance measure. Okay, so that was a quick overview about the various distance measures that are supported by k-means. Now let's go and check how exactly k-means clustering works. Okay, so this is how k-means clustering works. This is like a flowchart of the whole process. There is a starting point, and then we specify the number of clusters that we want. Now there are a couple of ways of doing this. We can do by trial and error. So we specify a certain number, maybe k is equal to 3 or 4 or 5 to start with, and then as we progress we keep changing until we get the best clusters. Or there is a technique called elbow technique, whereby we can determine the value of k. What should be the best value of k? How many clusters should be formed? So once we have the value of k, we specify that, and then the system will assign that many centroids. So it picks randomly, that to start with, randomly that many points that are considered to be the centroids of these clusters. And then it measures the distance of each of the data points from these centroids and assigns those points to the corresponding centroid from which the distance is minimum. So each data point will be assigned to the centroid which is closest to it. And thereby we have k number of initial clusters. However, this is not the final clusters. The next step it does is, for the new groups, for the clusters that have been formed, it calculates the mean position, thereby calculates the new centroid position. The position of the centroid moves compared to the randomly allocated one. So it's an iterative process. Once again, the distance of each point is measured from this new centroid point, and if required, the data points are reallocated to the new centroids, and the mean position or the new centroid is calculated once again. If the centroid moves, then the iteration continues, which means the convergence has not happened. The clustering has not converged. So as long as there is a movement of the centroid, this iteration keeps happening. But once the centroid stops moving, which means that the cluster has converged or the clustering process has converged, that will be the end result. So now we have the final position of the centroid, and the data points are allocated accordingly to the closest centroid. I know it's a little difficult to understand from this simple flowchart, so let's do a little bit of visualization and see if we can explain it better. Let's take an example. If we have a data set for a grocery shop. So let's say we have a data set for a grocery shop, and now we want to find out how many clusters this has to be spread across. So how do we find the optimum number of clusters? There is a technique called the elbow method. So when these clusters are formed, there is a parameter called within sum of squares, and the lower this value is, the better the cluster is. That means all these points are very close to each other. So we use this within sum of squares as a measure to find the optimum number of clusters that can be formed for a given data set. So we create clusters, or we let the system create clusters of a variety of numbers, maybe of 10 clusters, and for each value of k, the within SS is measured, and the value of k which has the least amount of within SS or WSS, that is taken as the optimum value of k. So this is the diagrammatic representation. So we have on the y-axis the within sum of squares or WSS, and on the x-axis we have the number of clusters. So as you can imagine, if you have k is equal to 1, which means all the data points are in a single cluster, the within SS value will be very high because they are probably scattered all over. The moment you split it into 2, there will be a drastic fall in the within SS value, and that's what is represented here. But then as the value of k increases, the rate of decrease will not be so high. It will continue to decrease, but probably the rate of decrease will not be high. So that gives us an idea. So from here, we get an idea, for example, the optimum value of k should be either 2 or 3 or at the most 4. But beyond that, increasing the number of clusters is not dramatically changing the value in WSS because that pretty much gets stabilized. Okay, now that we have got the value of K, and let's assume that these are our delivery points, the next step is basically to assign two centroids randomly. So let's say C1 and C2 are the centroids assigned randomly. Now the distance of each location from the centroid is measured, and each point is assigned to the centroid which is closest to it. So for example, these points are very obvious that these are closest to C1, whereas this point is far away from C2. So these points will be assigned, which are close to C1 will be assigned to C1, and these points or locations which are close to C2 will be assigned to C2. And then, so this is how the initial grouping is done. This is part of C1 and this is part of C2. Then the next step is to calculate the actual centroid of this data, because remember, C1 and C2 are not the centroids. They've been randomly assigned points, and only thing that has been done was the data points which are closest to them have been assigned to them. But now in this step, the actual centroid will be calculated, which may be for each of these data sets somewhere in the middle. So that's like the mean point that will be calculated, and the centroid will actually be positioned or repositioned there. Same with C2. So the new centroid for this group is C2 in this new position, and C1 is in this new position. Once again, the distance of each of the data points is calculated from these centroids. Now remember, it's not necessary that the distance still remains or each of these data points still remain in the same group. By recalculating the distance, it may be possible that some points get reallocated. Like so. You see this? So this point earlier was closer to C2 because C2 was here, but after recalculating, repositioning, it is observed that this is closer to C1 than C2. So this is the new grouping. So some points will be reassigned. And again, the centroid will be calculated, and if the centroid doesn't change, so that is a repetitive process, iterative process. And if the centroid doesn't change, once the centroid stops changing, that means the algorithm has converged. And this is our final cluster, with this as the centroid, C1 and C2 as the centroids, these data points as a part of each cluster. So I hope this helps in understanding the whole process, iterative process of k-means clustering. So let's take a look at the k-means clustering algorithm. Let's say we have x1, x2, x3, n number of points as our inputs, and we want to split this into k clusters, or we want to create k clusters. So the first step is to randomly pick k points and call them centroids. They are not real centroids because centroid is supposed to be a center point, but they are just called centroids. And we calculate the distance of each and every input point from each of the centroids. So the distance of x1 from C1, from C2, C3, each of the distances we calculate. And then find out which distance is the lowest and assign x1 to that particular random centroid. Repeat that process for x2. Calculate its distance from each of the centroids C1, C2, C3 up to Ck, and find which is the lowest distance and assign x2 to that particular centroid. Same with x3 and so on. So that is the first round of assignment that is done. Now we have k groups because we have assigned a value of k. So there are k centroids, and so there are k groups. All these inputs have been split into k groups. However, remember, we picked the centroids randomly, so they are not real centroids. So now what we have to do? We have to calculate the actual centroids for each of these groups, which is like the mean position. Which means that the position of the randomly selected centroids will now change, and they will be the mean positions of these newly formed k groups. And once that is done, we once again repeat this process of calculating the distance, right? So this is what we are doing as a part of step 4. We repeat step 2 and 3. So we again calculate the distance of x1 from the centroid C1, C2, C3, and then see which is the lowest value and assign x1 to that. Calculate the distance of x2 from C1, C2, C3 or whatever up to CK and find whichever is the lowest distance and assign x2 to that centroid, and so on. In this process, there may be some reassignment. X1 was probably assigned to cluster C2, and after doing this calculation, maybe now x1 is assigned to C1. So that kind of reallocation may happen. So we repeat the steps 2 and 3 till the position of the centroids don't change or stop changing, and that's when we have convergence. So let's take a detailed look at each of these steps. So we randomly pick K cluster centers. We call them centroids because they are not really the centroids. So let us name them C1, C2 up to CK. And then step 2, we assign each data point to the closest center. So what we do, we calculate the distance of each X value from each C value. So the distance between X1, C1, distance between X1, C2, X1, C3. And then we find which is the lowest value, right? That's the minimum value we find, and assign X1 to that particular centroid. Then we go next to X2. Find the distance of X2 from C1, X2 from C2, X2 from C3, and so on up to CK, and then assign it to the point or to the centroid which has the lowest value, and so on. So that is step number 2. In step number 3, we now find the actual centroid for each group. So what has happened? As a part of step number 2, we now have all the points, all the data points grouped into K groups because we wanted to create K clusters, right? So we have K groups. Each one may be having a certain number of input values. They need not be equally distributed, by the way. Based on the distance, we will have K groups. But remember, the initial values of the C1, C2 were not really the centroids of these groups, right? We assigned them randomly. So now in step 3, we actually calculate the centroid of each group, which means the original point which we thought was the centroid will shift to the new position which is the actual centroid for each of these groups. Okay? And we again calculate the distance. So we go back to step 2, which is what? We calculate again the distance of each of these points from the newly positioned centroids. And if required, we reassign these points to the new centroids. So as I said earlier, there may be a reallocation. So we now have a new set or a new group. We still have K groups, but the number of items and the actual assignment may be different from what was in step 2 here. Okay, so that might change. Then we perform step 3 once again to find the new centroid of this new group. So we have again a new set of clusters, new centroids, and new assignments. We repeat this step 2 again. Once again we find, and then it is possible that after iterating through 3 or 4 or 5 times, the centroid will stop moving, in the sense that when you calculate the new value of the centroid, that will be same as the original value, or there will be very marginal change. So that is when we say convergence has occurred, and that is our final cluster. That's the formation of the final cluster. Alright, so let's see a couple of demos of K-means clustering. We will actually see some live demos in Python Notebook using Python Notebook. But before that, let's find out what's the problem that we are trying to solve. The problem statement is, let's say Walmart wants to open a chain of stores across the state of Florida, and it wants to find the optimal store locations. Now the issue here is, if they open too many stores close to each other, obviously they will not make profit. But if the stores are too far apart, then they will not have enough sales. So how do they optimize this? Now, for an organization like Walmart, which is an e-commerce giant, they already have the addresses of their customers in their database. So they can actually use this information or this data and use k-means clustering to find the optimal location. Now, before we go into the Python notebook and show you the live code, I wanted to take you through very quickly a summary of the code in the slides, and then we will go into the Python notebook. So in this block, we are basically importing all the required libraries like NumPy, Matplotlib, and so on. And we are loading the data that is available in the form of, let's say, the addresses. For simplicity's sake, we will just take them as some data points. Then the next thing we do is quickly do a scatter plot to see how they are related to each other with respect to each other. So in the scatter plot, we see that there are a few distinct groups already being formed. So you can actually get an idea about how the cluster would look and how many clusters, what is the optimal number of clusters. And then starts the actual k-means clustering process. So we will assign each of these points to the centroids and then check whether they are the optimal distance, which is the shortest distance, and assign each of the points, data points, to the centroids, and then go through this iterative process till the whole process converges. And finally, we get an output like this. So we have 4 distinct clusters, and which is, we can say that this is how the population is probably distributed across Florida state, and the centroids are like the location where the store should be, the optimum location where the store should be. So that's the way we determine the best locations for the store, and that's how we can help Walmart find the best locations for their stores in Florida. So now let's take this into Python notebook. Let's see how this looks when we are running the code live. Alright, so this is the code for k-means clustering in Jupyter Notebook. We have a few examples here which we will demonstrate how k-means clustering is used, and even there is a small implementation of k-means clustering as well. Okay, so let's get started. Okay, so this block is basically importing the various libraries that are required, like Matplotlib and NumPy and so on and so forth, which would be used as a part of the code. Then we are going and creating blobs which are similar to clusters. Now this is a very neat feature which is available in scikit-learn. Make blobs is a nice feature which creates clusters of data sets. So that's a wonderful functionality that is readily available for us to create some test data kind of thing. Okay, so that's exactly what we are doing here. We are using make blobs, and we can specify how many clusters we want. So centers we are mentioning here. So it will go ahead, and so we just mentioned 4. So it will go ahead and create some test data for us. And this is how it looks. As you can see visually, also we can figure out that there are 4 distinct classes or clusters in this data set, and that is what make blobs actually provides. Now from here onwards, we will basically run the standard k-means functionality that is readily available. So we really don't have to implement k-means itself. The k-means functionality or the function is readily available. You just need to feed the data and we'll create the clusters. So this is the code for that. We import k-means, and then we create an instance of k-means, and we specify the value of k. This n underscore clusters is the value of k. Remember, k-means, in k-means, k is basically the number of clusters that you want to create, and it is a integer value. So this is where we are specifying that. So we have k is equal to 4, and so that instance is created. We take that instance, and as with any other machine learning functionality, fit is what we use. The function, or the method rather, fit is what we use to train the model. Here there is no real training kind of thing, but that's the call. Okay, so we are calling fit, and what we are doing here, we are just passing the data. So x has these values, the data that has been created, right? So that is what we are passing here. and this will go ahead and create the clusters, and then we are using, after doing fit, we run the predict, which basically assigns for each of these observations which cluster it belongs to. All right, so it will name the clusters. Maybe this is cluster 1, this is 2, 3, and so on, or I will actually start from 0, cluster 0, 1, 2, and 3 maybe, and then for each of the observations it will assign based on which cluster it belongs to, it will assign a value. So that is stored in y underscore k means. When we call predict, that is what it does. And we can take a quick look at these y underscore k means, or the cluster numbers that have been assigned for each observation. So this is the cluster number assigned for observation 1, maybe this is for observation 2, observation 3, and so on. So we have how many? About, I think, 300 samples, right? So all the 300 samples, there are 300 values here. Each of them, the cluster number is given, and the cluster number goes from 0 to 3. So there are 4 clusters, so the numbers go from 0, 1, 2, 3. So that's what is seen here. Okay, now, so this was a quick example of generating some dummy data and then clustering that. Okay, and this can be applied if you have proper data. You can just load it up into X, for example, here, and then run the k-means. So this is the central part of the k-means clustering program example. So you basically create an instance and you mention how many clusters you want by specifying this parameter n underscore clusters, and that is also the value of k, and then pass the data to get the values. Now, the next section of this code is the implementation of a k-means. Now, this is kind of a rough implementation of the k-means algorithm. So we will just walk you through. I will walk you through the code at each step, what it is doing, and then we will see a couple of more examples of how k-means clustering can be used in maybe some real life examples, real life use cases. All right. So in this case here, what we are doing is basically implementing the k-means clustering, and there is a function or a library calculates for a given 2 pairs of points. It will calculate the distance between them and see which one is the closest and so on. So this is pretty much like what k-means does, right? So it calculates the distance of each point or each data set from predefined centroid, and then based on whichever is the lowest, this particular data point is assigned to that centroid. So that is basically available as a standard function, and we will be using that here. So as explained in the slides, the first step that is done in case of k-means clustering is to randomly assign some centroids. So as a first step, we randomly allocate a couple of centroids, which we call here, we are calling as centers. And then we put this in a loop and we take it through an iterative process. For each of the data points, we first find out using this function pairwise distance argument. For each of the points, we find out which center or which randomly selected centroid is the closest, and accordingly we assign that data or the data point to that particular centroid or cluster. And once that is done for all the data points, we calculate the new centroid by finding out the mean position with the center position, right? So we calculate the new centroid, and then we check if the new centroid is the coordinates or the position is the same as the previous centroid. The positions we will compare, and if it is the same, that means the process has converged. So remember, we do this process till the centroids or the centroid doesn't move anymore, right? So the centroid gets relocated each time this reallocation is done. So the moment it doesn't change anymore, the position of the centroid doesn't change anymore, we know that convergence has occurred. So till then, so you see here, this is like an infinite loop. While true is an infinite loop. It only breaks when the centers are the same. The new center and the old center positions are the same. And once that is done, we return the centers and the labels. Now, of course, as explained, this is not a very sophisticated and advanced implementation, very basic implementation, because one of the flaws in this is that sometimes what happens is the centroid, the position will keep moving, but in the change will be very minor. So in that case also that is actually convergence, right? So for example, the change is 0.0001, we can consider that as convergence. Otherwise what will happen is this will either take forever or it will be never ending. So that's a small flaw here. So that is something, additional checks may have to be added here. But again, as mentioned, this is not the most sophisticated implementation. This is like a kind of a rough implementation of the k-means clustering. Okay, so if we execute this code, this is what we get as the output. So this is the definition of this particular function, and then we call that find underscore clusters, and we pass our data x and the number of clusters, which is 4. And if we run that and plot it, this is the output that we get. So this is, of course, each cluster is represented by a different color. So we have a cluster in green color, yellow color, and so on and so forth. And these big points here, these are the centroids. This is the final position of the centroids. And as you can see visually also, this appears like a kind of a center of all these points here, right? Similarly, this is like the center of all these points here, and so on. So this is the example, or this is an example of an implementation of k-means clustering. And next we will move on to see a couple of examples of how k-means clustering is used in maybe some real life scenarios or use cases. In the next example or demo, we are going to see how we can use k-means clustering to perform color compression. We will take a couple of images, so there will be 2 examples, and we will try to use k-means clustering to compress the colors. This is a common situation in image processing when you have an image with millions of colors, but then you cannot render it on some devices which may not have enough memory. So that is the scenario where something like this can be used. So before again we go into the Python notebook, let's take a look at quickly the code. As usual, we import the libraries and then we import the image, and then we will flatten it. So the reshaping is basically, we have the image information is stored in the form of pixels, and if the image is like, for example, 427 by 640 and it has 3 colors, so that's the overall dimension of the initial image. We just reshape it and then feed this to our algorithm, and this will then create clusters of only 16 clusters. So this colors, there are millions of colors, and now we need to bring it down to 16 colors. So we use k is equal to 16, and this is how, when we visualize, this is how it looks. These are all about 16 million possible colors. The input color space has 16 million possible colors, and we just compress it to 16 colors. So this is how it would look when we compress it to 16 colors, and this is how the original image looks, and after compression to 16 colors, this is how the new image looks. As you can see, there is not a lot of information that has been lost, though the image quality is definitely reduced a little bit. So this is an example which we are going to now see in Python notebook. Let's go into the Python notebook. And once again, as always, we will import some libraries and load this image called flower.jpg. Okay, so we'll load that, and this is how it looks. This is the original image, which has, I think, 16 million colors, and this is the shape of this image, which is basically, what is the shape is nothing but the overall size, right? So this is 427 pixel by 640 pixel, and then there are 3 layers, which is this 3 basically is for RGB, which is red, green, blue. So color image will have that, right? So that is the shape of this. Now what we need to do is data. Let's take a look at how data is looking. So let me just create a new cell and show you what is in data. Basically, we have captured this information. So data is what, let me just show you here. All right, so let's take a look at China. What are the values in China? And if we see here, this is how the data is stored. This is nothing but the pixel values. Okay, so this is like a matrix, and each one has about for this 427 by 640 pixels. All right, so this is how it looks. Now the issue here is these values are large, the numbers are large, so we need to normalize them to between 0 and 1. Right, so that's why we will basically create one more variable, which is data, which will contain the values between 0 and 1. And the way to do that is divide by 255. So we divide China by 255 and we get the new values in data. So let's just run this piece of code. And this is the shape. So we now have also, what we have done is we changed using reshape. We converted into the 3-dimensional into a 2-dimensional data set. And let us also take a look at how, let me just insert probably a cell here and take a look at how data is looking. All right, so this is how data is looking, and now you see this is the values are between 0 and 1. Right, so if you earlier noticed, in case of China, the values were large numbers. Now everything is between 0 and 1. This is one of the things we need to do. All right, so after that, the next thing that we need to do is to visualize this, and we can take random set of maybe 10,000 points and plot it and check and see how this looks. So let us just plot this. And so this is how the original, the color, the pixel distribution is. These are two plots. One is red against green and another is red against blue. And this is the original distribution of the color. So then what we will do is we will use k-means clustering to create just 16 clusters for the various colors and then apply that to the image. Now, what will happen is, since the data is large because there are millions of colors, using regular k-means may be a little time consuming. So there is another version of k-means which is called mini batch k-means. So we will use that, which processes in the overall concept remains the same, but this basically processes it in smaller batches. That's the only thing. Okay, so the results will pretty much be the same. So let's go ahead and execute this piece of code and also visualize this so that we can see that there are these. This is how the 16 colors would look. So this is red against green and this is red against blue. There is quite a bit of similarity between this original color schema and the new one, right? So it doesn't look very, very completely different or anything like that. Now we apply the newly created colors to the image, and we can take a look how this is looking now. We can compare both the images. So this is our original image and this is our new image. So as you can see, there is not a lot of information that has been lost. It pretty much looks like the original image. Yes, we can see that, for example, here there is a little bit, it appears a little dullish compared to this one, right? Because we kind of took off some of the finer details of the color, but overall the high level information has been maintained. At the same time, the main advantage is that now this is an image which can be rendered on a device which may not be that very sophisticated. Now let's take one more example with a different image. In the second example, we will take an image of the Summer Palace in China, and we repeat the same process. This is a high definition color image with millions of colors and also 3-dimensional. Now we will reduce that to 16 colors using k-means clustering, and we do the same process like before. We reshape it and then we cluster the colors to 16, and then we render the image once again, and we will see that the quality of the image slightly deteriorates. As you can see here, this has much finer details in this which are probably missing here, but then that's the compromise because there are some devices which may not be able to handle this kind of high density images. So let's run this code in Python Notebook. Alright, so let's apply the same technique for another picture which is even more intricate and has probably much complicated color schema. So this is the image. Now once again, we can take a look at the shape, which is 427 by 640 by 3. And this is the new data would look somewhat like this compared to the flower image. So we have some new values here, and we will also bring this. As you can see, the numbers are much big, so we will much bigger, so we will now have to scale them down to values between 0 and 1, and that is done by dividing by 255. So let's go ahead and do that and reshape it. Okay, so we get a two-dimensional matrix, and we will then, as a next step, we will go ahead and visualize this, how it looks, the 16 colors. And this is basically how it would look, 16 million colors. And now we can create the clusters out of this. The 16 k-means clusters we will create. So this is how the distribution of the pixels would look with 16 colors. And then we go ahead and apply this and visualize how it is looking for with the new just the 16 colors. So once again, as you can see, this looks much richer in color, but at the same time, and this probably doesn't have, as we can see, it doesn't look as rich as this one, but nevertheless the information is not lost, the shape and all that stuff. And this can be also rendered on a slightly a device which is probably not that sophisticated. Okay, so that's pretty much it. So we have seen two examples of how color compression can be done using k-means clustering, and we have also seen in the previous examples of how to implement k-means, the code to roughly how to implement k-means clustering, and we use some sample data using Blob to just execute the k-means clustering. All right, so with that, let's move on. So let's summarize what we have learned in this video. We started with an example of how we can apply k-means clustering, taking the cricket example. Then we understood what are the types of clustering, two major categories, hierarchical clustering and partitional clustering, which in turn had two subcategories, agglomerative and divisive, and then k-means and fuzzy C. Then we understood the distance measures, what are the different types of distance measures supported by k-means clustering, and we focused on k-means clustering. We talked about its applications and how exactly the process flow works for the k-means clustering, and then finally we ended up with a demo and a couple of use cases.
Currently today it's used in remote sensing. For example, they're used in the ETM devices. If you're a space buff, that's the enhanced thermatic mapper they use on satellites, which see far outside the human spectrum for looking at land masses. And they acquire images of the Earth's surface. The accuracy is higher and training time is less than many other machine learning tools out there. Also, object detection, multi-class object detection is done using random forest algorithms. A good example is traffic, where you're trying to sort out the different cars, buses, and things. And it provides a better detection in complicated environments. It's very complicated up there. And then we have another example, Connect. And let's take a little closer look at Connect. Connect, they use a random forest as part of the game console. And what it does is it tracks the body movements and it recreates it in the game. And let's see what that looks like. We have a user who performs a step. In this case, it looks like Elvis Presley going there. That is then recorded, so that Connect registers the movement, and then it marks the user based on accuracy. And it looks like we have Prince going on this one, from Elvis Presley to Prince. It's great. So it marks the user based on the accuracy. If we look at that a little closer, we have a training set to identify body parts. Where are the hands? Where are the feet? What's going on with the body? That then goes into a random forest classifier that learns from it. Once we've trained the classifier, it then identifies the body parts while the person's dancing. And it's able to represent that in a computer format, and then based on that, it scores the game and how accurate you are as being Elvis Presley or Prince in your dancing. Let's take a closer look at types of machine learning. Specifically, we're going to look at where the decision tree fits in with the different machine learning packages out there. We'll start with the basic types of machine learning. There's supervised learning, where you have lots of data and you're able to train your models. There's unsupervised learning, where it has to look at the data and then divide it based on its own algorithms without having any training. And then there's reinforcement learning, where you get a plus or negative if you have the answer correct. This particular tool belongs to the supervised learning. Let's take a closer look at that, what that means in supervised learning. Supervised learning falls into two groups, classification and regression. We'll talk about regression a little later and how that differs. This particular format goes underneath classification. So we're looking at supervised learning and classification in the machine learning tools. Classification is a kind of problem wherein the outputs are categorical in nature, like yes or no, true or false, or 0 or 1. In that particular framework, there's the KNN, where the NN stands for nearest neighbor, naive Bayes, the decision tree, which is part of the random forest that we're studying today. So why random forest? It's always important to understand why we use this tool over the other ones. What are the benefits here? And so with the random forest, the first one is there's no overfitting. If you use of multiple trees, reduce the risk of overfitting. Training time is less. Overfitting means that we have fit the data so close to what we have as our sample that we pick up on all the weird parts. And instead of predicting the overall data, you're predicting the weird stuff, which you don't want. High accuracy. Runs efficiently on large database. For large data, it produces highly accurate predictions. In today's world of big data, this is really important. And this is probably where it really shines. This is where why random forest really comes in. It estimates missing data. Data in today's world is very messy. So when you have a random forest, it can maintain the accuracy when a large proportion of the data is missing. What that means is if you have data that comes in from 5 or 6 different areas, and maybe they took one set of statistics in one area, and they took a slightly different set of statistics in the other, so they have some of the same shared data, but one is missing like the number of children in the house if you're doing something over demographics, and the other one is missing the size of the house. It will look at both of those separately and build 2 different trees, and then it can do a very good job of guessing which one fits better even though it's missing that data. Let us dig deep into the theory of exactly how it works. And let's look at what is random forest. Random forest, or random decision forest, is a method that operates by constructing multiple decision trees. The decision of the majority of the trees is chosen by the random forest as the final decision. And let's we have some nice graphics here. We have a decision tree, and they actually use a real tree to denote the decision tree, which I love. And given a random, some kind of picture of a fruit, this decision tree decides that the output is it's an apple. And we have a decision tree 2, where we have that picture of the fruit goes in, and this one decides that it's a lemon. And the decision 3 tree gets another image, and it decides it's an apple. And then this all comes together in what they call the random forest. And this random forest then looks at it and says, okay, I got 2 votes for apple, 1 vote for lemon. The majority is apples, so the final decision is apples. To understand how the random forest works, we first need to dig a little deeper and take a look at the random forest and the actual decision tree and how it builds that decision tree. In looking closer at how the individual decision trees work, we'll go ahead and continue to use the fruit example, since we're talking about trees and forests. A decision tree is a tree-shaped diagram used to determine a course of action. Each branch of the tree represents a possible decision, occurrence, or reaction. So in here we have a bowl of fruit, and if you look at that, it looks like they switched from lemons to oranges. We have oranges, cherries, and apples. And the first decision of the decision tree might be, is the diameter greater than or equal to 3? And if it says false, it knows that they're cherries because everything else is bigger than that. So all the cherries fall into that decision. So we have all that data we're training. We can look at that. We know that that's what's going to come up. Is the color orange? Well, it goes, orange or red? Well, if it's true, then it comes out as the orange. And if it's false, that leaves apples. So in this example, it sorts out the fruit in the bowl, or the images of the fruit. A decision tree, these are very important terms to know because these are very central to understanding the decision tree and when working with them. The first is entropy. Everything on the decision tree and how it makes a decision is based on entropy. Entropy is a measure of randomness or unpredictability in the data set. Then they also have information gain, the leaf node, the decision node, and the root node. We'll cover these other 4 terms as we go down the tree. But let's start with entropy. So starting with entropy, we have here a high amount of randomness. What that means is that whatever's coming out of this decision, if it was going to guess based on this data, it wouldn't be able to tell you whether it's a lemon or an apple. It would just say it's a fruit. So the first thing we want to do is we want to split this apart. And we take the initial data set, we're going to create a data set 1 and a data set 2. We just split it in two. And if you look at these new data sets, after splitting them, the entropy of each of those sets is much less. So for the first one, whatever comes in there, it's going to sort that data and it's going to say, okay, if this data goes this direction, it's probably an apple. And if it goes into the other direction, it's probably a lemon. So that brings us up to information gain. It is the measure of decrease in the entropy after the data set is split. What that means in here is that we've gone from one set, which has a very high entropy, to two lower sets of entropy. And we've added in the values of E1 for the first one and E2 for the second two, which are much lower. And so that information gain is increased greatly in this example. And so you can find that the information gain simply equals decision E1 minus E2. As we're going down our list of definitions, we'll look at the leaf node. And the leaf node carries the classification or the decision. So we look down here to the leaf node. We finally get to our set 1 or our set 2. When it comes down there and it says, okay, this object's gone into set 1, if it's gone into set 1, it's going to be split by some means, and we'll either end up with apples on the leaf node or a lemon on the leaf node, and on the right it'll either be an apple or lemons. Those leaf nodes, or those final decisions or classifications, that's the definition of leaf node in here. If we're going to have a final leaf where we make the decision, we should have a name for the nodes above it, and they call those decision nodes. A decision node has two or more branches. And you can see here where we have the 5 apples and 1 lemon, and in the other case the 5 lemons and 1 apple. They have to make a choice of which tree it goes down based on some kind of measurement or information given to the tree. And that brings us to our last definition. The root node, the topmost decision node, is known as the root node. And this is where you have all of your data and you have your first decision it has to make, or the first split in information. So far we've looked at a very general image with the fruit being split. Let's look and see exactly what that means to split the data and how do we make those decisions on there. Let's go in there and find out, how does a decision tree work? So let's try to understand this, and let's use a simple example, and we'll stay with the fruit. We have a bowl of fruit, and so let's create a problem statement, and the problem is we want to classify the different types of fruits in the bowl based on different features. The data set in the bowl is looking quite messy, and the entropy is high in this case. So if this bowl was our decision maker, it wouldn't know what choice to make. It has so many choices. Which one do you pick? Apple, grapes, or lemons? And so we look in here. We're going to start with a training set. So this is our data that we're training our data with. And we have a number of options here. We have the color, and under the color we have red, yellow, purple. We have a diameter, 331, 331, and we have a label, apple, lemon, grapes, apple, lemon, grapes. And how do we split the data? We have to frame the conditions to split the data in such a way that the information gain is the highest. And it's very key to note that we're looking for the best gain. We don't want to just start sorting out the smallest piece in there. We want to split it the biggest way we can. And so we measure this decrease in entropy, that's what they call it, entropy, there's our entropy, after splitting. And now we'll try to choose a condition that gives us the highest gain. We will do that by splitting the data using each condition and checking the gain that we get out of them. The conditions that give us the highest gain will be used to make the first split. So let's take a look at these different conditions. We have color, we have diameter, and if we look underneath that, we have a couple different values. We have diameter equals 3, color equals yellow, red, diameter equals 1. And when we look at that, you'll see over here we have 1, 2, 3, 4 threes. That's a pretty high selection. So let's say the condition gives us a maximum gain of 3. So we have the most pieces fall into that range. So our first split from our decision node is we split the data based on the diameter. Is it greater than or equal to 3? If it's not, that's false, it goes into the grape bowl. And if it's true, it goes into a bowl full of lemon and apples. The entropy after splitting has decreased considerably. So now we can make two decisions. If you look at, there's very much less chaos going on there. This node has already attained an entropy value of 0, as you can see. There's only one kind of label left for this branch. So no further splitting is required for this node. However, this node on the right still requires a split to decrease the entropy further. So we split the right node further based on color. If you look at this, if I split it on color, that pretty much cuts it right down the middle, and it's the only thing we have left in our choices of color and diameter too. And if the color is yellow, it's going to go to the right bowl, and if it's false, it's going to go to the left bowl. So the entropy in this case is now 0. So now we have 3 bowls with 0 entropy. There's only one type of data in each one of those bowls. So we can predict a lemon with 100% accuracy. And we can predict the apple also with 100% accuracy, along with our grapes up there. So we've looked at kind of a basic tree in our forest, but what we really want to know is how does a random forest work as a whole? So to begin our random forest classifier, let's say we already have built 3 trees. And we're going to start with the first tree that looks like this. Just like we did in the example, this tree looks at the diameter. If it's greater than or equal to 3, it's true, otherwise it's false. So one side goes to the smaller diameter, one side goes to larger diameter. And if the color is orange, it's going to go to the right, true. We're using oranges now instead of lemons. And if it's red, it's going to go to the left, false. We build a second tree very similar, but it's split differently. Instead of the first one being split by diameter, this one, when they created it, if you look at that first bowl, it has a lot of red objects. So it says, is the color red? Because that's going to bring our entropy down the fastest. And so, of course, if it's true, it goes to the left. If it's false, it goes to the right. And then it looks at the shape, false or true, and so on and so on. And tree 3 is the diameter equal to 1. And it came up with this because there's a lot of cherries in this bowl. So that would be the biggest split on there is the diameter equal to 1. That's going to drop the entropy the quickest. And as you can see, it splits it into true. If it goes false, and they've added another category, does it grow in the summer? And if it's false, it goes off to the left. If it's true, it goes off to the right. Let's go ahead and bring these 3 trees so you can see them all in one image. So this would be 3 completely different trees categorizing a fruit. And let's take a fruit. Now let's try this. And this fruit, if you look at it, we've blackened it out. You can't see the color on it, so it's missing data. Remember, one of the things we talked about earlier is that a random forest works really good if you're missing data, if you're missing pieces. So this fruit has an image, but maybe the person had a black and white camera when they took the picture. And we're going to take a look at this, and it's going to have, they put the color in there, so ignore the color down there. But the diameter equals 3. We find out it grows in the summer equals yes, and the shape is a circle. And if you go to the right, you can look at what one of the decision trees did. This is the third one. Is the diameter greater than or equal to 3? Is the color orange? Well, it doesn't really know on this one, but if you look at the value, it'd say true, and it'd go to the right. Tree 2 classifies it as cherries. Is the color equal red? Is the shape a circle? True, it is a circle. So this would look at it and say, oh, that's a cherry. And then we go to the other classifier, and it says, is the diameter equal 1? Well, that's false. Does it grow in the summer? True. So it goes down and looks at as oranges. So how does this random forest work? The first one says it's an orange. The second one said it was a cherry. And the third one says, it's an orange. And you can guess that if you have 2 oranges and one says it's a cherry, when you add that all together, the majority of the vote says orange. So the answer is, it's classified as an orange, even though we didn't know the color and we're missing data on it. I don't know about you, but I'm getting tired of fruit. So let's switch, and I did promise you we'd start looking at a case example and get into some Python coding. Today we're going to use the case, the iris flower analysis. Ooh, this is the exciting part as we roll up our sleeves and actually look at some Python coding. Before we start the Python coding, we need to go ahead and create a problem statement. Wonder what species of iris do these flowers belong to? Let's try to predict the species of the flowers using machine learning in Python. Let's see how it can be done. So here we begin to go ahead and implement our Python code. And you'll find that the first half of our implementation is all about organizing and exploring the data coming in. Let's go ahead and take this first step which is loading the different modules into Python. And let's go ahead and put that in our favorite editor, whatever your favorite editor is. In this case, I'm going to be using the Anaconda Jupyter Notebook, which is one of my favorites. Certainly there's Notepad++ and Eclipse and dozens of others, or just even using the Python terminal window. Any of those will work just fine to go ahead and explore this Python coding. So here we go. Let's go ahead and flip over to our Jupyter Notebook. And I've already opened up a new page for Python 3 code, and I'm just going to paste this right in there, and let's take a look and see what we're bringing into our Python. The first thing we're going to do is from the sklearn.datasets import load iris. Now this isn't the actual data, this is just the module that allows us to bring in the data, the load iris. And the iris is so popular, it's been around since 1936 when Ronald Fisher published a paper on it, and they're measuring the different parts of the flower, and based on those measurements predicting what kind of flower it is. And then if we're going to do a random forest classifier, we need to go ahead and import a random forest classifier from the sklearn module. So sklearn.ensemble import random forest classifier. And then we want to bring in two more modules. And these are probably the most commonly used modules in Python and data science with any of the other modules that we bring in. And one is going to be pandas. So we're going to import pandas as PD. PD is the common term used for pandas. And pandas is basically creates a data format for us where when you create a pandas data frame, it looks like an Excel spreadsheet. And you'll see that in a minute when we start digging deeper into the code. Panda is just wonderful because it plays nice with all the other modules in there. And then we have NumPy, which is our numbers Python. And the numbers Python allows us to do different mathematical sets on here. We'll see right off the bat, we're going to take our NP and we're going to go ahead and seed the randomness with it with 0. So np.random.seed is seeding that as 0. This code doesn't actually show anything. We're going to go ahead and run it because I need to make sure I have all those loaded. And then let's take a look at the next module on here. The next 6 slides, including this one, are all about exploring the data. Remember I told you half of this is about looking at the data and getting it all set. So let's go ahead and take this code right here, the script, and let's get that over into our Jupyter Notebook. And here we go. We've gone ahead and run the imports. And I'm going to paste the code down here. And let's take a look and see what's going on. The first thing we're doing is we're actually loading the iris data. And if you remember up here, we loaded the module that tells it how to get the iris data. Now we're actually assigning that data to the variable iris. And then we're going to go ahead and use the df to define data frame. And that's going to equal PD. And if you remember, that's pandas as PD. So that's our pandas. And panda data frame. And then we're looking at iris data. And columns equals iris feature names. And we're going to do the df head. And let's run this so you can understand what's going on here. The first thing you want to notice is that our df has created what looks like an Excel spreadsheet. And in this Excel spreadsheet we have set the columns. So up on the top you can see the 4 different columns. And then we have the data, iris.data, down below. It's a little confusing without knowing where this data is coming from. So let's look at the bigger picture. And I'm going to go print. I'm just going to change this for a moment. And we're going to print all of iris and see what that looks like. So when I print all of iris, I get this long list of information. And you can scroll through here and see all the different titles on there. What's important to notice is that first off, there's a brackets at the beginning. So this is a Python dictionary. And in a Python dictionary, you'll have a key or a label. And this label pulls up whatever information comes after it. So feature names, which we actually used over here under columns, is equal to an array of sepal length, sepal width, petal width. These are the different names they have for the 4 different columns. And if you scroll down far enough, you'll also see data down here. Oh goodness, it came up right towards the top. And data is equal to the different data we're looking at. Now there's a lot of other things in here like target. We're going to be pulling that up in a minute. And there's also the names, the target names, which is further down. And we'll show you that also in a minute. Let's go ahead and set that back to the head. And this is one of the neat features of pandas and panda data frames is when you do df.head or the panda data frame.head, it'll print the first 5 lines of the data set in there, along with the headers if you have it. In this case, we have the column headers set to iris features. And in here, you'll see that we have 0, 1, 2, 3, 4. In Python, most arrays always start at 0. So when you look at the first 5, it's going to be 0, 1, 2, 3, 4, not 1, 2, 3, 4, 5. So now we've got our iris data imported into a data frame. Let's take a look at the next piece of code in here. And so in this section here of the code, we're going to take a look at the target. And let's go ahead and get this into our notebook, this piece of code, so we can discuss it a little bit more in detail. So here we are in our Jupyter notebook. I'm going to put the code in here. And before I run it, I want to look at a couple things going on. So we have df species. And this is interesting because right here you'll see where I have df species in brackets, which is the key code for creating another column. And here we have iris.target. Now these are both in the pandas setup on here. So in pandas we can do either one. I could have just as easily done iris and then in brackets target, depending on what I'm working on. Both are acceptable. Let's go ahead and run this code and see how this changes. And what we've done is we've added the target from the iris data set as another column on the end. Now what species is, this is what we're trying to predict. So we have our data, which tells us the answer for all these different pieces. And then we've added a column with the answer. That way when we do our final setup, we'll have the ability to program our neural network to look for this different data and know what a setosa is, or a varicolor, which we'll see in just a minute, or virginica. Those are the three that are in there. And now we're going to add one more column. I know, we're organizing all this data over and over again. It's kind of fun. There's a lot of ways to organize it. What's nice about putting everything onto one data frame is I can then do a printout and it shows me exactly what I'm looking at. And I'll show you where that's different, where you can alter that and do it slightly differently. But let's go ahead and put this into our script up to date now. And here we go. We're going to put that down here. And we're going to run that. And let's talk a little bit about what we're doing. Now, we're exploring data, and one of the challenges is knowing how good your model is. Did your model work? And to do this, we need to split the data up. And we split it into two different parts. They usually call it the training and the testing. And so in here, we're going to go ahead and put that in our database so you can see it clearly. And we've set it df. And remember, you can put brackets. This is creating another column. Is train, so we're going to use part of it for training. And this equals np, remember that stands for numpy, .random.uniform. So we're generating a random number between 0 and 1. And we're going to do it for each of the rows. That's where the length df comes from. So each row gets a generated number. And if it's less than 0.75, it's true. And if it's greater than 0.75, it's false. This means we're going to take 75% of the data, roughly, because there's a randomness involved, and we're going to use that to train it. And then the other 25%, we're going to hold off to the side and use that to test it later on. So let's flip back on over and see what the next step is. So now that we've labeled our database for which is training and which is testing, let's go ahead and sort that into two different variables, train and test. And let's take this code and let's bring it into our project. And here we go, let's paste it on down here. And before I run this, let's just take a quick look at what's going on here. Is we have up above, we created, remember there's our def.head, which prints the first 5 rows. And we've added a column is train at the end. And so we're going to take that, we're going to create two variables. We're going to create two new data frames. One's called train. One's called test, 75% in train, 25% in test. And then to sort that out, we're going to do that by doing df, our main original data frame with the iris data in it. And if df is train equals true, that's going to go in the train. And if df is train equals false, it goes in the test. And so when I run this, we're going to print out the number in each one. Let's see what that looks like. And you'll see that it puts 118 in the training module, and it puts 32 in the testing module, which lets us know that there was 150 lines of data in here. So if you went and looked at the original data, you could see that there's 150 lines. And that's roughly 75% in one and 25% for us to test our model on afterward. So let's jump back to our code and see where this goes. In the next two steps, we want to do one more thing with our data, and that's make it readable to humans. I don't know about you, but I hate looking at zeros and ones. So let's start with the features, and let's go ahead and take those and make those readable to humans, and let's put that in our code. Let's see, here we go, paste it in. And you'll see here we've done a couple very basic things. We know that the columns in our data frame, again this is a Panda thing, the DF columns, and we know the first four of them, 0, 1, 2, 3, that'd be the first four, are going to be the features or the titles of those columns. And so when I run this, you'll see down here that it creates an index, SEPA length, SEPA width, petal length, and petal width. And this should be familiar because if you look up here, here's our column titles going across, and here's the first four. One thing I want you to notice here is that when you're in a command line, whether it's Jupyter Notebook or you're running command line in the terminal window, if you just put the name of it, it'll print it out. This is the same as doing print features. And the shorthand is you just put features in here. If you're actually writing a code and saving the script and running it by remote, you really need to put the print in there. But for this, when I run it, you'll see it gives me the same thing. But for this, we want to go ahead and we'll just leave it as features because it doesn't really matter. And this is one of the fun thing about Jupyter Notebooks is I'm just building the code as we go. And then we need to go ahead and create the labels for the other part. So let's take a look and see what that. For our final step in prepping our data, before we actually start running the training and the testing, is we're going to go ahead and convert the species on here into something the computer understands. So let's put this code into our script and see where that takes us. Alright, here we go. We've set y equal to pd.factorize train species of 0. So let's break this down just a little bit. We have our pandas right here, PD. Factorize. What's factorize doing? I'm going to come back to that in just a second. Let's look at what train species is and why we're looking at the group 0 on there. And let's go up here, and here is our species. Remember this that we created this whole column here for species? And then it has Setosa, 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 and if you scroll down enough, you'd also see Virginica and Varicolor. We need to convert that into something the computer understands, zeros and ones. So the trained species of 0, because this is in the format of an array of arrays, so you have to have the 0 on the end. And then species is just that column. Factorize goes in there and looks at the fact that there's only 3 of them. So when I run this, you'll see that y generates an array that's equal to, in this case it's the training set, and it's 0s, 1s, and 2s representing the 3 different kinds of flowers we have. So now we have something the computer understands, and we have a nice table that we can read and understand. And now, finally, we get to actually start doing the predicting. So here we go. We have 2 lines of code. Oh my goodness, that was a lot of work to get to 2 lines of code. But there is a lot in these 2 lines of code. So let's take a look and see what's going on here and put this into our full script that we're running. And let's paste this in here. And let's take a look and see what this is. We're creating a variable CLF, and we're going to set this equal to the random forest classifier. And we're passing 2 variables in here, and there's a lot of variables you can play with. As far as these 2 are concerned, they're very standard. In jobs, all that does is to prioritize it. Not something to really worry about. Usually when you're doing this on your own computer, you do in jobs equals 2. If you're working in a larger or big data and you need to prioritize it differently, this is what that number does, is it changes your priorities and how it's going to run across the system and things like that. And then the random state is just how it starts. 0 is fine for here. But let's go ahead and run this. We also have clf.fit train features, y. And before we run it, let's talk about this a little bit more. clf.fit. So we're training it. We are actually creating our random forest classifier right here. This is the code that does everything. And we're going to take our training set. Remember, we kept our test off to the side. And we're going to take our training set with the features, and then we're going to go ahead and put that in, and here's our target, the y. So the y is 0, 1, and 2 that we just created, and the features is the actual data going in that we put into the training set. And let's go ahead and run that. And this is kind of an interesting thing because it printed out the random forest classifier and everything around it. And so when you're running this in your terminal window or in a script like this, this automatically treats this like just like when we were up here and I typed in Y and it printed out Y instead of print Y. This does the same thing. It treats this as a variable and prints it out. But if you were actually running your code, that wouldn't be the case. And what is printed out is it shows us all the different variables we can change. And if we go down here, you can actually see njobs equals 2. You can see the random state equals 0. Those are the two that we sent in there. You would really have to dig deep to find out all these different meanings of all these different settings on here. Some of them are self-explanatory if you kind of think about it a little bit, like max features is auto. So all the features that we're putting in there is just going to automatically take all 4 of them. Whatever we send it, it'll take. Some of them might have so many features because you're processing words. There might be like 1.4 million features in there because you're doing legal documents, and that's how many different words are in there. At that point, you probably want to limit the maximum features that you're going to process. And leaf nodes, that's the end nodes. Remember we had the fruit and we're talking about the leaf nodes. Like I said, there's a lot in this. We're looking at a lot of stuff here. So you might have, in this case, there's probably only 3 leaf nodes, maybe 4. You might have thousands of leaf nodes, at which point you do need to put a cap on that and say, okay, you can only go so far, and then we're going to use all of our resources on processing this. And that really is what most of these are about, is limiting the process and making sure we don't overwhelm a system. And there's some other settings in here. Again, we're not going to go over all of them. Warm start equals false. Warm start is if you're programming it one piece at a time externally. Since we're not going to have we're not going to continually to train this particular learning tree. And again, like I said, there's a lot of things in here that you'll want to look up more detail from the sklearn. And if you're digging in deep and running a major project on here. For today though, all we need to do is fit or train our features and our target Y. So now we have our training model. What's next? If we're going to create a model, we now need to test it. Remember, we set aside the test feature, test group, 25% of the data. So let's go ahead and take this code and let's put it into our script and see what that looks like. Okay, here we go. And we're going to run this, and it's going to come out with a bunch of 0s, 1s, and 2s, which represents the 3 types of flowers, the Setosa, the Virginica, and the Versicolor. And what we're putting into our predict is the test features, and I always kind of like to know what it is I am looking at. So real quick, we're going to do test features. And remember, features is an array of sepal length, sepal width, petal length, petal width. So when we put it in this way, it actually loads all these different columns that we loaded into features. So if we did just features, let me just do features in here so you can see what features looks like. This is just playing with Pandas data frames. You'll see that it's an index. So when you put an index in like this into test features, into test, it then takes those columns and creates a Panda data frames from those columns. And in this case, we're going to go ahead and put those into our predict. So we're going to put each one of these lines of data, the 5.0, 3.4, 1.5, 0.2, and we're going to put those in and we're going to predict what our new forest classifier is going to come up with. And this is what it predicts. It predicts 0, 0, 0, 1, 2, 1, 1, 2, 2, 2. And again, this is the flower type, Setosa, Virginica, and Versicolor. So now that we've taken our test features, let's explore that. Let's see exactly what that data means to us. So the first thing we can do with our predicts is we can actually generate a different prediction model. When I say different, we're going to view it differently. It's not that the data itself is different. So let's take this next piece of code and put it into our script. So we're pasting it in here, and you'll see that we're doing predict, and we've added underscore proba for probability. So there's our clf.predict probability. So we're running it just like we ran it up here, but this time with this we're going to get a slightly different result, and we're only going to look at the first 10. So you'll see down here, instead of looking at all of them, which was 27, you'll see right down here that this generates a much larger field on the probability. And let's take a look and see what that looks like and what that means. So when we do the predict underscore proba, for probability, it generates 3 numbers. So we had 3 leaf nodes at the end. And if you remember from all the theory we did, this is the predictors. The first one is predicting a 1 for Setosa. It predicts a 0 for Virginica, and it predicts a 0 for Versicolor, and so on and so on and so on. And let's, you know what, I'm going to change this just a little bit. Let's look at 10 to 20, just because we can. And we start to get in a little different of data, and you'll see right down here, it gets to this one, this line right here. And this line has 0, 0.5, 0.5. And so if we're going to vote, and we have 2 equal votes, it's going to go with the first one. So it says Setosa gets 0 votes, Virginica gets 0.5 votes, Versicolor gets 0.5 votes, but let's just go with the Virginica since these 2 are equal, and so on down the list. You can see how they vary on here. So now we've looked at both how to do a basic predict of the features, and we've looked at the predict probability. Let's see what's next on here. So now we want to go ahead and start mapping names for the plants. We want to attach names so that it makes a little more sense for us. And that's what we're going to do in these next 2 steps. We're going to start by setting up our predictions and mapping them to the names. So let's see what that looks like. And let's go ahead and paste that code in here and run it. And this goes along with the next piece of code. So we'll skip through this quickly and then come back to it a little bit. So here's iris.targetNames. And if you remember correctly, this was the names that we've been talking about this whole time, the Setosa, Virginica, Versicolor. And then we're going to go ahead and do the prediction again. We could have just set a variable equal to this instead of rerunning it each time. But we're going to go ahead and run it again, clf.predictTestFeatures. Remember that returns the 0s, the 1s, and the 2s. And then we're going to set that equal to predictions. So this time we're actually putting it in a variable. And when I run this, it distributes, and it comes out as an array, and the array is Setosa, 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 Setosa. We're only looking at the first 5. We could actually let's do the first 25, just so we can see a little bit more on there. And you'll see that it starts mapping it to all the different flower types, the Versicolor and the Virginica in there. And let's see how this goes with the next one. So let's take a look at the top part of our species in here, and we'll take this code and put it in our script. And let's put that down here and paste it. There we go. And we'll go ahead and run it. And let's talk about both these sections of code here and how they go together. The first one is our predictions. And I went ahead and did predictions through 25. Let's just do 5. And so we have Setosa, 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 Setosa. That's what we're predicting from our test model. And then we come down here and we look at test species. I remember I could have just done test.species.head, and you'll see it says Setosa, 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 and they match. So the first one is what our forest is doing, and the second one is what the actual data is. Now, we need to combine these so that we can understand what that means. We need to know how good our forest is, how good it is at predicting the features. So that's where we come up to the next step, which is lots of fun. We're going to use a single line of code to combine our predictions and our actuals so we have a nice chart to look at. And let's go ahead and put that in our script in our Jupyter Notebook here. Let's see, let's go ahead and paste that in, and then because I'm on the Jupyter Notebook, I can do a Control minus so you can see the whole line there. There we go, resize it. And let's take a look and see what's going on here. We're going to create in pandas, remember PD stands for pandas, and we're doing a crosstab. This function takes 2 sets of data and creates a chart out of them. So when I run it, you'll get a nice chart down here. And we have the predicted species. So across the top, you'll see the Setosa, Versicolor, Virginica, and the actual species, Setosa, Versicolor, Virginica. And so the way to read this chart, and let's go ahead and take a look on how to read this chart here. When you read this chart, you have Setosa where they meet, you have Versicolor where they meet, and you have Virginica where they meet. And they're meeting where the actual and the predicted agree. So this is the number of accurate predictions. So in this case, it equals 30. If you add 13 plus 5 plus 12, you get 30. And then we notice here where it says Virginica, but it was supposed to be Versicolor. This is inaccurate. So now we have two inaccurate predictions and 30 accurate predictions. So we'll say that the model accuracy is 93. That's just 30 divided by 32. And if we multiply it by 100, we can say that it is 93% accurate. So we have a 93% accuracy with our model. I did want to add one more quick thing in here on our scripting before we wrap it up. So let's flip back on over to my script. In here, we're going to take this line of code from up above. I don't know if you remember it, but predicts equals the iris.target_names. So we're going to map it to the names, and we're going to run the prediction, and we read it on test features. But we're not just testing it, we want to actually deploy it. So at this point, I would go ahead and change this, and this is an array of arrays. This is really important when you're running these to know that. So you need the double brackets, and I could actually create data. Maybe let's just do 2 flowers. So maybe I'm processing more data coming in, and we'll put 2 flowers in here. And then I actually want to see what the answer is. So let's go ahead and type in preds and print that out. And when I run this, you'll see that I've now predicted 2 flowers that maybe I measured in my front yard as Versicolor and Versicolor. Not surprising, since I put the same data in for each one. This would be the actual end product going out to be used on data that you don't know the answer for. So that's going to conclude our scripting part of this. And let's just go ahead and take a look at the key takeaways with today's tutorial. We have solutions under classification. So we looked at where the random forest fits in the bigger model as far as supervised learning and part of the machine learning class, and in this case it's in classification. And why a random forest? The 3 main points: it has very little overfitting, if any. It has a high accuracy, and in my opinion one of the most powerful tools is it estimates missing data. We saw that with the missing color of the fruit. We talked about what is a random forest versus a tree. And then we went into how does a decision tree work, how does a random forest work, we put all those trees together, and then we took a look at some basic Python coding in the iris example.
With that, we have come to the end of this session. I hope it was interesting and informative. If you liked it, please let us know in the comment section below. Also, do subscribe to our channel and stay tuned for more from Simplilearn.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.